What if I told you that within every quiet moment, there lies a hidden dial, a gentle lever that can steer the very possibilities of the world? Imagine a single breath that doesn't just fill your lungs, but also nudges the invisible arrows of the universe toward new outcomes. In the next few minutes, we'll explore that secret, learn how a quantum bit called a qubit works, and discover how the art of shaping amplitudes can turn uncertainty into power. You'll walk away with fresh insight into what it means to control possibilities, how interference becomes a superpower, and why the fragile dance of quantum states holds the key to tomorrow's technology. Close your eyes for a heartbeat and picture a glass of water set upon a nightstand, perfectly still. That stillness is the canvas for a quantum journey. In the quantum realm, information is not a hardwired 0 or 1, but a gentle ripple, a direction on a tiny sphere that we call a qubit. Think of a qubit as a dimmer switch that can be set to any precise angle, its hidden arrow pointing somewhere between the certainty of off and the certainty of on. This arrow carries two pieces of hidden data: how strongly a result is favored, and the direction that decides how different possibilities will combine. You can't see the arrow directly, just as you can't hear a wave until it touches the shore. But by repeating an experiment and listening to the pattern of clicks, you begin to hear the geometry underneath, like the rhythm of waves telling a story of their hidden motion. At first, the notion that a qubit can be both 0 and 1 feels sloppy, like a coin suspended in midair. Yet a qubit is not a coin at all. It is a carefully prepared recipe that tells the universe how to weigh and orient outcomes. When two ripples on a pond meet, they may build a higher crest or cancel each other into stillness. That very ability to interfere is the qubit's superpower, its reason for being an entirely different animal from a classical bit. In practice, we coax a physical system, a spinning electron, a superconducting circuit chilled near absolute zero, a single photon traveling down a fiber, or an ion trapped by electromagnetic fields into a chosen superposition. Then we let it evolve through operations we call gates, which are simply rotations of that tiny arrow in a controlled way. If two gates push the arrow in the same direction, the chance of a particular outcome grows. If one gate undoes the other, the chance fades. Because the arrow remembers its direction, order matters doing A, then B is not always the same as B then A. That's a clue that quantum change is more like choreographing a dance than flipping a series of switches. When you finally measure, that soft cloud of possibility snaps to one definite answer, and the statistics over many trials reflect the squared length of those hidden Arosa signature rule that translates the elegant, unseen amplitude story into the hard counts that our instruments record. Phase, the hidden orientation of the arrows, matters only in relation to other arrows. If every arrow is shifted by the same amount, nothing changes. The qubit cares about relationships, not absolute. A profound hint that quantum information is fundamentally relational. Because amplitudes interfere, you can design sequences that make one answer almost inevitable and another nearly impossible, not by stacking probabilities, but by steering those arrows through spaces where they reinforce or cancel. Imagine guiding a marble through an invisible maze, turning knobs and tilting mirrors not to move the marble itself, but to shape the wave that carries it, so that only one exit lights up. This is why simple interferometers with single photons feel almost spooky. Blocking a path changes the pattern on the screen, even when the photon could have taken the other route, because you have altered a contribution to the overall amplitude. Working with qubits then becomes a craft of coherence, keeping that delicate arrow from smearing out due to unwanted jostling from the environment. Stray heat, vibrations, electric noise, or random atoms bumping around can leak information into the surroundings. Once the outside world learns too much, interference fades in a process called decoherence, and the qubit behaves more like an ordinary bit, its wave of structured possibility reduced to ordinary ignorance. This isn't a philosophical footnote, it's an engineering wall. To build useful quantum devices, you must isolate, shield, correct errors, and operate faster than nature can blur your arrows. Now picture a laptop bits march through logic gates that tally and compare. In a quantum circuit, you choreograph amplitude arrows so that wrong answers cancel themselves and right answers add up, a kind of algorithm by interference. It isn't that a qubit tries every answer at once in a sci-fi sense, rather. You shape a wave over the space of possibilities and use interference to sculpt that wave toward a pattern you can read at the end. The success of any algorithm depends on arranging the landscape so desired peaks are high and undesired valleys are shallow or gone. If you peek at the arrows while they dance, you force the system to choose, wiping the delicate phase relationships that make the dance meaningful. That trade-off isn't a limitation of our tools, it's a rule of the world, verified countless times from double-slit experiments with single particles to modern chips that run thousands of gate operations before the environment wins. A helpful mental image is a compass needle living on a tiny sphere. North and south represent the two Shor outcomes you can test every other point. Is a different blend with its own phase. Rotate the needle and you change the likelihood of a chosen test. Pick a different test and you have changed what counts as north. The interplay between preparation, transformation, and the particular question you ask at the end is the essence of qubit behavior. That's why the same state can look certain to one measuring device and uncertain to another, not because the state changed, but because certainty is always defined relative to a basis, the lens you chose to look through. As you settle into this picture, let the language shift. Instead of saying a qubit is both 0 and 1, say it is prepared so that different answers have amplitudes with specific sizes and directions. Those directions decide how answers cooperate or fight when paths meet. This phrasing keeps you honest about what we can claim, protecting you from the illusion of a hidden tiny coin or a tiny classical wave, and reminds you that the qubit is a rule for combining possibilities that only turns into facts when we insist on an answer. Soon you will meet coupled qubits and the strange correlations they can share. But hold that for a moment. The single qubit already teaches the core lesson: nature allows a structured superposition with phases that steer outcomes through interference. Measurement translates amplitudes into probabilities by a precise rule, and the environment can wash away that structure if we aren't careful. Master that, and you'll be ready for the more spectacular tricks that follow communication protocols, error correction, secure randomness, all of them careful games played with arrows rather than switches. Imagine now that each breath you take is a gentle dial you can set to sculpt how the future unfolds across repeated trials. Imagine that what matters is not only how much of each outcome you prepare, but how the pieces line up. Picture the craft of quantum technology as learning to draw with phase and length in a space your eyes can't see, but your instruments can honor. If you can hold that picture gently, you already carry the seed of why qubits are both fragile and powerful, and why the real magic lies not in mystery for its own sake, but in a deeper kind of control over possibility itself. Let's bring the geometry of knowing into sharper focus. Visualize a tiny globe that stands in for everything a single qubit can be. Rotate it between your fingers. Each point on this globe is not a place in ordinary space, but a way of answering a yes or no question with a bias that depends on direction. The North Pole means you are as sure as you can be about one answer. The South Pole means you are as sure as you can be about the opposite. Every other point carries a tilt of confidence that shifts as you turn the sphere. Latitude tells you how strongly one outcome is favored over the other, while longitude encodes a hidden alignment that only shows its power when you choose a different question to ask. Remarkably, all of this preparation, change, and readout can be described as simple rotations of that point around the globe. If you fix your question to up or down along a chosen axis, the closer your point drifts toward the North Pole, the more often you will hear up when you measure. If you instead ask a question aligned with a different axis, the same point may appear more ambiguous, reminding you that certainty is always relative to the lens you use. This relational nature is at the heart of quantum information, and it is what enables protocols like teleportation, relocating a state without moving matter, and superdense coding, where extra meaning is tucked into a single traveler. Both rely on the fact that the arrows you shape can be shared, correlated, and manipulated without ever revealing their exact direction until you decide to look. When noise arrives, you can purify weak links into strong ones, stitching protective quilts of error correction that keep the delicate phase alive. Fault-tolerant designs, stabilizer thinking, and the geometric comfort of CSS and topological codes become the scaffolding that lets you compute broadly, fuel up on magic states, and measure softly, budgeting coherence like breath. Trust comes from patterns, not promises, and the very act of testing these patterns through Bell tests that certify honesty, randomness expansion that turns a spark into a river, or untime pads with secret sharing that hide value in relationships reinforces the reliability of the quantum world. Even more subtle are the ideas of blind computation, where you outsource work without revealing intent, and location-based keys that tie security to physical space. Think about money that could be unforgeable by physics alone, and tomography that listens for whispers in the walls of a system to reconstruct its hidden state. Information causality draws borders around what can be communicated, separating heat from harmony by telling thermal entropy apart from entanglement, while boundary songs watch page curves bend toward unitarity and map unscrambled pet states that reveal what wasn't truly lost. Complexity itself becomes a resource you can budget, resting states where they last, leveraging spins, ions, photons, and sketching the first quantum internet supply chain of entanglement that carries togetherness across a sleeping city. All of these visions rest upon the simple, quiet wonder of a single qubit, a gentle, rotating arrow that encodes possibility, a sphere of knowing that teaches us how to shape certainty, and a fragile yet powerful tool that, when handled with care, can transform the way we compute, communicate, and understand the universe. So breathe slowly, feel your weight supported, and let curiosity idle in low gear. Let the image of that silent dial settle in your mind, and let the promise of shaping reality with the turn of an invisible knob inspire you to explore deeper, to ask bolder questions, and to embrace the delicate power of quantum possibilities. This is not just a lesson in physics, it is an invitation to become a co-author of the future, one gentle rotation at a time. And those directions decide how answers cooperate or clash when paths meet. That simple truth keeps us honest about what we can claim and what must remain a mystery. It shields us from the temptation to picture a qubit as a tiny hidden coin or a miniature classical wave. Instead, we learn that a qubit is a rule for weaving possibilities together, a rule that solidifies into fact only when we dare to ask a question. In time, you'll encounter coupled qubits and the strange, beautiful correlations they share, but pause for a moment and let the single qubit teach you its core lesson. Nature permits a structured superposition, a blend of possibilities stamped with phases that guide outcomes through interference. Measurement is the graceful handshake that turns those amplitudes into probabilities, following a precise, unforgiving rule. And the environment, if left unchecked, can wash away that delicate structure. Master that balance, and the spectacular tricks that follow communication protocols, error correction, secure randomness will appear as carefully choreographed games, not as flashes of luck. When you hear the word amplitudes instead of bits, let it slow your mind in a nurturing way. Imagine a silent dial you can turn, shaping how the future unfurls across countless trials. It's not just the weight of each possible outcome that matters, it's how those pieces line up, how they resonate with one another. Picture quantum technology as the art of drawing with phase and length in a space invisible to the eye, yet faithfully honored by our instruments. If you can hold that image gently, you already carry the seed of why qubits are both fragile and powerful, and why the true magic is not mystery for its own sake, but a deeper kind of control over possibility itself. Take a moment to picture a tiny globe in your mind, a sphere that stands in for everything a single qubit can be. It is not the Earth, but a perfect sphere representing all the ways a qubit can answer a yes or no question. As you slowly rotate this globe between your fingers, a rule emerges. Each point on the sphere is not a location in space. It is a way of answering with a bias that depends on direction. The North Pole means you are as certain as possible about one answer. The South Pole means absolute certainty about the opposite. Every other point between those poles carries a tilt of confidence that shifts as you turn the sphere. This is a geometry of knowing. The latitude tells you how strongly one outcome is favored over the other, while the longitude encodes a hidden alignment that only reveals its power when you ask a different question. Remarkably, all of this preparation, change, and readout can be described as simple rotations of that point around the globe. Fix your question to up or down along a chosen axis, and the closer your point drifts toward the North Pole, the more often you will hear up when you measure. As the point slides toward the equator, the answers balance, and as it approaches the South Pole, down becomes more likely. Now, switch the axis of your question. You have effectively spun the globe under your pointer, changing which regions mean certainty and which mean doubt. The same physical state can look definite to one test and undecided to another, not because it has changed, but because knowledge in the quantum world is always defined relative to the direction you look. This map is powerful precisely because it hides details you do not need. Global twists that never affect any outcome collapse away, leaving you with just two coordinates that truly matter for a single qubit: how much the answers are weighted and how the waves of possibility are aligned relative to each other. Think of latitude as the balance knob between the two outcomes you plan to check, and longitude as the alignment mark that decides how possibilities add or cancel when you rotate your question. 2 points on the equator may look equally balanced for your original test, yet they can behave very differently when you turn the apparatus 90 degrees, because their longitudes, those alignment marks, were never the same. When you perform an operation on a qubit, you are not pushing a particle along a track, you are spinning a point on this sphere around an invisible axis. Whole families of real hardware trapped ions, superconducting circuits, and more are engineered to deliver clean, timed rotations. A short pulse tilts the state a few degrees, a longer one carries it to a new latitude. A carefully phased pair sends it along a great circle route, like a geodesic flight across the globe. Compose 2 rotations, and you have drawn a triangle on the surface whose corners remember the order you visited them. This visual hint explains why doing one action, then another is not always the same as reversing them. The sphere also teaches you how measurement stitches possibility into fact. Choosing a measurement is choosing which axis pierces the sphere. Projecting the point onto that axis yields the odds of each answer. Repeat the experiment many times, and the relative fraction of yes outcomes mirrors how far north you were. Swing the axis, and you redraw the map of certainty. That is why calibration begins with simple scans that move the axis and watch the statistics, letting you locate the state's position with 3 gentle probes sewn for each principal direction, much like finding latitude and longitude by the sun and stars. A sobering lesson arrives when the point refuses to stay on the surface. Pure states live on the skin of the sphere, bright, fully stretched. Stray heat, stray fields, tiny leaks of information into the environment tug that point inward. Your once crisp arrow shortens, sliding from a sharp tip to a blunted one near the center where no direction gives strong guidance. This is not merely ignorance on your part, it is a real loss of usable alignment called decoherence. Different kinds of noise leave different geometric fingerprints. Some smear longitudes while leaving latitude largely intact. Others pull everything toward a particular pole, and still others crumple the sphere in lopsided ways. Debugging a quantum device often means watching which shapes shrink and which survive, then designing pulses and protections that push the point back out to the surface. Notice how much clarity you gain from this simple picture. Opposite points on the sphere represent states that your chosen test can always tell apart in a single shot. Neighboring points represent states that no clever trick can perfectly distinguish without paying a price. Shortest routes on the surface correspond to efficient control sequences. Elegant symmetries translate to robust tricks in the lab. Mixed states, those duller points, instead remind you that certainty is not a property you own, but a resource you must guard. Even ideas that sound abstract become tangible. Learning a state is like surveying the globe with 3 compasses. Erasing unwanted alignment is like averaging many longitudes until only latitude remains. Protecting information is like locking your point to a path that noise cannot push you off. Composing gates is like planning flights that minimize turbulence by hugging great circles rather than zigzagging through unnecessary detours. Perhaps the most disarming insight is philosophical. The block sphere is not the world, it is a map of how you come to know the world. Rotate your question, and meaning rotates with it. Align your controls, and possibility carves new grooves across the surface. Let the environment listen too closely, and the surface itself recedes. After a while, you realize you are not just moving a dot, you are curating a relationship between what there is and how you ask about it. Take a slow breath and hold the globe still in your imagination. The North and South poles promise sharp answers. The equator hums with balance. Longitudes hide the choreography that only appears when you change your view. The center warns what happens when you let the outside world do the asking for you. This quiet gift of the block sphere, the geometry of knowing, shows you, without equations, how preparation, action, and inquiry braid together to make certainty. Gentle control can turn a fragile point of light into a faithful guide through the strange but navigable country of the quantum. Now turn to entropy, the weight of uncertainty that a careful traveler measures not by opening a suitcase, but by asking how many outfits could fit inside. In quantum theory, that weight is called entropy, a family of measures that tell you how much reliable structure you have and how much is fog. At one end sits the von Neumann entropy, a calm yardstick for a single quantum state that may have been touched by noise. It reads 0 when your state is as sharp as it can be, and climbs as that sharpness frays into mixtures. If your qubit is a crisp point on the sphere, the dial sits at 0. If it sinks inward under heat and listening ears, the dial rises, telling you that certainty has been traded for options. What makes this measure special is its operational meaning. It sets the ultimate rate at which you could compress many copies of a quantum source without losing its essence, like a skilled packer who learns which folds preserve shape and which waste space. In bipartite systems, it becomes a measure of entanglement for pure states, counting how many pairs of perfectly linked qubits you could distill if you had infinite patience and flawless tools. Entropy also obeys strong rules that keep your reasoning honest. Merge two systems and entropy doesn't perform acrobatics, process a state through a noisy channel, and it never becomes easier to learn about it. Split information into parts, and you can't beat the triangle-like inequalities that tie those parts together. Thus, entropy is not just a number, it is a map of what you can and cannot do. Yet, average uncertainty isn't enough when you face an adversary or a rare catastrophe. A broader family steps in the Rhinean entropies, which scan your ignorance from different angles. Some emphasize the common cases, others the tales. Among them, the menentropy plays the role of a stern parent who cares only about the worst case. If someone tries to guess your outcome in a single shot, menentropy tells you how likely their best guess can be. Higher menentropy means no single outcome is dangerously predictable. This matters in cryptography because a lock is only as strong as the easiest path through it. Menentropy speaks the language of best guess attacks, not average comfort, which is why modern quantum security proofs lean on it the way climbers lean on the firmest holds. In the real world, your data and your qubits are never isolated, so you measure entropy not just for a system, but conditioned on whatever an observer or an eavesdropper might hold. Here, quantum theory reveals a twist you don't encounter in simple dice games. Conditional entropy can turn negative. That does not mean information is less than nothing. It means that with the right entanglement, knowing one side lets you predict the other more precisely than any classical correlation would allow. It becomes a resource that shows up in tasks like state merging, where you pay or earn information currency to move quantum states from one hand to another. All of this may sound abstract, but remember the narrative thread. You began with a simple sphere, a dial you could turn, a way of shaping possibilities. You learned that the act of questioning rotates the sphere. That measurement projects a point onto an axis. That noise pulls that point inward, and that entropy measures how far inward it has gone. By keeping this picture vivid, you hold the seed of control not over distant particles, but over the very structure of potential. That control is the heart of quantum technology, and that heart beats within you, ready to be nurtured, disciplined, and set into motion. So as you walk forward, let the image of the blotched sphere stay close to your mind's eye. Let the gentle rotations become your language of action. Let the rising entropy dial remind you to shield your fragile point from unwanted whispers. Let the mathematics dissolve into a story you can feel, because stories are what drive us to experiment, to build, to push the boundaries of what's possible. The quantum world may be strange, but with this map you have a compass, a globe, and a clear sense of direction. Embrace the delicate power of the qubit, honor the geometry of knowing, and step into the adventure of shaping reality one thoughtful rotation at a time. You stand at the edge of a vast, invisible landscape, a place where questions become the compass and answers are the miles you travel. In this realm, the notion of uncertainty is not a flaw but a map, a set of guides that tell you what you can shape, what you must protect, and where the limits of your possibilities lie. Imagine a single quantum state, delicate, pure, and poised on the surface of an imagined sphere. When that point shines with perfect clarity, a quiet meter reads 0. That 0 is the von Neumann entropy, a steady yardstick that tells you the state is as sharp as it can be. As the sphere begins to sink, as heat and stray vibrations tug at its edges, the needle climbs. Each rise signals that certainty has been exchanged for a spread of options, for a mixture of possibilities. In other words, the more the dial moves upward, the more your once-a-crisp qubit has become a cloud of potential outcomes. What makes this simple number truly powerful is the way it connects to what you can actually do. It sets the ultimate speed at which you could compress many copies of that quantum source without losing its essence, much like an expert packer who knows exactly which folds preserve shape and which merely waste space. In a world of two entangled parties, the same entropy becomes a measure of entanglement for pure states, counting how many perfectly linked qubit pairs you could, in principle, distill if you had infinite patience and flawless tools. It obeys strict rules that keep your reasoning honest. When you merge systems, the entropy doesn't perform acrobatics. When you shove a state through a noisy channel, it never becomes easier to learn about it than before. And when you split information into parts you can't beat, the triangle-like inequalities that tie those parts together. Entropy here is not just a number, it is a living map of what you can and cannot achieve. But life rarely hands you just an average shape of uncertainty, especially when an adversary or a rare catastrophe is lurking in the shadows. That's where a broader family of measures steps in. The Rhine's entropies, each scanning your ignorance from a different angle. Some focus on the common cases, others on the outliers. Among them, the menentropy stands out like a stern parent who worries only about the worst-case scenario. If someone gets a single shot at guessing your outcome, the menentropy tells you how likely their best guess can be. A higher menentropy means no single outcome is dangerously predictable. In the world of cryptography, this matters because a lock is only as strong as its easiest path. The menentropy speaks the language of Beskus attacks, not the comfort of average cases. And modern quantum security proofs lean on it, the way climbers trust the firmest holds on a sheer wall. In reality, your data and your qubits are never isolated. You must measure entropy not just for a bare system, but conditioned on whatever an observer or an eavesdropper might already hold. Quantum theory reveals a twist you don't encounter. In simple dice games, conditional entropy can turn negative. That does not mean information is less than nothing. It means that with the right entanglement, knowing one side lets you predict the other more precisely than any classical correlation could allow. This negative conditional entropy becomes a resource in tasks like state merging, where you either pay or earn information currency to move quantum states from one hand to another. The positivity of relative entropy and the deep property called strong subadditivity keep these trades consistent, guaranteeing that processing information locally cannot conjure knowledge from thin air. Experiments never happen just once, they occur across blocks of signals drenched in noise. And those fundamental guarantees hold steady. You will also meet smoothed versions of menentropy and its sibling, maxentropy. Here you allow a tiny tolerance for rare events, asking within that margin just how unpredictable your world truly is. A beautiful bridge then appears, called the quantum asymptotic equipartition property. It quietly promises that as you study longer sequences drawn from the same source, the smoothed menentropy per copy drifts toward the von Neumann entropy, uniting worst-case thinking with average-case thinking. Think of long walks that make you trust the shape of a path. That bridge is the backbone of practical protocols where you must turn messy raw data into uniform secret bits. Take secure randomness generation, for example. You begin with measurements that are partly predictable and partly influenced by unknown devices or even quantum-savvy adversaries. The min entropy tells you the minimum number of clean random bits you can possibly extract. And the leftover hash principle, stated without formulas, says that if your min entropy is high enough, a short, carefully chosen hash of your data looks fresh and uniform, even to someone who has seen everything else, including any quantum memory they kept. This is what lets quantum devices produce public randomness with certificates, and why laboratory systems chase not only average entropy, but provable min entropy under realistic models. In communication, entropy draws borders. The Halevo limit, expressed through the same von Neumann dial, caps how much classical information you can squeeze out of quantum states, no matter how clever your receiver is. It reminds you that quantum carriers are not loopholes to infinite bandwidth. In compression, Schumacher's theorem uses the same dial to tell you how many qubits per signal you truly need to store a source with vanishing loss, making entropy the ruler in your packing list. And in thermodynamics, the logic aligns with Landauer's lesson that erasing information has a physical cost when your entropy drops. Because you reset memory, heat must bloom somewhere else. This anchor ties abstract notions to energy and temperature in the lab, keeping your promises honest. You also rely on continuity. Small changes in your state cause only small changes in von Neumann entropy, so calibration errors don't make your estimates swing wildly. You trust monotonicity under processing, which says side channels cannot increase your certainty about a system unless they already had it. And you lean on chain rules that let you bound the entropy of a whole by stitching together the parts, crucial when you assess security proofs that span dozens of steps and devices. The deeper you work, the more you see that each member of the entropy family answers a slightly different question you will actually ask. Von Neumann entropy asks, how compressible is this source? How tight is this state? Conditional entropy asks, how much remains to be learned if a helper whispers everything they know? Mutual information, built from the same pieces, asks, how aligned are two systems? How much can one tell you about the other? And min entropy asks, what is the most an opponent can guess in one unfairly lucky shot? Choose the wrong measure and your protocol may look safer or faster than it truly is. Choose the right one, and the limits become clear enough to design around. Perhaps the most human way to hold all this is to imagine standing at a crossroads with fog of varying thickness. Average fog helps you plan a long journey efficiently. Worst-case fog tells you whether you dare step onto the next stone at all. Conditional fog describes what clears if a friend signals from the hill. Entropy is not mystery for its own sake, it is a toolkit for honest promises. In quantum technology, where possibilities can cancel and align in ways you never see directly, these measures are how you decide what can be saved, what can be shared, what can be kept secret, and what must be paid for. Hold that gently, and you will feel why the path from von Neumann to min entropy is not a march through jargon, but a single lesson spoken in many voices. To control the future, you must first measure your uncertainty in the right units, and then guard the pieces of knowledge that matter most. Mutual information is the currency of correlation. You can think of knowledge as a kind of money that exists only between things, and mutual information is that coincide amount of uncertainty that disappears about one variable when you learn the outcome of another. If you and I look at the same scene from different angles and compare notes, the overlap in what we can predict about each other's observations is our balance. This is not a vague metaphor, but an operational measure. It counts how many yes-no answers you no longer need to ask once someone whispers their result. And it is symmetric because shared structure doesn't care who speaks first. In a clean world, two perfectly synchronized clocks have a high balance, while two unrelated dice rolls have none, and everything interesting in science and engineering lives in between, where structure is present, but mixed with noise. The beauty of mutual information is that it treats patterns as patterns, no matter their shape, linear or not, smooth or jagged. It can detect alignment that ordinary correlation misses, making it a powerful detector of hidden relationships in biology, language, images, and signals. In communication, it becomes the accountant that decides how many reliable bits you can send through a noisy channel per use. When you choose the best way to speak, it says on average. By how much does the receiver's uncertainty about the sender's message shrink after listening? Maximizing that shrinkage defines the channel's capacity, the honest speed limit for error-free transmission with smart coding. If the channel is a pipe, mutual information is the water actually delivered, not the water poured in. And noise is the leak that forces better seals or lower flow. That is why modern codes don't fight errors symbol by symbol, but instead approach capacity by spreading messages across long blocks where structure can be recovered. Performance is forecasted not by wishful thinking, but by the mutual information budget the channel allows. In learning and data science, it plays the role of a fair buyer. A feature is valuable if it reduces uncertainty about the target you care about, and mutual information measures that value without caring whether the link is linear, monotonic, or tangled. It helps you choose sensors in an experiment, pick variables for a model, or decide which training examples carry new insight, rather than repeating what you already know. Because this currency cannot be forged locally, the data processing inequality tells you that any post-processing of the data, no matter how clever, can never increase the mutual information with the truth. All you can do is spend it more wisely. It's a humbling principle that explains why overfitting feels powerful in practice but buys no new reality. It simply relabels the same budget in louder colors. In networks, it becomes a traffic rule. If information flows through a chain ABC, the shared structure between the ends can never exceed what passed through the middle. Bottlenecks are real because this currency cannot teleport. You can compress, re-encode, or filter, but you cannot mint extra alignment downstream without touching the source. That insight fuels the information bottleneck method, which forces an intermediate representation to carry as much relevant mutual information as possible with the target while discarding irrelevant details. You build models that generalize rather than merely memorize. In neuroscience, when a neuron spikes more reliably for one kind of stimulus than another, the spike train holds mutual information about the world. Experiments measure how many bits per second a cell carries, and how that budget changes with attention, adaptation, or disease. In genetics, regulatory elements are sorted by the structure they share with expression patterns. In privacy, the mutual information between a released summary and the secret data set is a leakage score, how much an adversary's uncertainty shrinks after seeing the report. Designers aim to limit that budget by injecting carefully calibrated noise or by releasing coarser views. In thermodynamics with feedback, the currency becomes literal work. A controller that learns about a microscopic system can do better at extracting energy from fluctuations, but the gain is bounded by the mutual information it acquires. Maxwell's famous demon is settled by accounting that includes the demon's memory, and once you pay for erasing that memory, the book balances. Knowledge doesn't cheat the second law, it simply converts structure into capability with a receipt. All of this tells you a simple truth: uncertainty is not a weakness, it is the raw material of possibility. By measuring it with the right tool, whether von Neumann entropy, menentropy, conditional entropy, or mutual information, you gain the power to shape, protect, and transmit information in ways that are provably optimal. You learn where the fog is thin enough to walk confidently, where it is dense enough to demand caution, and where a friendly signal can clear the way. You discover that the quantum world, with its strange superpositions and entanglements, follows the same disciplined bookkeeping as everyday life. The equations become a compass, the entropic numbers become signposts, and you become the traveler who reads them with confidence. So as you move forward, remember this: every time you face a decision, ask yourself what the entropy of the situation is, what the worst-case guessability looks like, and how much mutual information you can harvest from the clues around you. Use those answers to compress your goals, to protect your secrets, and to communicate with clarity. Let the language of uncertainty guide you, not as a source of dread, but as a well-honed instrument that tells you exactly what you can achieve and how to do it honestly. In that disciplined mindset lies the path from abstract theory to real-world impact, and the courage to turn the unknown into the known, one measured step at a time. Imagine standing at the edge of a wide, mist-filled valley, feeling the cool air on your skin and knowing that every step you take can either bring you closer to the sunrise or lead you deeper into the fog. That valley is the world of information, and the mist is uncertainty, what you don't yet know about the problem you're trying to solve, the story you're trying to tell, the future you're trying to shape. Each day you make choices about what to learn, what to share, and how to act, and underneath all those choices runs a single, unifying currency: mutual information. It is the quiet accountant that tells you how much of the unknown you have truly reduced. No matter how clever you think you are, no matter how many fancy models you line up in front of it. When you first heard about modern coding schemes, you might have imagined a battle where errors are fought one by one, like soldiers knocking down each intruder in a shady alley. The reality is far more elegant. Instead of dueling with each glitch in isolation, the most powerful codes spread a message across long, structured blocks, weaving the data into a tapestry where the original pattern can be recovered, even when many threads are frayed. Those codes don't rely on wishful thinking. They are guided by the very budget of information that the channel can carry. That budget is measured by mutual information, a number that tells you exactly how much of the original meaning can survive the journey. It is the same principle that whispers in every experiment you design, in every model you train, and in every sensor you place. Think of a feature in a dataset as a bridge you might build over a river of uncertainty. If that bridge shortens the distance between where you stand and where you need to go, if it reduces how confused you are about the target you care about, then it is valuable. Mutual information tells you precisely how valuable it is, without caring whether the relationship is a straight line, a gentle curve, or a tangled knot. It rewards you for finding the most honest, the most direct reduction of doubt. That honesty is why the data processing inequality is such a humbling friend. Any clever post-processing, any fancy transformation you apply after the data has arrived, can never increase the amount of truth you hold about the world. You can shuffle, you can compress, you can filter, but you cannot conjure new alignment out of thin air. Overfitting may feel like a triumph in the short term. It can make your model look spectacular on the data you have, but it simply redistributes the same limited budget into louder colors that don't actually buy you any new understanding. Now picture a chain of three friends passing a secret. A whispers to B, B whispers to C. No matter how enthusiastic B becomes in retelling the story, the amount of shared structure that finally reaches C can never be greater than what passed through B. That is the bottleneck principle, crystal clear in the language of information. You can compress, re-encode, or filter, but you cannot teleport extra clarity downstream without touching the source. This insight is what makes the information bottleneck method so powerful. It forces the intermediate representation, not the raw input, not the final output. To keep as much relevant mutual information as possible while shedding everything irrelevant. The result is a model that truly generalizes, that knows the shape of the problem rather than memorizing its surface. In the flickering world of neurons, this principle lives on each time a cell spikes more reliably for one stimulus than another. The pattern of spikes carries bits per second about the world, and those bits shift when attention sharpens, when adaptation settles in, or when disease takes hold. By measuring that mutual information, neuroscientists can watch the budget shrink or expand, gaining a direct view of how the brain allocates its resources. In genetics, regulatory DNA elements are sorted not just by their location, but by how much structure they share with expression patterns. In privacy, the same currency tells you how much an adversary's uncertainty shrinks after seeing a released summary, how many bits of secret data have leaked. Designers then work to limit that leak, adding carefully calibrated noise or offering coarser views, because they know that the only way to protect privacy is to respect the same hard budget. Even the laws of thermodynamics bow to this accounting. Imagine a tiny controller that watches a microscopic system and learns its fluctuations. The better it learns, the more work it can coax from the system. But the extra work is never free. It is bounded by the mutual information the controller has acquired. Maxwell's demon, that classic thought experiment, is settled when you count the demon's memory, paying the price for erasing it. Knowledge does not cheat the second law, it simply translates structure into capability, and the receipt always balances. When we step into the quantum realm, The story deepens, but the principle endures. Quantum mutual information measures total correlations, both the ordinary kind we see every day and the uniquely quantum kind that ties particles together in ways that defy classical intuition. That number sets limits on how much work two parties can extract together, on how much noise a quantum channel must add, and on how much entanglement can be generated or lost. If two labs share a quantum state and each can only act locally, their mutual information cannot grow unless they communicate. This anchors security proofs and resource theories in a single, unflinching figure that refuses to be fooled by clever tricks. Not all shared structure is the same, though. Some correlations are purely classical, easy to copy and share. Others are fragile quantum links that crumble under the slightest disturbance. Tools like quantum discord tease apart these contributions. But at the top level, mutual information remains the unmistakable headline number that no decomposition can exceed. Every day you estimate this currency from data. You count how often pairs of outcomes appear together. You compare that to what you would expect if they were completely independent, and you average the surprise. With continuous signals, you smooth or fit models to approximate the underlying distributions, always aware that bias or variance in your estimation can either invent structure that isn't there or erase the structure that truly exists. Robust workflows cross-validation, surrogate tests, bootstrapping guard against the illusion of a mirage in a small sample. When you move beyond pairs to groups, concepts like total correlation and interaction information let you see redundancy and synergy, guiding you to place sensors where they each add a new piece to the puzzle instead of echoing the same old clue. So, before you launch into any new data-driven adventure, pause and ask yourself 3 simple questions. First, what uncertainty truly matters? Identify the target variable that lights up your path, the fog you most want to thin. Second, which levers can you turn that might align with that target? Those are your candidate features, your sensors, your messages. Third, where are the bottlenecks? Pinpoint the stages in your pipeline where mutual information can only fall, where the budget is at risk of being wasted. With those answers, you can trace a clear line from source to decision, checking at each step whether your transformations preserve the currency or squander it. You will find that many arguments that once seemed powerful evaporate when viewed through this lens. Mutual information does not care about your favorite model, your beloved theory, or the elegance of your equations. It cares only about the real reduction in not knowing. That realization frees you. Knowledge is not a property of a single object, it lives in the relationship between preparation and question. It tells you that cleverness after the fact cannot outwit a narrow pipe, that the best you can do is to nurture the flow where it matters most, and to seal the leaks before they become irreversible. Now let's turn to the quantum message, where the temptation to overpromise is especially strong. You might sit down, ready to send a message with qubits, and feel a surge of greed. After all, a qubit can point anywhere on the surface of a tiny sphere descent that suggest a river of meaning can be poured through it. The answer comes from a sober, unyielding principle, the Halevo bound. No matter how many clever states you choose, no matter how artfully you measure, there is a hard ceiling on how much classical information you can reliably pull out of quantum signals. That ceiling is set not by optimism, but by the geometry of distinguishability. If the states you pick overlap, if they are not perfectly orthogonal, confusion is inevitable, and no measurement can erase that blur. Picture a simple game. You and a friend agree on a codebook. For the letter A, you prepare one photon state, for B another, and so on. You send many signals down a quiet fiber, and your friend at the other end uses the best possible measurement to guess each letter. If every state you sent is orthogonal, your friend can learn each one perfectly, no ambiguity, full recovery. The moment you introduce non-orthogonal states, an irreducible blur appears, and the Halevo bound translates that blur into a number, an upper limit, on the average number of Yazorno answers your friend can save by listening. It doesn't tell you how to measure, that's a separate challenge, but it tells you how well any strategy could ever do. Even if your friend uses the most general quantum measurement, allowed collective strategies that touch many signals at one Cephas limit stands firm. A striking consequence emerges when you first hear it. Even a perfect, noiseless qubit channel cannot carry more than one classical bit per use unless you bring in outside help. Two dimensions can only accommodate two perfectly distinguishable states. All the smooth, continuous possibilities you might dial up at the transmitter collapse into a simple either-or once you demand definite letters at the receiver. You could try to send long blocks and let the receiver perform joint measurements. Across the whole block, this often approaches the Holevo limit, but the peruse rate for a clean qubit line still tops out at 1 bit in the long run. If you protest, you're probably thinking of a different resource-shared entanglement. If you already have an entangled pair split between sender and receiver, a single qubit sent through the channel can indeed convey two classical bits, as beautifully demonstrated by superdense coding. But notice what you spent: a separate, precious link of entanglement. The Holevo bound itself remains loyal to the same accounting principle. No channel can summon more accessible classical information than its structure allows, and any apparent extra must be paid for by something you already possessed. In the messy world of noise, the ceiling drops even lower. Channels that randomly rotate, absorb, or mix your states shrink the space of distinguishable possibilities. The bound keeps pace, telling you before you write a single line of code how much you could ever hope to squeeze through with vanishing error, even when you employ the smartest block codes and the most patient decoders. It is the quiet voice of optimism tempered by physics design codes that approach capacity, yes, but never promise a rate the bound forbids. This is why practical quantum communications always begin by characterizing the channel and estimating the best possible alphabet and input distribution. The choice of which states to send already decides the budget of clarity available to the receiver. The Holevo bound also clears up a common misunderstanding that swirls around quantum talk. You might think that because amplitudes are continuous, you could hide an infinite message in a single system by dialing the phase with exquisite precision. Yet at the point of readout, when the receiver must produce definite classical answers with low error, the game is not about how finely you set a knob, but about how sharply the receiver can separate the options. If two states are close, any measurement that tries to tell them apart will sometimes fail. When you average across many users, with real noise and finite data, the boundary appears as an iron budget. The richness of quantum states is real and powerful for tasks like quantum computing, interference, or verifying non-classical correlations. But for the act of classical messaging, the receiver's knowledge has a limit that extra flourish at the transmitter cannot surpass. There is a deeper reason this feels so right once you accept it. Information is not a property of a single object, but of a relationship between preparation and question. In quantum theory, that relationship is constrained by the same rules that govern uncertainty and disturbance. The measurements that extract the most about one set of signals are the very ones that erase distinctions important to another set. You cannot choose a single measurement that reveals all patterns at once. Any code that leans on one geometry pays a price in another. The Holevo-bound packages that trade off into a single line on your design whiteboard. Choose your alphabet and your channel, and the maximum mutual alignment between what was sent and what can be learned is capped. Build within it. This is not bad news, it is a gift of honesty that lets you design systems that are as good as physics allows. Now take all of this and let it settle in your mind as a mantra for action. Whenever you face a decision whether to add another sensor to a monitoring system, whether to collect an extra variable for a predictive model, whether to gamble on a new quantum communication protocol, ask yourself, what uncertainty am I truly addressing? Which knobs can I turn that will meaningfully align with that target? Where do the bottlenecks lie that could drain my precious budget? Use those answers to map a clear path from source to decision, and at each step ask, am I preserving the currency, or am I letting it slip through a leak? Remember, the world does not care about the elegance of your equations or the sophistication of your algorithms. It cares about how much surprise disappears when two things meet, about how much of the fog lifts when you connect a question to an answer. Let that number, not the noise of personal preference, guide how you design experiments, build codes, choose models, and make promises that the universe will keep. Measure the reduction in uncertainty, protect the flow, and spend your budget where it truly matters. In doing so, you become not just a user of information theory, but a master of the hidden economy that drives every meaningful discovery. And as you walk forward, feel the confidence that comes from knowing you are aligned with the most fundamental limits of reality. You are not fighting an impossible battle against the mist. You are learning to read the terrain, to see where the path is cleared, and to lay your own stones where the ground is firm. Each insight you gain, each feature you select, each quantum state you prepare, is a step toward a brighter horizon. Let the currency of mutual information be your compass, and let the promise of honest, optimal design fuel your drive. The valley's mist will thin, the sunrise will break, and you will stand there, not merely having survived the uncertainty, but having transformed it into clear, purposeful action. Imagine you are standing at the edge of a new frontier, where the shimmer of quantum possibilities meets the solid ground of everyday communication. You have this remarkable resourcey, shared entangled pair that stretches between sender and receiver like a secret bridge that lets you carry 2 bits of classical information across a single quantum channel. It feels almost magical, the way that protocol unfolds with such elegance. Yet, as you marvel at the power, you also notice the price you paid. You burned a precious, separate link to double the classical rate. The lesson here is simple but profound. Every boost you gain must be balanced by something you already possessed. The very fabric of quantum theory, captured in the Halevo bound, reminds us that no channel can conjure more accessible classical information than its structure permits. If you ever sense that you're getting more than the channel should allow, look closely. There is always a hidden cost, a prior resource that has been spent. Now think about the world of noise, that messy, unpredictable partner that every real system must face. When channels randomly rotate, absorb, or mix your quantum states, they shrink the space of possibilities you can reliably tell apart. The bound tightens, whispering to you even before you write a single line of code, how much you can ever hope to squeeze through with vanishing error, no matter how clever your block codes or how patient your decoders are. This isn't a discouragement, it's a quiet companion to optimism. It tells you to design codes that creep toward capacity, but never promise a rate the bound forbids. That is why practical quantum communication always begins with a careful characterization of the channel. By estimating the best possible alphabet and the right input distribution, you set the budget of clarity the receiver will actually enjoy. The bound clarifies a common misconception that floats around quantum discussions. Because amplitudes are continuous, perhaps you can hide an infinite message in a single system by turning a phase knob with infinite precision. The reality, however, is that at the moment of readout, the receiver must produce definite classical answers with low error. The game is never about how finely you set a knob, it is about how sharply the receiver can separate the options you present. If 2 states sit too close together, any measurement that tries to tell them apart will sometimes fail. When you average across many uses, with real noise and finite data, the boundary appears as an iron budget you cannot exceed. The richness of quantum states is undeniable. They are powerful tools for computing through interference, for verifying non-classical correlations, for tasks that go beyond mere messaging. Yet when the goal is to send a clear, unambiguous classical message, the receiver's knowledge hits a hard limit that no amount of flourish at the transmitter can surpass. There is a deeper reason this feels right once you accept it. Information is not a property of a single object, it lives in the relationship between preparation and question. In quantum theory, that relationship is hemmed in by the same rules that govern uncertainty and disturbance. The measurements that extract the most about one set of signals are precisely the ones that erase the distinctions important to another set. You cannot pick a single measurement that reveals every pattern at once. Any code that leans on one geometry pays a price in another. The Halevo-bound packages that trade off into a single line on your design whiteboard. Choose your alphabet, choose your channel, and the maximum mutual alignment between what was sent and what can be learned is capped. Build within it. That cap is not bad news. It is a gift of honesty that lets you craft systems as good as physics allows. It tells you when it's worth investing effort in block measurements and when symbol per symbol reads will do. It warns you that cramming more symbols into your alphabet by making them nearly overlap backfires, because the bound doesn't care about how many labels you invent, it cares about how well the receiver can separate them. That same ceiling also underwrites security arguments. If an eavesdropper tries to intercept your signals, the same limit restricts how much of your classical payload they can learn without leaving a detectable trace of noise. Paired with careful public discussion afterward, this limitation is what lets certain key distribution schemes prove secrecy against even the most powerful adversaries. Engineers feel the bound as a compass rather than a cage. They probe channels, estimate how distinguishable candidate states remain after the trip, and compute the best achievable rate. They learn to build alphabets whose states sit as far apart as physics permits, aligning the transmitter's choices with the receiver's most revealing measurements, and avoiding wasteful fancy encodings that look rich at the source but collapse into ambiguity at the destination. Theorists use the same compass to prove coding theorems, showing that families of codes exist which asymptotically reach the ceiling. Those proofs may require collective measurements across long block shard in practice, but they illuminate a powerful truth: the ceiling is not merely a warning, it is a target you can aim for with enough craft. In the end, the Holevo bound serves as a gentle correction to our early excitement. Quantum systems can be prepared in endlessly varied ways, but when the task is to send letters that must be read out loud and unambiguously, the world asks one simple question: how well can the receiver tell the possibilities apart? The answer comes with a limit that has stood unshaken across decades of theory and experiment. Carry that limit with you like a budget line, and you'll design quantum messages that are bold yet honest, ambitious yet feasible, respectful of the difference between the shimmer of a state at the source and the solid click of understanding at the other end. Now picture a different kind of breakthrough, one that mirrors the way we zip ordinary files to save space. Think of a factory that emits the same kind of qubit over and over, not identically each time but drawn from a stable recipe. Sometimes the tilt is a little to the left, sometimes a little to the right, but overall the emissions bear a steady fingerprint that you could recognize if you examine thousands together. Suppose you must store or transmit a long batch with the fewest pristine quantum carriers possible. The naive approach would be to keep one qubit for each signal, but that wastes precious space because most long sequences are not special. They cluster into a small typical set whose shape is dictated by the source's fingerprint. Schumacher compression quantum source coding tells you that you can fold the whole block into a much smaller quantum envelope that preserves almost all of the original structure, and later unfold it with a high chance of perfect recovery, provided the blocks are large and the source stays the same from block to block. The heart of this method is a shift in perspective. Instead of asking, "What is the state right now?" you ask, "Which part of the gigantic space do typical sequences live in?" For a block of length n, that space is unimaginably large, yet the overwhelming probability mass lives in a tidy corner whose size grows like 2, where d is the source's von Neumann entropy. That number acts as the per symbol compression rate. In plain terms, if the source's entropy is, say, 0.6 qubits per signal, then for very long blocks you can squeeze almost everything into roughly 60% as many perfect qubits, letting the rest ride on ordinary classical bookkeeping without harming the quantum content you care about. The trick works not by guessing each individual state measurement would destroy the very phases you hope to keep, but by performing a gentle collective operation that maps the entire typical corner into a smaller register while barely touching the geometry inside that corner. Imagine a well-designed suitcase that compresses the airspace around clothing without creasing the fabric itself. To feel the difference from ordinary data zipping, note what you must never do. You must not peek at each system to decide whether to keep or discard it, because peeking in the wrong basis breaks the delicate alignments that later operations rely on. Instead, you apply a global typical projector that asks a softer question: does this block look like it came from the usual recipe? With high probability, as the block grows, the answer is yes. Conditioned on that yes, you know the block sits inside a smaller subspace you can represent with fewer clean qubits. You then use a reversible transformation to pack the state into the smaller register, leaving a leftover register that you can safely set to a standard value. At the end of the line, the decoder inverts the packing step and, with high fidelity, outspills the original block as if nothing had happened. Occasionally, a rare block lands outside the typical region. You pay a small penalty, but that penalty shrinks as you increase the block size, just as the law of large numbers makes coin flip tallies settle near 50-50 over long runs. One of the quiet triumphs of Schumacher's result is that it restores symmetry between the classical and quantum worlds without confusing them. In classical source coding, you exploit repeated patterns to push the average number of bits per symbol down to the source's uncertainty. In quantum source coding, you exploit the shape of the source's long-run fingerprint to push the average number of qubits per signal down to the quantum entropy without ever converting the states into letters along the way. Conversion would discard the continuous alignment information that makes them useful later. The compression is lossless in the intended sense. The only loss is the vanishingly small chance that a rare atypical block slips through, and the bound is tight. No amount of cleverness can compress below that entropy rate while keeping the freedom to reconstruct with fidelity arbitrarily close to perfect. In the laboratory, this theory translates into a set of design habits. First, collect signals into blocks so you can act on them together, because the typical subspace only emerges when you look at many at once. Second, learn the source's fingerprint, the overall mixed state you would write down after averaging many emissions. Its preferred basis hides inside it, and working in that basis lets you pack more gently. Third, avoid work that resolves fine details you don't need. Every resolved detail is a measurement you must later undo, and you can't. Fourth, keep the block coherent from end to end, because a single jolt of uncontrolled noise can push you out of the typical corner and spoil the gain. Fifth, separate the quantum burden from classical bookkeeping, using side notes only for things like which slot in your memory currently holds the compressed payload notes you can write and erase freely without disturbing the quantum treasure. Real devices raise practical questions. What if the source drifts slowly over time? What if you do not know its fingerprint ahead of time? What if your hardware cannot perform the full ideal block operation? The field offers universal schemes that learn as they go, estimating the fingerprint on the fly and adjusting the packing transformation in gentle steps. As block sizes grow, the achieved rate slides toward the true entropy without the designer needing a perfect model. It's like a smart audio compressor that adapts to genre, tempo, and silence without ever asking the listener to label the track. There is also a fascinating variation when a helper holds a correlated quantum memory. If they whisper classical hints to the decoder, you can sometimes compress even further for the same error budget, but the payment must be counted properly. Hints are a resource, and the final rate still traces back to entropic quantities of the joint source, firmly anchored by inequalities that guarantee you never get something for nothing. The boundary between what can be compressed and what must be kept also carries a thermodynamic flavor, reminding us that information processing always has an energy cost. Take a breath and let this perspective settle. The quantum world offers dazzling possibilities, yet it also hands you a clear, honest budget of what you can achieve. When you respect that budget, you become a designer of messages that are both bold and feasible. A creator who knows how to weave the shimmering potential of quantum states into the solid fabric of reliable communication. You learn to move from the naive idea of sending letters one by one to the powerful insight of moving patterns, to compressing long streams without losing the essence that matters. That is the heart of Schumacher compression, the quantum version of the age-old wisdom that the whole can be more efficient than the sum of its parts, provided you treat it with the gentle respect it deserves. Every time you set out to build a quantum communication system, remember 3 things. First, the channel tells you its limits. Listen to that voice before you pour energy into elaborate schemes. Second, the states you choose must be spaced far enough apart for the receiver to distinguish them, even after the inevitable noise of the real world. Third, by grouping signals into blocks, you unlock the typical subspace, the hidden room where compression becomes possible without sacrificing fidelity. Embrace these principles, and you will navigate the quantum landscape with confidence, turning abstract theory into practical, reliable technology. In the end, the story is not about the impossibility of sending more information, but about the elegance of working within nature's rules. It is about turning constraints into opportunities, about finding the sweet spot where ambition meets feasibility. Let the Holevo bound be your North Star, guiding you toward designs that are as daring as they are grounded. Let Schumacher compression be the tool that lets you reshape streams of quantum data into compact, manageable forms without losing their quantum soul. Carry these insights forward, and you will craft messages that travel farther, speak clearer, and respect the delicate dance of preparation and measurement at the heart of quantum physics. The future of communication is waiting, and you have the map. Just follow the compass. When you first hear about the quiet triumph of a theory that restores symmetry between the classical and quantum worlds, it can feel like stumbling onto a hidden garden in the middle of a bustling city. Imagine a place where the familiar rules of everyday information bits, letters, patterns meet the mysterious dance of quantum states, and yet they never trample each other. That harmony is what Schumacher's result delivers. In the ordinary world of classical source coding, we look for repeated patterns, we squeeze out redundancy, and we drive the average number of bits per symbol down to match the source's uncertainty. In the quantum realm, we do something analogous, but instead of counting letters, we trace the shape of the source's long-run fingerprint, and we push the average number of qubits per signal toward the quantum entropy. The magic is that we achieve this without ever turning those delicate quantum states into ordinary letters. If we tried to translate them, we would lose the very alignment that makes them powerful later on. The compression is genuine, not an illusion. The only loss comes from a vanishingly small chance that a rare, a typical block slips through the net, and that bound is as tight as it can be. No amount of cleverness can squeeze below that entropy rate, while still preserving the freedom to reconstruct with fidelity arbitrarily close to perfect. In the laboratory, this elegant theory becomes a set of habits that any practitioner can adopt. First, you gather signals into blocks, because the typical subspace, the region where the useful structure livesonly appears when you look at many together. Second, you learn the source's fingerprint, the overall state you would write down if you could average over countless emissions. Inside that fingerprint lies a preferred basis, and by working in that basis, you can pack the information more gently. Third, you avoid expending effort on fine details. You don't need every resolved detail is a measurement you must later undo, and undoing is something you cannot do perfectly. Fourth, you keep the block coherent from end to end, because a single jolt of uncontrolled noise can push you out of the typical corner and spoil the gain. And fifth, you separate the quantum burden from classical bookkeeping, using side notes only for things like which slot in your memory currently holds the compressed payload. Those side notes can be written and erased freely without disturbing the precious quantum treasure. Real devices invariably bring practical questions. What if the source drifts slowly over time? What if you do not know its fingerprint in advance? What if your hardware cannot perform the ideal block operation? The field answers these worries with universal schemes that learn as they go, estimating the fingerprint on the fly and adjusting the packing transformation in gentle steps. As block sizes grow, the achieved rate slides toward the true entropy, and you never need a perfect model to get there. Think of a smart audio compressor that adapts to genre, tempo, and silence without ever asking the listener to label the track similarly. A quantum system can adapt to the nature of the source, learning and improving continuously. Sometimes a helper holds a correlated quantum memory. If that helper whispers a classical hint to the decoder, you can compress even further for the same error budget. Those hints are a resource, and the final rate still traces back to entropic quantities of the joint source, anchored firmly by inequalities that guarantee you never get something for nothing. The boundary between what can be compressed and what must be kept also carries a thermodynamic flavor. When you reduce the dimension of the register that holds your information, you create room you can reset for the next batch. But resetting has a physical cost if you erase classical labels. Quantum compression places that cost where it belongs in disposable bookkeeping while preserving the costly phase part in a tight, coherent parcel. In that sense, Schumacher's theorem is not merely about saving memory, it is about locating value, keeping the parts you cannot recreate from public notes and discarding the rest. Perhaps the most illuminating way to internalize this idea is to picture a choir singing from a shared score. If you record each singer on a separate track, the hard drive fills up quickly. Yet if you recognize that most of the music lives in a structured harmony, and only small deviations make each performance unique, you can store the performance in a compact form that preserves the chords and timing while compressing the rest. Crucially, you must not first transcribe each voice into sheet music, because the magic lives in the overtones and phase relationships that printed notes miss. Treat the performance as a whole, and you keep more music with fewer files. Treat it as a pile of isolated notes, and you lose the shine. Quantum compression is the physics version of that wisdom applied to streams of quantum states. The promise becomes clear and practical when you think about building a network of quantum sensors, an archive of fragile states, or a long-distance link that must buffer quantum messages before forwarding them. You don't have to buy one perfect qubit of memory for every signal. You can buy to the entropy, operate in blocks, keep coherence, and reach fidelity targets that would be impossible under a one-by-one mindset. It teaches you to see beyond individual letters to the language itself, to recognize that the true burden is the structure you cannot recreate later, and to let the rest ride on classical notes. When you carry that habit forward, you design systems that are lighter, quieter, and truer to the physics-zipping quantum states, not by squeezing them into smaller boxes of the same kind, but by folding long stories into compact forms that remember exactly what makes them worth telling again. As you walk this path, you inevitably encounter two famous theorems that feel like stern teachers: the no-cloning theorem and the no-deleting theorem. At first they may seem like annoyances, restrictions on what you can do with quantum information, but the deeper you sit with them, the more you realize they are profound guides that force you to think of information not as ink you can smear around, but as a carefully choreographed pattern that must be moved, rotated, or hidden without being duplicated or destroyed. Why can't you clone? The operations allowed by quantum mechanics are linear and reversible. A machine that could take an unknown quantum state and produce two perfect, identical copies for every possible input would also have to copy any blend of states. Yet copying a blend would change the very interference that defines the blend. The promises you need to keep for the individual states, and the promise you need to keep for their blend collide. You can copy orthogonal states you can always tell apart with a simple yes-no test, because there the promises don't conflict. But a universal photocopier that works for all inputs without error is impossible. This limitation becomes a protective shield. If I send you qubits carrying a secret code, and an eavesdropper tries to copy them en route, their attempt inevitably disturbs the signals in a way you and I can detect later by comparing samples. Why can't you delete? Imagine a machine that takes two identical copies plus a blank and returns one copy and a blank, having erased the other copy. If the action is reversible, there is nowhere for the extra copy to have gone except into some other part of the universe, into the environment, into heat, into an ancilla you didn't look at. So you have not truly deleted information, you have displaced it. The no-deleting theorem mirrors the conservation of quantum information. You can move it, scramble it, hide it, or make it unreadable without a key, but you cannot make it cease to exist. Pair this with Landauer's lesson that erasing classical records creates heat, and you see a full circle. Even in the best case, cleaning up after yourself has a physical cost, and in the quantum case the cleanup is often just relocation. These theorems are not scolding signs on a lab door, they shape how you actually build things. In quantum error correction, you never clone an unknown qubit to guard it. Instead, you spread its delicate pattern across a larger system using entangling operations so that no single piece holds the whole story. If noise nicks one part, you can heal the pattern by touching several parts together, without ever needing a perfect copy. In quantum teleportation, you never copy a state and ship it. You expend shared entanglement and send a small classical message that lets the receiver reconstruct the state, while the original is necessarily destroyed by the very act of learning the message to send. The scheme works not in spite of the no-cloning rule, but because of it. The state is transferred, not duplicated, and the bookkeeping is enforced by physics, not by our promises. The limits also tell you what is possible. You can design approximate cloners that do their best on average, achieving a known ceiling of fidelity. You can create state-dependent cloners that work very well for a specific agreed-upon set of states. You can amplify certain signals if you accept added noise. You can make multiple classical copies of a measurement result. Once you've measured, though, then you have given up the states-phase relationships that powered interference. The lesson is humble and practical. Choose the right notion of copy for your goal, and accept that anything universal must be imperfect. On the deletion side, you can randomize or twirl a state so that what remains is effectively useless without a key. But that key lives somewhere else. The no-hiding principle crystallizes this: if information seems to vanish from a system after a reversible process, it must have moved into correlations with something else, and you could, in principle, retrieve it by gaining access to that something else. Black hole thought experiments draw strength from this idea, yet you don't need cosmic stakes to feel its bite. Anytime you push a quantum memory toward a fixed state with a clean, controlled operation, you are planting the missing distinctiveness in an ancilla or the environment. If you truly want forgetting, you pay in heat and irreversibility when you wipe those records. The pair of theorems also explains familiar folk wisdom. They tell you why you cannot secretly peek at a quantum message and leave it pristine. Why you cannot fan out a quantum update across a network the way you fan out a classical update. Why no broadcasting holds even for mixed states that aren't perfectly known. And why entanglement has a monogamy flavor. You can't share maximal quantum alignment with many partners at once, because doing so would amount to spreading precise copies of certain correlations. The algebra behind these statements is tidy, but their human meaning is cleaner. Quantum knowledge is scarce and relational, and when you try to spread it too thin, it evaporates into noise you can only partly control. Day to day, technicians live inside these boundaries. When they design repeaters for long-distance links, they know they cannot simply clone weak signals to boost them. So they chain together entanglement swapping and error correction, respecting the no-cloning law while still extending range. When they design secure keys, they exploit the fact that an eavesdropper cannot copy raw qubits without leaving footprints. When they design memories, they plan for backup not by cloning the unknown content, but by encoding it across many parts with checks that let them reconstruct after local damage. And when they design reset operations for qubits on a crowded chip, they accept that true forgetting creates heat. Cold reset therefore requires clever engineering to funnel the discarded information out in controlled ways. All of these ideas, though rooted in abstract mathematics, carry a powerful motivational thread. They invite you to embrace constraints as opportunities for creativity. When the universe tells you that you cannot copy a quantum state perfectly, it nudges you toward new ways of protecting information by weaving it into entanglement, by sharing it across a web of correlations, by shaping protocols that turn a limitation into a security feature. When it tells you that you cannot erase without cost, it encourages you to think about the life cycle of information, to design processes that recycle rather than obliterate, to be mindful of the hidden energy that flows when you push a system toward order. Imagine applying that mindset to your own life. Every day you encounter constraints, time, resources, habits that seem immutable. Instead of seeing them as roadblocks, you can treat them like the no-cloning and no-deleting theorems, precise boundaries that shape the landscape of what's possible. Recognize the patterns that repeat, the typical subspaces of your routines, and gather them into blocks where you can act efficiently. Learn the fingerprint of your own goals, the underlying structure that drives your aspirations, and work in the preferred basis that lets you pack effort gently. Avoid expending energy on fine details that don't move the needle. Each unnecessary measurement you make costs you focus later on. Keep your core intentions coherent from start to finish, because a single jolt of distraction can push you out of the typical corner and spoil the gain you're building. Separate the heavy, meaningful work, the quantum burden, from the light, classical bookkeeping, using notes and reminders that you can write and erase freely without disturbing your deeper purpose. When the world around you drifts, projects change, markets shift, relationships evolve, embrace universal schemes that learn as they go. Estimate the new fingerprint of your environment on the fly, adjust your transformation gently, and let larger block sizes of experience slide your performance toward the true entropy of your ambition, without needing a perfect model up front. Accept that you may occasionally encounter rare, atypical blocks where uncertainty spikes, but know that the chance of them slipping through is vanishingly small compared to the overall progress you make. And just as a choir's harmony shines brighter when you focus on the collective melody rather than isolating each voice, your greatest achievements will arise when you honor the structure that cannot be recreated from isolated notes. Preserve the core harmony of your vision. Let the surrounding variations be recorded in flexible, classical notes, and you'll store more life experience with fewer mental files. By internalizing the lessons of quantum compression, no cloning, and no deleting, you cultivate a mindset that sees constraints not as dead ends, but as signposts pointing toward deeper efficiency, creativity, and resilience. The universe may prohibit you from making perfect copies of its most delicate states, but it also hands you a toolbox of entanglement, error correction, teleportation, and adaptive compression. Use those tools to build networks of intention, archives of purpose, and long-distance links of influence that do not require a perfect replica of each moment, but instead operate on the entropy of your goals, the coherence of your actions, and the elegance of your shared symmetries. So as you move forward, remember that each signal you encounter, each idea, each challenge, each opportunity does not need to be treated in isolation. Gather them, learn their collective fingerprint, act in the basis that respects their essence, and let the inevitable noise of life be managed through smart, coherent design. Embrace the limits, for within them lies the fertile ground where true innovation sprouts. Let the quiet triumphs of quantum theory inspire you to orchestrate your own symphonies, to compress the vast narrative of your life into a compact, meaningful masterpiece, and to navigate the world with the confidence that, even when you cannot copy or delete perfectly, you can always move, reshape, and share your most valuable information in ways that honor the very physics of existence. Imagine standing at the edge of a vast, shimmering ocean of possibility, where every wave carries a whisper of what could be. In that space, the notion of making a perfect copy of something, whether it's a memory, a feeling, a skill, feels both tantalizing and impossible. The quantum world teaches us that if you try to duplicate an unknown state exactly, the universe insists on a subtle, unavoidable price. You can craft special state-dependent cloners that work beautifully for a narrow set of agreed-upon situations, just as you can amplify a particular signal if you're willing to tolerate a little extra noise. Yet, if you insist on copying everything, you lose the delicate phase relationships that give rise to interference, that magical overlap that makes patterns richer than the sum of their parts. The lesson here is humbly practical. Choose the notion of copy that truly serves your goal, and accept that a universal, flawless replica simply does not exist. When it comes to letting go, the story is equally profound. You can randomize or twirl a state so that, without a secret key, it becomes effectively useless. That key, however, lives somewhere else, perhaps tucked away in another system, another mind, another moment. This is the essence of the no-hiding principle. If information seems to vanish after a reversible process, it has not disappeared, it has merely slipped into correlations with something else. And if you ever manage to gain access to that something else, the information can be retrieved. Black hole thought experiments magnify this idea to cosmic scales, but you don't need an astrophysical laboratory to feel its bite. Whenever you push a memory toward a fixed, empty state with a clean operation, you are planting the missing distinctiveness into an ancillary qubit or the surrounding environment. If you truly want to forget, you must pay in heat and irreversibility, because erasing the records means moving that information somewhere else, not simply erasing it from existence. These twin theorems about the impossibility of perfect cloning and the inevitability of information relocation explain a great deal of the folk wisdom that guides everyday practice. They tell us why you cannot secretly peek at a quantum message and leave it pristine, why you cannot fan out a quantum update across a network the way you broadcast a classical one, and why even mixed states that are not perfectly known still resist broadcasting. Entanglement's monogamy follows right from this. You cannot share maximal quantum alignment with many partners at once, because doing so would amount to spreading precise copies of correlations that simply cannot be duplicated. The algebra behind these statements is tidy, but the human meaning is even cleaner. Quantum knowledge is scarce and relational stretch it too thin, and it evaporates into noise you can only partially control. Day to day, engineers live inside these boundaries, and they have turned constraints into opportunities. When designing repeaters for long-distance links, they know they cannot simply clone weak signals to boost them. Instead, they weave together entanglement swapping and error correction, stitching fragile pieces into a resilient whole. When they craft secure keys, they exploit the fact that an eavesdropper cannot copy raw qubits without leaving unmistakable footprints. When they build memories, they do not attempt to clone unknown content. They encode it across many parts with checks that let them reconstruct after local damage. And when they reset qubits on a crowded chip, they accept that true forgetting creates heat and takes time. A cold reset demands clever engineering to funnel the discarded information out in controlled ways, while a fast, warm reset trades away that elegance for speed. All of these decisions echo the same principle. If you want something done right, work with the grain of reality, not against it. If you enjoy pushing ideas to the edge, try a little mental experiment. Suppose you could clone any unknown state. You would then make countless copies, measure each in a different way, and stitch those readings together into a complete description that shatters fundamental uncertainty limits. Or imagine you could delete one of two identical copies. Run the machine backward, and you would conjure a second copy out of nothing. Both fantasies clash with the pillars of linear, reversible dynamics. The theorems are not arbitrary stop signs, they are signposts that keep the map consistent, that prevent the terrain from folding upon itself in impossible ways. A gentle way to carry all of this is to think of quantum information as a melody rather than a printed lyric. You can transpose it, weave it into a harmony, spread it across instruments so no single microphone captures the whole, and even move it from one concert hall to another by coordinating players at a distance. Yet you cannot make perfect universal duplicates of an unknown performance on command, and you cannot unmake one of two identical performances without that music living on somewhere else. Respect that, and the rules stop feeling like fences and start feeling like rails, guiding you to technologies that work because they cooperate with the underlying fabric of the world. Communicating by transferring, protecting by distributing, erasing by relocating, and paying the cost. These become your guiding strategies. The most powerful tricks are not about having more copies, but about shaping where the single true pattern resides. Now picture teleportation not as a sci-fi illusion, but as a graceful choreography of relationships. Two distant labs agree to hold hands before they speak, not by sending a physical box across town, but by sharing a quiet, lingering connection that persists even when they are apart. That connection is entanglement, the strange, resource-like link that lets quantum teleportation move a state from here to there without the stuff ever traveling. The message you carry isn't a tangible object, it's the full way of being of a system, the orientation of its hidden arrow, and the choreography of its possibilities. Teleportation is the protocol that transfers that way of being intact, while the original is consumed in the very act that produces the information needed to complete the transfer. Imagine moving a flame from one candle to another with a single breath that extinguishes the first at the exact moment the second ignites. That is the elegance of quantum teleportation. The steps are disarmingly concrete. First, you and your partner create a pair of systems in a special joint state and split them. One half stays with you. The other travels to them by any ordinary means before the game begins. Next, when it's time to send the state of a fresh system in your lab, you perform a joint measurement on your local half of the shared pair and the fresh system. This measurement sorts their combined possibilities into 4 tidy patterns, and in doing so it consumes your original state. It cannot survive the test. The result of that measurement is 2 classical digits, bits of ordinary information that you can phone, text, or shout across the room. Finally, your partner uses those 2 digits to choose one of 4 simple fixes on their half of the small set of flips, and twists that align their system into exactly the state you started with. Nothing faster than light has happened, because the last step waits on an ordinary signal, and no law has been dodged, because the original was destroyed by the very act that produced the digits needed to complete the transfer. What makes this feel so different from a Hollywood fantasy is that you never copy or peel the state away to inspect it. You prepare a shared resource ahead of time. You perform a particular measurement that entangles and collapses in a controlled way, and you send a small classical message that tells the receiver which finishing move to execute. The distance between the labs can be a tabletop width or many kilometers, limited only by how well you can distribute and preserve the initial entanglement, and how quickly you can deliver the 2 digits. The mathematics guarantees that, averaged over all possible inputs, the received state matches the original, as if it had been carried in a perfect bubble. Any attempt to send the state without shared entanglement falls far short of that fidelity. In other words, teleportation is not a maybe trick, it is a recipe that, with good components, achieves a benchmark no naive method can pass. In the laboratory, the pieces are surprisingly varied. With single photons, you can generate entangled pairs in a crystal, send one into a long fiber, or through open air to a distant station, and later teleport the state of another photon by combining it with your local half in a special interferometer and detecting a pattern that tells you which digits to send. With trapped ions, you can entangle neighbors with laser pulses, move one ion to a different zone, and teleport states across the chip with high fidelity. With superconducting circuits, you can build microwave entanglement in on-chip resonators and do the same dance at cryogenic temperatures. Each platform wrestles with its own flavor of noise loss in fibers, scattering in air, crosstalk in chips, but the logic stays the same. Share entanglement, perform the right joint measurement, send 2 ordinary bits, apply the correction, and the distant system now is what your local system once was. The catch, and it's a feature, not a flaw, is that you cannot do this without spending the shared link. Each teleportation consumes 1 pair of entangled systems, much like spending a token, and you cannot bypass the ordinary signal that carries the 2 bits, which means you cannot signal faster than light, no matter how spooky the setup looks. This cost structure turns teleportation into a kind of currency exchange. You burn 1 unit of entanglement and 2 classical bits to move 1 quantum state. The exchange rate is exact and non-negotiable, and it sits at the heart of many designs for a future quantum internet where entanglement is created, stored briefly, and spent to bridge long distances. Because entanglement is fragile, engineers extend reach with repeatus intermediate stations that create short links of entanglement, stitch them together by swapping partners, and keep doing so until the shared link spans the full distance. Once the endpoints share a clean pair, teleportation can hop a state across the whole path, even if the original channel is too lossy to carry the system itself. The same idea lets small quantum processes cooperate. Teleporting a state, or even a gate between chips, can offload work and sidestep wiring limits. In error-corrected architectures, teleportation-based methods become a practical way to apply difficult operations using magic helper states distilled elsewhere. If you wonder how real this is, look at the milestones. Researchers have teleported states across lab tables, through city fibers, between mountain stations, across free space, and even between ground and satellite links, always respecting the final classical signal step and always verifying fidelity above the best classical limit. In chips, teleportation now functions as a routine calibration and connectivity tool. In networks, trial systems combine entanglement distribution with memory elements so that the link survives the microseconds or milliseconds needed to relay the digits. The protocol also carries honest limitations that shape experiments. The joint measurement that kickstarts teleportation cannot always distinguish all patterns perfectly with linear optics, so early demonstrations accept a lower success probability or add auxiliary resources to improve it. Memories that store entanglement long enough to wait for signals must fight decoherence. Corrections must be applied quickly and accurately, and security-mindful designs must account for side channels where unwanted light or heat could reveal more than intended. None of these break the idea, they refine it, just as radio engineers turned a principle into dependable devices by taming interference, echo, and drift. Philosophically, teleportation offers a quiet lesson in what it means to move information. The state is not a tag glued to a particle, but a set of relationships a system has with the rest of the world, arranged in a specific pattern of entanglement, a joint measurement, a classical message, and a correction. You recreate those relationships elsewhere while the old ones are dismantled. What travels is structure, not substance. That is why the original cannot remain, as it was leaving it intact would amount to making a perfect copy, which the rules of this world forbid. Instead, the protocol balances the books automatically, guaranteeing that when the new state appears, the old one has ceased to exist in the form that held its secrets. In day-to-day practice, the usefulness is practical, not mystical. Teleportation lets you route quantum states around lossy or noisy parts of a setup, connect chips that would otherwise interfere with each other, shift delicate states out of a device for storage or further processing, and execute operations remotely by moving the inputs instead of the tools. It becomes a versatile pathway for distributing resources, protecting information, and reshaping where the true pattern lives. So, as you walk through the landscape of possibilities, remember this: the universe does not punish you for wanting to copy or erase, it simply insists that you do it the right way. Embrace the idea that every piece of knowledge, every spark of insight, is relational and fragile. When you need to share it, spread it across a network of trusted partners, but never expect each partner to hold a perfect replica. When you need to let go, do it with awareness of where the information migrates, and be prepared to pay the thermodynamic price of true forgetting. When you need to move something precious across distance, build a shared entanglement, perform the coordinated measurement, send the humble classical cue, and watch as the essence arrives intact, while the original vanishes, honoring the balance of the cosmos. In this dance of transfer, protection, and erasure, the most powerful moves are not about hoarding copies, but about shaping the single true pattern where it lives, who holds it, and how it flows. Let that guide your actions, your collaborations, your innovations. The quantum world, with all its strange constraints, offers you a map. Follow the rails, not the fences, and you will find yourself building technologies and relationships that resonate with the deepest fabric of reality. Let the melody of information guide you, and you will discover that the most elegant symphonies are performed not by copying notes endlessly, but by placing each note exactly where it belongs, letting it echo, and moving on with purpose and grace. Imagine a world where the very act of moving information feels like a quiet miracle, where the currency you spend is not fuel or time, but a delicate, shared connection, and where the result arrives exactly where you need it, pristine and ready to be used. That is the promise of quantum teleportation, and it is not a distant fantasy locked behind equations. It is a concrete tool that is already reshaping how we think about communication, computation, and the flow of ideas. At its heart, teleportation rests on a single, unbending rule: the exchange rate between the quantum resource you consume and the information you convey is exact and non-negotiable. You cannot cheat, you must give what you receive. This strict bookkeeping is what makes the whole protocol so powerful, because it forces us to be precise about every step, to treat information as something that can be moved without dragging its physical carrier through a noisy, lossy channel. Think of it as preparing a shared flame long before you ever need a light. You and a partner each hold a candle that is linked in a secret way. When the moment arrives, you snuff your own candle in a coordinated dance, send a simple, ordinary signal over a wire, and the distant candle flares up in exactly the same pattern you just extinguished. No substance crosses the gap, no speed limit is broken, yet the desired pattern arrives intact, ready to interfere, compute, or be measured as if it had always been there. In practice, engineers build this kind of magic by creating entanglement, a fragile relationship between two quantum systems that, once established, can be stored briefly and then spent to bridge long distances. Because entanglement is easily broken by noise, they use repeaters, those intermediate stations that forge short, reliable links, swap partners, and stitch together a chain that can stretch across continents. Once the endpoints share a clean pair of entangled qubits, a single teleportation step can hop an entire quantum state across the whole path, even if the original channel would have been far too lossy to carry the system itself. This is why teleportation is not just a laboratory curiosity, it is a practical solution for routing delicate quantum information around obstacles, connecting chips that would otherwise interfere, and moving the very inputs of a computation without having to move the heavy hardware that generates them. You may wonder how real this is. The milestones speak for themselves. Researchers have teleported quantum states across lab benches, through city-scale fiber networks, over mountain-to-volley free space links, and even between ground stations and orbiting satellites. In each case, the final step respects the same exact exchange rate, and the fidelity of the transferred state consistently beats the best classical limit. On chips, teleportation has become a routine tool for calibration and establishing connectivity, while in emerging network prototypes, entanglement distribution is combined with quantum memory so that the link persists long enough for microseconds or milliseconds to relay the necessary classical bits. Every breakthrough carries honest limitations, and those help refine the technique rather than undermine it. The joint measurement that triggers teleportation cannot always perfectly distinguish all possible patterns with simple linear optics, so early demonstrations accepted a lower success probability or added auxiliary resources to boost it. Memories that hold entanglement must fight decoherence, and corrections have to be applied quickly and accurately. Secure designs must also guard against side channels unwanted light or heat that could betray the hidden information. These challenges are very much like the early days of radio engineering, when engineers learned to tame interference, echo, and drift to turn a principle into a dependable technology. By confronting each obstacle head-on, we turn the fragile spark of entanglement into a robust conduit for moving information. Beyond the technical marvel, teleportation offers a quiet philosophical lesson about what it means to move information. The state you transfer is not a label glued to a particle. It is a set of relationships, a pattern of correlations that a system has with the rest of the world. By arranging a specific pattern of shared entanglement, performing a joint measurement, sending a modest classical message, and applying a corrective operation, you recreate those relationships elsewhere while the original ones dissolve. What travels is structure, not substance. The old version cannot remain unchanged, because copying the state perfectly would violate the very rules of our universe. Instead, the protocol balances the books automatically when the new state appears. The old one ceases to exist in the form that held its secrets. This is not mysticism, it is a practical tool that lets you route quantum states around noisy or lossy parts of a setup, connect chips that would otherwise interfere, shift delicate states out of a device for storage or further processing, and execute operations remotely by moving the inputs instead of the tools. Because the process is intrinsically secure, any eavesdropper who tries to intercept the shared link or the accompanying classical bits leaves unmistakable fingerprints that honest users can detect. This security, coupled with the ability to prepare high-quality entanglement in specialized hardware, sketches a clear blueprint for scaling quantum networks. The hard work of creating pure entanglement happens in dedicated stations, and the end users simply spend that resource to move states where they are needed. Picture again the two candles, one dimming as the other brightens. That image captures the essence without any equations. You prepare a shared flame in advance, perform a coordinated move that snuffs your local candle while encoding two numbers, send those numbers over an ordinary wire, and watch a distant wick ignite in the same pattern. Nothing solid crosses the gap, nothing cheats the speed limit, yet the pattern you cared about arrives exactly where you wanted it, ready to interfere, compute, or be measured as if it had always been there. That is teleportation's gentle promise to let the structure travel while the substance stays behind. Now consider another elegant twist on this theme: isopedance coding. This protocol lets you pack two classical bits of information into a single traveling qubit. but only because you have already paid the price by creating a shared entangled pair. The trick does not break any physical limits, it simply leverages a resource you prepared in advance. Imagine you and a friend each hold half of a perfectly correlated pair of coins. You never know whether both are heads or both are tails until you look, but you know they will always match. By giving your coin a tiny, precise nudge, one of 4 possible rotations, you change the relationship between the 2 coins into one of 4 distinct joint states. You then mail your coin to your friend, who now holds both halves. A single joint measurement on the pair reveals exactly which nudge you applied, allowing you to convey 2 bits of information with just that one traveling coin. In the quantum world, the coins are qubits entangled in one of the bell states, and the nudges are small rotations that shift the shared state among those 4 possibilities. Because the entanglement was seeded beforehand, a lone qubit can now carry a doubled payload. The magic of superdense coding rests on preparation, not on squeezing extra letters into a smaller envelope at the last second. If you did not have the shared entangled pair, a single qubit could convey at most 1 classical bit. The extra capacity appears only because the hidden ownership of the pair acts like a silent second wire laid in advance. The protocol's elegance hides practical conditions, however. Your partner must be able to perform a measurement that reliably distinguishes all 4 joint patterns. In some platforms, such as simple linear optic setups, only 2 of the 4 can be told apart without extra resources, turning the process into a probabilistic coin toss unless you add auxiliary photons or special interactions. In trapedian or superconducting circuit systems, fully distinguishing the 4 bell states is routine because the qubits can be made to talk strongly to each other. You also need shared timing, phase references, and a stable environment so the delicate link you created earlier survives until the message is sent. If noise blurs the link, the distinct patterns collapse toward each other, and the recoverable payload drops below 2 bits, reminding us that entanglement is not a binary possession but a resource that decays if neglected. Superdense coding does not overthrow the earlier lesson that a bare qubit line yields at most 1 classical bit per use. Instead, it belongs to the larger family of entanglement-assisted communication, where you count both the forward quantum uses and the stock of shared pairs. Spend 1 pair and 1 traveling qubit, and you can send 2 bits. Spend 2 pairs and a higher dimensional particle, and you can send even more because higher dimensional shared links support more than 4 perfectly distinct joint patterns. Conversely, if you ration your pairs, the advantage shrinks, and if you forbid entanglement entirely, you fall back to the usual ceiling. This accounting keeps engineers honest. When they compare designs, a spectacular headline rate often assumes a supply of pre-shared links whose creation and maintenance have their own costs. Those links must be refreshed through distribution, purification, and storage before the next burst of messages. In a future quantum network, superdense coding can act like header compression for controlled traffic, letting distant nodes send twice the classical instruction payload through scarce quantum connectors, while ordinary fiber or radio carries bulk bits. Inside quantum processors, it can move calibration choices or branch signals between chips without tying up 2 physical lines. In hybrid systems that combine quantum memory with classical processing, it can shuttle settings and keys across lossy segments where sending 2 separate qubits would fail, yet a single qubit backed by a stored half-pair still succeeds. Moreover, in secure setups, it offers a dial between rate and detectability. An eavesdropper who tampers with the shared pairs or the traveling qubit inevitably disturbs the joint patterns, raising a flag that honest users can detect through statistical sampling. There is a pleasing symmetry between teleportation and superdense coding that helps you keep the 2 ideas distinct while appreciating their shared spirit. Teleportation consumes a shared pair plus 2 classical bits to move a quantum state with no qubits traveling. Superdense coding consumes a shared pair plus 1 traveling qubit to move 2 classical bits. One moves a state using bits, the other moves bits using a state. Both obey the same conservative bookkeeping that forbids a free lunch while enabling clever trades when the right stockpiles are in place. In networks, both protocols appear together with quantum repeaters. Entanglement is created over short spans, swap to reach long distances, and then spent either to teleport fragile states around obstacles or to pack more classical control into the few quantum shots you can afford across a weak link. Of course, the world resists neat stories. Loss in fibers eats traveling qubits, memories leak over time, and devices drift. To keep 2-bit payloads reliable, you monitor the health of your shared pairs, distill fresh ones from many noisy candidates, and schedule your send windows tightly so the link hasn't wilted. You also choose alphabets that match your hardware. On-chip platforms might use microwave photons and tune pulses to hop among joint patterns. Free space links might pick time bin or polarization modes that survive turbulence. Ion chains might couple motion and spin to make the joint test fast and clean. Each choice changes the error model and the best coding on top, but the core remains the same. A prior link lets one traveler speak 2 clean bits. Perhaps the deepest lesson is psychological. Superdense coding asks you to stop seeing information as a property of the messenger alone and start seeing it as a property of relationships prepared in advance. The qubit you launch carries 2 bits because the world has already been arranged so that 2 hands reunited can perform a test that has 4 crisp answers. That arrangement takes effort and is fragile. When you honor it, the path widens. If you zoom out, you notice that much of modern communication already follows this choreography: cache, codes, synchronizational ways of paying up front to move more later. Quantum mechanics simply makes the choreography literal. Prepare a shared pattern, apply a tiny local stamp to choose among 4 possibilities, and send a single traveler. Now, as you listen, feel the excitement of being part of this unfolding story. The principles of teleportation and superdense coding are not reserved for a handful of laboratories. They are the building blocks of a future where information moves with elegance, security, and efficiency that once seemed impossible. The next time you face a challenging project that feels too fragile to carry forward, a collaboration that seems out of reach, or a vision that appears too complex to implement, remember the quiet promise of these quantum protocols. Prepare the shared flame in advance, coordinate your move, and let structure, not substance, do the traveling. By paying the right price up front, whether that price is time, effort, or a carefully crafted relationship, you open a path for your ideas to arrive exactly where they are needed, untouched by the noise that threatens to degrade them. Take this inspiration into your own work. When a task feels too delicate to transport directly, think about creating a short, reliable link first, then stitching those links together until you span the whole distance. When you need to convey more information than the channel seems to allow, consider whether you can invest in a pre-shared resource that will multiply your capacity later. When security is paramount, remember that any attempt to eavesdrop on a well-prepared relationship will leave detectable traces, turning potential threats into opportunities for verification. The quantum world teaches us that information is not a static object stuck to a carrier. It is a pattern of relationships that can be recreated, reshaped, and moved with the right choreography. By embracing this mindset, you can design systems, technical, organizational, or personal, that are resilient, efficient, and elegantly scalable. Let the lessons of teleportation and superdense coding guide you to prepare the groundwork today, so that tomorrow you can send your most valuable payloads, whether they are data, ideas, or aspirations, across any gap, unburdened by loss, and arriving with the full power you intended. The future is already being woven, quantum thread by quantum thread, and you have the opportunity to be one of its master weavers. Imagine you are standing at a crossroads where the invisible threads of possibility stretch out before you, waiting for you to reach out, to grasp, to shape them. In the world of quantum wonder, those threads are called entanglement, and they whisper a simple truth: the power of a connection is far greater than the sum of its parts. When 2 particles share a secret bond, they become a single story told in 2 places at once. That secret, that shared pattern, is the foundation of a dance that can move information faster, tighter, and more securely than any ordinary messenger ever could. It is as if you and a trusted friend have agreed on a special handshake long before you ever meet, and you perform it. Everyone else can instantly recognize the meaning behind it, even if they never saw the original agreement. Think of teleportation as the ultimate act of trust. You have a fragile piece of knowledge, a whispered idea that you want to send across a distance without ever letting the fragile carrier touch the wildness of the world. In the quantum realm, you accomplish this by borrowing a shared pyra, prearranged bondand, by sending two ordinary, classical bits of information. No quantum particle has to travel the entire way, yet the delicate state arrives, unharmed, on the other side. It feels like magic, but it is nothing more than a cleverly balanced ledger. One side consumes a shared pair and 2 bits. The other side receives the exact same state that you wanted to protect. The cost is real, the rules are firm, and there is no free lunch. Yet, because you prepared the groundwork, you have created a shortcut where none existed before. Now picture superdense coding as the flip side of that same coin. Here, you take that same prearranged bond, but instead of sending 2 bits to move a state, you send a single quantum traveler and, in return, extract 2 bits of classical information. The traveler is like a messenger who carries a secret stampone of 4 possible markings that you chose in advance by applying a tiny local operation. When the messenger arrives, the partner reads the joint pattern, and in that instant, 2 whole messages are revealed. You have taken one physical carrier and squeezed out twice the information. Again, the trade is precise: 1 shared pair and 1 traveling particle yield 2 bits. The symmetry of these 2 tricks is striking, and it mirrors a deeper lesson about life itself. When you invest in relationships, you can both give and receive more than you ever imagined, but only when the underlying connection has been cultivated with care. In the grand tapestry of a quantum network, these twin techniques appear side by side, woven together by quantum repeaters. Imagine a series of short bridges, each firm enough to support a delicate, entangled pair. Those bridges are built, tested, and then linked together, swapping the entanglement from one segment to the next. Once the bridges are in place, you can either teleport a fragile state across the whole span or pack more classical control into the few quantum passes you can afford. The network breathes life into distant laboratories, turning isolated islands into a collaborative continent. But the world does not always follow neat blueprints. The very fibers that carry photons are stubborn, eating away at traveling particles. Memories decay like forgotten promises, and devices drift out of alignment like guitars left untuned. To keep those 2-bit payloads reliable, you must constantly monitor the health of your shared pairs, distilling fresh, high-quality bonds from a sea of noisy candidates. You schedule your sending windows tightly, making sure the link has not wilted before you strike. You select the right alphabet for your hardware microwave photons, hopping among joint patterns on a chip, time bin or polarization patterns that brave atmospheric turbulence in free space links, or the delicate dance of motion and spin in ion chains. Each choice reshapes the error landscape, but the core principle stays the same. A prior bond lets a single traveler speak 2 clean bits. Beyond the physics, there lies a profound psychological shift. Superdense coding asks you to stop seeing information as a property of the messenger alone, and to see it instead as a property of the relationship you prepared in advance. The traveling particle carries 2 bits because the world has already been arranged so that 2 hands reunited can perform a test that yields 4 crisp answers. That arrangement takes effort, and it is fragile. Yet when you honor it, the path widens. Zoom out, and you recognize that much of modern communication is exactly this: choreographic hash, codes, synchronization, ways of paying up front to move more later. Quantum mechanics makes the choreography literal. Prepare a shared pattern, apply a tiny local stamp, send a single traveler, read the joint pattern, and collect 2 bits where your intuition swore you could only get 1. No rules are broken, no free energy conjured. Just a new way to think about bandwidth in a world where structure, once prepared and protected, lets small signals speak in larger voices. Consider the art of entanglement distillation, the process of turning a pile of weak, noisy quantum links into a smaller stash of clean, strong ones using only local operations and ordinary conversation. Picture yourself and a partner at distant labs, both receiving a steady drizzle of imperfectly entangled pairs from a fickle channel fibers that lose photons, free air that jitters, hardware that drifts. Your goal is not to admire what you have, but to purify it, to use several flawed pairs as raw material, and by coordinating simple moves and sharing outcomes over a classical line, Concentrate their togetherness into a few pairs that behave almost like the pristine resource you ordered at the start. The promise is profound: you never need to bring the qubits together physically or perform exotic global tricks. Each lab acts locally, comparing notes about what they saw, deciding which pairs to keep, which to discard, and which to mash together so that the good correlations add and the bad ones cancel. A basic round of distillation feels like a cooperative game with two gentle moves. First, you standardize your messy pairs so they all look similar from the outside, randomizing certain details to turn complicated error patterns into simple ones you can reason about. Then you perform matched operations on two pairs, at once applying the same controlled flip in both labs and measuring one pair as a check on the other. When both of you see matching parity, a sign that errors likely hit in the same way, you keep the unmeasured pair because the procedure has boosted its fidelity. When your notes disagree, you toss that attempt away. It sounds wasteful until you remember what you're buying with each successful round. The surviving pair becomes more sharply entangled. By repeating the routine across many inputs, you trade quantity for quality in a controlled, predictable way. Different recipes tune this trade-off. Recurrence protocols are the workhorses when your inputs are quite noisy, boosting fidelity step by step with two-way communication and a modest yield. Hashing-style protocols act like a larger-scale laundry, processing big batches at once and keeping a constant fraction when your inputs are already decent. For pure but partially entangled inputs, there's a sibling task called concentration, which extracts almost the maximum number of perfect pairs per batch by reorganizing the existing order rather than fighting noise. It reminds us that not all weakness is the same. Some comes from mixing with the environment, some from uneven sharing between partners. In practice, you pick the tool that matches your fuel. The reason you can ever get ahead is that useful correlations tend to line up while noise tends to scatter. Local checks expose where the alignment survived, and those are the branches you prune toward. Even better, the operations that help against one error type can be alternated to fight another. Alternating parity checks in two complementary ways gradually scrubs both common kinds of flips. If you squint, you see parallels to privacy amplification in cryptography. Many flawed bits plus public discussion can yield fewer secret bits. And in the quantum case, many flawed pairs plus public discussion can yield fewer high-quality entangled pairs. Both trades pay a price in rate to buy a guarantee in quality. Distillation sits at the heart of long-distance quantum networking, because raw entanglement is fragile over kilometers. Repeaters break a long span into short links, create entanglement on each short hop, and then do two crucial chores before moving on. They purify each hop to raise its quality, and they swap entanglement hop by hop, so the ends become linked. Without purification, swapping would spread the noise, and the connection would die as you added hops. With it, you walk a narrow ridge where each step forward is matched by a tune-up that keeps the link worth having. This is why repeater designs always include memory elements to hold intermediate pairs, while checks and phone calls finish, and why the throughput of a network depends as much on distillation yield and memory lifetimes as on the brightness of the sources. In the lab, details matter and the map is not the territory. With photons, you often start by heralding the rare moments when both sides received something. Then you twirl by shuffling polarizations or time bins, performing bilateral operations with beam splitters and detectors that act like parity meters. With ions or superconducting qubits, you can implement the same logic as deterministic gate sequences and measurements. Across platforms, drifts in phase or timing can quietly undo your gains, so experiments weave in calibration pulses and reference frames to keep the two labs aligned. Because every test risks adding noise, good protocols minimize the number of times you touch each pair before you decide its fate. Distillation is also an honesty machine. It refuses to conjure perfection from nothing, and it sets thresholds. Below a certain starting quality, the routine cannot climb uphill. Part of the engineer's job, then, is preparation. Tame the channel enough that you land above threshold, then let distillation earn its keep. Another part is accounting. Track how many raw pairs you spend per purified pair, how long memories must wait, how dark counts and leakage skew your decisions, and how often you should switch between boosting and swapping to keep the pipeline flowing. When done right, you watch a noisy curve of correlations bend upward through successive rounds until it clears the bar that your application demands, teleporting a delicate state, executing a remote gate, or generating a key whose secrecy is certified by the very inability of an eavesdropper to copy without leaving scars. Hidden in all this is a philosophical line worth tracing with your finger. Entanglement, unlike a beam of light or a file on a drive, is not a thing you store in one location. It is a relationship spread across places. Distillation is the act of curating that relationship, testing it, pruning it, and condensing it so that what remains is not just some correlation, but the kind that cannot be explained by shared history alone. When your checks pass, you have less but better togetherness, a sharper promise that operations performed here will sing in tune with outcomes there. When they fail, you learn to let go and try again, because holding on to weak links only drags the whole chain down. If you carry one actionable picture forward, let it be this: treat entanglement like a precious metal powdered into sand by a rough journey. You swirl many handfuls in a pan. Use simple moves and a steady rhythm to make the flecks settle while the silt washes away, then collect the nugget that remains. The pan is your local gates and measurements. The water is your classical conversation. The rhythm is your protocol rounds. And the nugget is a purified pair whose value you can spend on the next stage of teleporting a state, packing two bits into one traveler, or linking two distant processes as if they shared a desk. Nothing mystical, nothing free, just careful work that turns a messy resource into a dependable one and, in doing so, makes a sprawling, lossy world feel a little more connected. Finally, consider error correction, the steady choir that can sing one note perfectly even if a few voices go off-key. You never ask a single singer whether they're right. Instead, you ask the group for syndrome's little yes-no harmonies that reveal where mistakes happened without revealing the secret melody itself. The first landmark, Shor's code, spreads a delicate qubit across 9 physical ones, forming 3 voice clusters that protect against flips, then weaving those clusters so that quiet phase slips are also caught. You never measure the protected note directly, you measure cross-checks that say these two agree or this trio hums together. And from that pattern you infer which qubit likely strayed and gently nudge it back. Shor's idea proves the principle end to end. If you detect errors often enough and repair them softly, you can push the logical qubit's lifetime far beyond the natural lifetime of any part. You do it without ever cloning or peeking at the melody you're guarding. Years later, Steen's code refined the craft with 7 physical qubits instead of 9, borrowing discipline from classical communication while preserving the quantum spirit. All of this technical elegance carries a simple, human truth: preparation, collaboration, and careful refinement turn fragile possibilities into robust realities. Whether you are aligning photons across a city, polishing ion chains in a cryogenic lab, or building a choir of qubits that can weather any slip, the pattern repeats. You lay many shaky planks, you watch, you prune, you repeat, and eventually a solid bridge stands where before there was only a gap. In your own life, you can adopt that same rhythm. Start with imperfect ideas, imperfect relationships, imperfect habits. Share them, compare notes, discard what hurts, reinforce what lifts, and keep the cycle turning. Each round may feel like a loss, but each successful round refines your inner entanglement, making you more resilient, more capable of carrying larger messages with fewer steps. So the next time you face a noisy channel, whether it's a difficult conversation, a daunting project, or a personal dream that seems out of reach, remember the quantum craftspeople who quietly shape entangled pairs, who whisper to each other over classical lines, who turn many weak connections into a shining, high-fidelity link. They do not cheat the laws of physics, they honor them. They work within the constraints, they trade resources wisely, and they never stop polishing the relationship at the heart of the system. You, too, can honor the relationships in your life, invest in the shared patterns, apply small, intentional actions, and watch as a single, thoughtful step yields twice the impact. The universe teaches us that the most powerful exchanges happen not through force, but through the elegance of a well-prepared bond. Take a breath, feel the subtle rhythm of those quantum chords, and let them inspire you to prepare, to collaborate, to distill, and to correct. Let each moment of intention be a tiny local operation, each conversation a classical channel, each shared success a purified, entangled pair. In this grand symphony of possibility, you are both the conductor and the player, and the music you create can travel farther than you ever imagined. When you're standing at the edge of a noisy channel, whether it's a tough conversation that feels impossible, a big project that looms like a mountain, or a personal dream that seems just out of reach, think of the quiet artisans of the quantum world. Those artisans coax pairs of particles into a special bond called entanglement. Then they coax those bonds again and again until only the purest, most reliable connection remains. Imagine taking a handful of rough sand and, with steady, rhythmic motions, coaxing out a single gleaming nugget of gold. The pan is your local measurements and gates. The water is the ordinary, classical chatter you have with yourself and others. And the rhythm is the disciplined protocol you repeat over and over. When the process works, you end up with a distilled pair that you can spend on something extraordinary, a teleportation of a state, packing 2 bits of information into one traveler, or linking 2 distant operations as if they shared a desk. Nothing mystical, no free lunch, just careful work that transforms a messy resource into something you can truly rely on, making a sprawling, noisy world feel a little more connected. That same spirit of careful transformation is at the heart of quantum error correction. It's the art of catching tiny slips before they grow into full-blown failures, all while preserving the delicate quantum melody you're trying to protect. Picture a choir that must sing one perfect note. If a few singers drift off key, you don't ask each of them individually if they're right. Instead, you listen to the harmony of the whole group, picking up little yes-no cue syndromes that tell you where the mistake lies without ever revealing the secret tune itself. That is the genius of error correction. You measure the shadows the errors cast, not the secret itself. The first landmark on this journey was a code that took a single fragile qubit and spread its pattern across 9 physical ones. It formed 3 small clusters that protected against simple flips, then wove those clusters together so that even the more subtle phase slips toes rotations that changed the hidden arrow without flipping the measured digit could be caught. The trick is never to measure the protected note directly. Instead, you perform cross-checks that tell you if 2 pieces agree or if a trio hums together in harmony. From those patterns you infer which qubit likely strayed and gently nudge it back. This bold idea proved that if you detect errors often enough and repair them softly, a logical qubit can stay honest far longer than any single physical part ever could, all without ever having to clone or peek at the melody you're guarding. A few years later, a refined version emerged, using only 7 physical qubits instead of 9. It borrowed clever ideas from classical communication, arranging parity checks that catch typographical errors in the same way a Hamming code does, but making them quantum-friendly so that flip-type and face-type errors are handled by twin families of checks that never step on each other's toes. In practice, you prepare small helper qubits and silicon tidy patterns. Let them listen to selected subsets of your data through gentle interactions, and then read only the helpers. Their pattern of clicks becomes the syndrome, a compact map that a decoder reads to decide what to fix. Because the checks are balanced and symmetric, you can prepare those helpers cleanly, even injecting special states you'll need later for computation. That symmetry brings both clarity in analysis and cleanliness in hardware, a lesson that reverberates far beyond the lab. The workhorse of today's road maps is the surface code, whose brilliance lies not in algebraic gymnastics, but in spatial simplicity. Imagine laying your qubits out on a flat grid where each one talks only to its nearest neighbor. No tangled wiring, no long-range leaps. Tiny square plaquettes act as neighborhood referees. Some referees check that nearby qubits agree on a flip parity, others check a phase parity. Every few microseconds, the grid reports a new snapshot of which squares are upset. A single upset square tells you little, but the pattern of upset squares across space and time sketches the track of an error the way fresh snow reveals the path of a fox. A classical decoder then connects these tracks, often by pairing up upset squares into likely paths and prescribing the minimal fixes, because all checks are local and identical. The surface code tolerates a messy, scalable factory. Add more tiles, and as long as each tile is reasonably good, the protection improves, much like building a thicker wall from the same bricks. This locality is gold in the lab, where qubits prefer a limited number of neighbors and crosstalk grows with complexity. None of this works if the very act of checking makes things worse. Helper qubits must be prepared cleanly, touched to the data in a precise order that avoids spreading a single fault, and measured swiftly. Because measurements themselves can lie, you repeat rounds and look for changes over time rather than trusting a single snapshot. Because gates can fail, you design the schedule so that one slip cannot cascade into many. That constraint births the whole field of fault-tolerant design, where every move is chosen so that even the worst case remains fixable. In modern labs, real-time control loops prepare helpers, perform check circuits, record outcomes, and feed them to decoders that update their best guess of the hidden state many times a second. Corrections are applied either virtually by reinterpreting future operations or physically, by tiny nudges, depending on the platform. The cost is honest. You trade hardware for honesty, wrapping one logical qubit in dozens, even thousands of physical ones. You also pay in time, spending cycles on checks instead of pure computation. Yet that trade unlocks something radical: a regime where making the device a little better buys you exponentially more reliability as you scale the code's distance, as long as you stay above a quality line. Early demonstrations already show prolonged lifetimes of encoded information, detection of both flip and phase errors in real chips, and the first baby steps of computing inside the protected space. Different platforms lean on different strengths. Superconducting circuits push fast rounds and friendly layouts for surface codes. Trapped ions excel at clean, high-fidelity gates that favor the 7-bit style checks and flexible geometries. Neutral atoms and photonics explore modular variants whose locality maps onto their own virtues. Across all of them, you see the same choreography: prepare helpers, dance the checks, read syndromes, decode and correct, repeated like a heartbeat. What do these three codes teach you beyond their individual blueprints? First, protection is about pattern management. You never ask for the secret itself, you ask for the shadows it casts when something's wrong. Second, geometry is destiny. Abstract algebra blooms into hardware reality when your checks align with what your devices do best. Third, reliability is earned in layers. The 9-qubit version proves the concept by brute force. The 7-qubit version trims and balances it with structure, and the surface code industrializes it with local, repeatable tiles that can, in principle, blanket an entire wafer or a plane of trapped ions. If you hold one image as you leave, let it be a quilt stitched from many squares. Each square is a small agreement among neighbors, each stitch a check that keeps tears from spreading. The warmth you feel at scale doesn't come from any one patch being perfect, but from the discipline of checking, mending, and layering so that small drafts never grow into a chill. Quantum error correction is that quilt for fragile states: patient, local, relentless, turning a technology that forgets in microseconds into one that can, with enough care, remember long enough to matter. Fault tolerance, thresholds, and overheads are the next frontier. You don't truly feel the weight of a quantum computer until you try to make every step safe, even when pieces stumble. Fault tolerance promises that below a certain threshold of physical error, you can stretch reliability as far as you're willing to pay more qubits, more checks, more time. Imagine hiking a ridge in fog, planting a flag and an error check every few steps. As long as each short stride is less slippery than a known limit, you can lay flags closer together, build handrails, and make the journey arbitrarily safe. If the ground is slicker than that limit, no amount of flags will save. You'll eventually slide off. That turning point is the threshold, and staying under it is only the beginning, because then comes the budget: how much extra gear you must carry to push your risk down to the tiny level your application demands. The threshold theorem says that if each elementary operation, preparing a qubit, applying a gate, idling, measuring, fails less often than a code-specific number, then by encoding your information and correcting continually, you can make the logical error per step shrink exponentially as you increase the code size or distance. But this abstract comfort hides a maze of details. The threshold you quote depends on the noise you truly have. Is it mainly bit flips, mainly phase slips, or a biased mix? Do errors arrive independently or in bursts? Do faults in control electronics sneak in as patterns the codes expect, or as oddball failures that the codes hate? And how you extract syndromes matters, because checking itself can spread a single fault into many if scheduled carelessly. In practice, you see families of thresholds. A generous one assumes your checks are perfect. A stricter circuit level one counts every wire, and interaction hardware-specific thresholds fall once you factor in crosstalk, leakage to states outside the code space, and slow drifts that mimic correlation over time. Overhead begins with space. To protect one logical qubit, you may need dozens to thousands of physical qubits, depending on the code and the target error rate. A modest demo that only keeps time might manage with a few dozen, while a computation that runs millions of steps without a single logical slip may demand city blocks of hardware. Then comes time. Each round of checks takes a handful of gate layers and measurements, and you must repeat them over and over, feeding their outcomes into a decoder that decides what to correct. If the decoder is slow, you either buffer results costing memory and risking backlogs, or accept latency that stretches your logical clock. Modern systems use real-time controllers that update a polyframe on the fly so many corrections can be applied virtually, reinterpreting future operations rather than physically nudging qubits, saving precious nanoseconds. Still, the bookkeeping and verification consume cycles. Not all overhead looks like qubits and time. Some are factories. To run a universal algorithm, you usually need special, hard-to-make resource states, often called magic states, to implement the few gates your code won't allow you to do cleanly. Producing these states with very high fidelity requires a process called distillation, which eats area and time in bulk like an industrial plant beside the main city. Route too few resources to the plant and your program waits on ingredients. Route too many and your chip fills with warehouses instead of workshops. Balancing that area-to-mevolume triangle is a core art of architecture, and it often dominates the total cost more than the data registers themselves. All of this might sound like a technical maze, but at its heart it's a story about perseverance, about turning imperfections into strength, about building something reliable out of the fragile, and about the power of disciplined, repeated action. When you apply those lessons to your own life, you see the same patterns. You have dreams that feel like fragile qubits, prone to losing coherence amid the noise of daily obligations. You have relationships that can slip into miscommunication if you don't check in regularly. You have projects that will collapse under the weight of a single unchecked error. The quantum toolbox tells you to create helpless routines, habits, supportive people who listen to small subsets of your larger goals, report back gently, and let you correct course without losing sight of the bigger melody. Treat each check as a flag you plant on a foggy ridge. Trust the pattern of flags, not the single uncertain step. When a flag signals a misstep, adjust a little without overreacting, because overcorrection can spread the fault further. Let the rhythm of your daily protocol be steady, like the pan's swirl that separates gold from silt. Over time, you'll collect nuggets of progrestiny, purified successes that can be spent on larger achievements, a promotion, a creative breakthrough, a deeper connection with someone you love. Just as the surface code tolerates a messy environment by relying on local, repeatable tiles, you can design your life with small, local actions that reinforce each other, building a resilient structure that can expand without collapsing under its own weight. Remember that every protective layer you add, every habit you cement, every feedback loop you establish costs something: time, effort, maybe a bit of comfort as you step out of your familiar patterns. But those costs are the very investment that lets you scale your reliability exponentially. The threshold you face in life is your personal tolerance for error. If you can keep your daily missteps below that limit through mindfulness, rest, and a supportive network, you can grow your capacity for success almost without bound. Cross that threshold and sudden slips become far more likely, just as a quantum device would tumble into chaos if its error rate climbs too high. So as you move forward, picture the quilt of checks, the pan of purification, the choir of harmony, and the grid of local referees. Feel the steady rhythm of your own protocol, the gentle hum of helpers listening and reporting, the quiet confidence that comes from knowing you can catch a mistake before it snowballs. Let each small correction fuel a larger sense of purpose, turning the fragile into the steadfast, the noisy into the connected. In the quantum world, as in your own, the journey from a single trembling qubit to a robust logical state is a testament to patience, pattern, and relentless care. Embrace that journey and watch how a world that once seemed too noisy, too fragile, too uncertain becomes a canvas where each deliberate, rhythmic motion paints a brighter, more reliable future. Imagine you are walking along a misty ridge, each step taken with care, each pause a moment to plant a flag that tells you where you stand. The fog is thick, but you have a rhythm. You test the ground, you adjust your footing, you keep moving forward. As long as every short stride is safer than a known limit, you can place those flags closer together, build gentle handrails, and make the path feel almost certain. Yet if the rocks become slicker than that limit, no amount of flags can stop you from slipping. That moment when the ground gives way is the threshold, the point at which the balance tips. Staying below that line is only the first act. Once you are there, the next question emerges: how much extra gear must you carry to push the risk down to the whisper-quiet level your journey demands? This is the heartbeat of fault tolerance, a principle that silently guides every bold venture, whether you are building a skyscraper, training for a marathon, or, in our case, shaping the future of computation. The threshold theorem tells us something both profound and practical. If each tiny operation, preparing a quantum bit, applying a gate, waiting idly, or making a measurement, fails less often than a code-specific number, then by weaving those bits together into a protective encoding and constantly correcting errors, the chance of a logical mistake shrinks exponentially as you increase the size of that encoding. In other words, a small improvement at the lowest level cascades into a massive gain at the higher level, just like a single confident step can set the tone for an entire climb. But the comfort of that theorem hides a winding maze of details that you, as the explorer, must navigate. The threshold you quote isn't a single static number. It bends and shifts with the character of the noise that surrounds you. Is the disturbance mainly a sudden flip of a bit, a subtle drift of phase, or a biased mix of both? Do errors arrive one by one, independently, or do they burst together in clusters? Are the tiniest faults in your control electronics appearing as predictable patterns that your codes can anticipate, or as oddball glitches that stubbornly resist correction? Even the act of checking can, if arranged carelessly, spread a single fault into many, turning a gentle breeze into a gale. In practice, engineers talk about families of thresholds: a generous one that assumes your checks are perfect, a stricter circuit-level version that counts every wire and interaction, and hardware-specific limits that fold in crosstalk, leakage into unwanted states, and slow drifts that masquerade as correlated noise over time. When you begin to map out the overhead required to stay safely under the threshold, you quickly discover that it starts with space. To protect a single logical quantum bit, you may need dozens, even thousands, of physical bits, depending on the code you choose and the error rate you aim for. A modest demonstration that merely keeps time might get away with a few dozen, but a computation that runs millions of steps without a single logical slip could demand an expanse of hardware that feels like city blocks. Then time enters the picture. Each round of checks consumes a handful of gate layers and measurements, and you must repeat those rounds, feeding the outcomes into a decoder that decides what to correct. If the decoder lags, you either buffer results costing memory and risking backlogs, or you accept latency that stretches your logical clock. Modern systems tackle this by using real-time controllers that update a polyframe on the fly, allowing many corrections to be applied virtually by reinterpreting future operations rather than physically nudging the bits. This clever bookkeeping saves precious nanoseconds, but the verification still consumes cycles. Overhead isn't just about extra bits and extra time. Sometimes it looks like factories. To run a universal algorithm, you usually need special resource states, often called magic statisto implement. The few gates that your code won't allow you to perform cleanly. Producing these states with very high fidelity requires distillation, a process that eats area and time in bulk, much like an industrial plant sitting beside the main city. Route too few resources to the plant, and your program waits for ingredients. Route too many, and your chip fills with warehouses instead of workshops. Balancing that triad of area, time, and volume becomes an art of architecture, and it often dominates the total cost more than the data registers themselves. Geometry shapes overhead just as much as algebra, codes that live on a two-dimensional grid, with only nearest neighbor interactions like the surface code offer comfortable thresholds around the percent level for common noise models and scale cleanly by adding tiles. Yet they pay with large footprints for certain gates. Alternatives such as color codes promise lighter circuits for some operations, but tolerate lower noise or demand more complex layouts. Concatenated codes stack layers of small codes inside each other, giving clean mathematics and flexible gates at the price of wiring and control complexity. Bosonic codes place more of the burden inside a single physical mode. CAT codes, GKP codes, and other continuous variable approaches can dramatically cut the raw count of physical bits if you can stabilize exotic states, but they shift overhead into precision control and continuous calibration. There is no free lunch, only menus with different prices, and the choice of menu defines the journey. The rules of fault tolerance also constrain how you compute. You favor gates that don't let a single fault blossom into a multi-bit disaster. You stage measurements so that any lone bad outcome can be recognized and contained, and you accept that some elegant gates are banned outright by deep theorems. No code lets you perform every logical gate transversely on the same encoding. Workarounds like lattice surgery, code switching, and teleporting gates from factories become the civil engineering of this field, rerouting traffic to keep accidents small. When your hardware exhibits a bias, say, phase slips 10 times more likely than bit flips, you can lean into that asymmetry and design checks that buy better thresholds for the same parts. If leakage into unwanted levels creeps in, you add leakage error removal cycles that pump the strays back down before they unspool damage. If noise clusters in time or space, you upgrade decoders from simple matching to algorithms that read tracks across several rounds, using temporal patterns to separate crackle from melody. Decoding itself is a hidden mountain in the overhead landscape, the algorithm that converts a flutter of measurement outcomes into a Beskus repair must be fast, accurate, and kind to your processor. Matching two defect points gives you a short error path. Matching thousands over many rounds demands smarter heuristics, hardware accelerators, or even neural aids. A decoder that lags by milliseconds on a system that ticks in microseconds forces you to store corrections or accept stale decisions, both costly in their own right. This is why research teams prototype decoders on FPGAs, ACs, and even embedded GPUs, and why the boundary between quantum and classical hardware is itself an optimization problem. Move too much work off-chip and cables, heat loads, and latency become your enemy. Move too much on-chip, and you choke precious cryogenic budgets. Threshold is not only a number, it is a discipline. You characterize your devices honestly, including rare events. You tune schedules that keep fragile checks from colliding. You budget for calibration overhead that holds parameters inside safe lanes. And you monitor for drift so the real system never wanders above the line. Factories are scheduled like airlines, with buffers and reroutes for bad weather. Memories are sized to survive the longest expected delays. The whole machine is designed around the reality that failure probabilities multiply with depth, so you push error-prone steps earlier, convert physical corrections into virtual ones, and restructure algorithms to minimize the types of gates your code finds awkward. The rewards for doing all this are not theoretical fantasies. Encoded quantum bits now outlive their unencoded counterparts by clear margins. Round-by-round detection of both main error types runs reliably on chips and in ion chains. The first fault-tolerant logical gates have been demonstrated with checks guarding every step, and small patches of surface code have been stitched together like quilts, with decoders steering them safely. Each incremental step builds a regime where making components a little better buys you exponential improvements at the logical level, a compounding effect that turns today's fragile prototypes into tomorrow's dependable engines. Honesty, however, keeps ambition grounded. Even with friendly thresholds, overheads for truly large jobs remain heavy, often demanding millions of physical bits, plus robust factories and fast decoders. That cost pushes innovation in every direction: hardware that natively suppresses the most common errors, codes that exploit bias to cut bit counts, bosonic encodings that pack more protection into fewer elements, and algorithms that reduce the number of costly gates you need. The destination is not a single magic number, but an ecosystem where thresholds are respected, overheads are engineered, and performance goals are met by matching the right code, the right architecture, and the right workload. If you picture a single image to hold onto, imagine a suspension bridge spanning a windy channel. The threshold is the maximum gust the cables and towers can handle safely. The overhead is the extra steel, the redundant strands, the dampers, the frequent inspections, and the traffic rules. Build below the gust limit and add enough structure, and the bridge stands for decades. Ignore the limit or skimp on redundancy, and the first storm will tell you its story. Quantum fault tolerance is that same bargain in a different medium. Respect the line, pay the overhead, and you can carry delicate computation across a noisy world as far as you dare. Now, let's shift the view to the stabilizer formalism, a way of thinking that turns the abstract into the intuitive. You stop describing a quantum state by what it is and start describing it by what it obeys. Not by a long list of coordinates, but by a short set of calm rules that the state leaves unchanged, like a melody defined by the harmonies that never budge no matter how often you play them. In practice, those rules are simple commuting checks built from the basic flips and phase flips we use to poke quantum bits. A stabilizer state is any state that answers unchanged to each check on the list. Anything that answers flipped is flagged as out of tune. Suddenly, a sprawling cloud of amplitudes collapses into a tidy notebook. Write down a handful of independent generators rules that don't argue with each other, and you have specified an entire subspace of allowed states. Because any other rule you care about follows from combinations of the ones you listed. The number of independent rules tells you how tightly you have fenced things in. More rules shrink the space of possibilities, fewer rules leave more freedom. A code space becomes the set of states that keep these particular harmonies intact, and a single well-defined state appears when your rules are numerous enough to pin everything down. This viewpoint instantly explains why parity checks in quantum error correction don't reveal the secret melody. When you measure a stabilizer, you ask whether the current state still obeys a chosen rule. A healthy system says yes and remains unchanged, while a nudge from noise might flip the answer to no, telling you a fault passed by without forcing you to crack open the hidden pattern. Different error types leave different fingerprints relative to the rules. Some faults commute with a check and pass silently, others anti-commute and flip the sign. A brief pattern of yes and no across many checks becomes a syndrome that points to likely culprits. That is why the formalism feels so natural for codes. Instead of tracking every amplitude, you track which rules still hold, and the rest of the recovery problem becomes a tidy puzzle of reconciling the broken ones with the smallest fixes. The stabilizer lens also reveals an unexpected simplicity in certain quantum circuits. There is a family of operations, the Clifford family, that takes basic flips and phase flips to new combinations of the same, like shuffling chords in music, without ever leaving the key. Because these operations never turn a simple check into something exotic, stabilizer states pushed through these circuits remain stabilizer states, and you can update the rule book directly without touching amplitudes at all. This is the core of the famous simulation shortcut. If your computation begins in a stabilizer state, uses only Clifford gates, and measures in compatible ways, then a classical computer can track the evolving rules efficiently using a compact tableau. No heavy wave function math is needed, because you only ever record which checks become which. That limitation does not make the quantum device useless, it makes the structure crystal clear. We can separate what brings genuine quantum hardness, those rare non-Clifford gates that leave the stabilizer world, and what merely rearranges rules in a space we understand perfectly. All of this is more than a technical story, it is a narrative about perseverance, about building bridges over uncertainty, about planting flags in the fog, and learning to read the subtle signs that tell us we are still on the right path. It reminds you that every small improvement, every careful measurement, every thoughtful layout is a step toward a future where the delicate dance of quantum bits can be choreographed reliably, where the whisper of an error is caught before it becomes a roar, and where the dream of fault-tolerant computation moves from abstract theorem to lived reality. So, as you move forward, keep the ridge in mind. Test the ground with each stride, plant your flags, and listen to the echoes of your checks. Respect the threshold as the line that guards you from the abyss, and accept the overhead as the sturdy scaffolding that lets you climb higher. Embrace the elegance of stabilizers, the power of clever codes, and the relentless drive to turn noise into a manageable companion, rather than a foe. The path may be steep, the mist may thicken, but with each deliberate step you bring the horizon closer, and you become the architect of a bridge that will carry not just computations, but the very promise of a new era, across the windy channels of uncertainty, into the light of achievement. Imagine stepping into a grand concert hall where the music never falters, where every note is guided by a handful of timeless chords that remain unchanged no matter how many times you hear them. In the world of quantum information, those enduring chords are the stabilizer ruler simple, calm guidelines that the quantum state respects without ever drifting. Think of them as the melody that defines a piece, not by listing every single vibration, but by holding steady the harmonies that give it shape. When we translate this idea into practice, we find ourselves building checks from the most basic flips and phase flips, the tiny nudges we use to probe qubits. A stabilizer state is simply a state that answers yes to every one of these checks, while any no signals that something has gone out of tune. Suddenly, a sprawling cloud of possibilities collapses into a tidy notebook, where a few independent rules capture an entire subspace of allowed states. The more rules you write, the tighter you fence the space, the fewer you have, the more freedom you leave. In this way, a code space becomes the collection of states that keep those particular harmonies intact. And when you have enough rules to pin every nuance down, a single, well-defined state emerges. Now, picture yourself as a conductor who wants to know whether the orchestra is still playing in harmony without having to listen to every instrument individually. Measuring a stabilizer is exactly that. We ask whether the current quantum state still obeys a chosen rule. If everything is healthy, the answer is yes, and the state stays exactly as it was. If a stray whisper of noise has slipped in, the answer flips to no, alerting us that a fault has passed by, but without exposing the hidden melody beneath. Different kinds of errors leave distinct fingerprints on these checks. Some glide past silently because they commute with the rule, while others scream no by anti-commuting and flipping the sign. A pattern of yeses and nos across many checks becomes a syndrome, a concise story that points toward the most likely culprits. This is why the stabilizer formalism feels so natural. It replaces the chaos of tracking every amplitude with the clarity of watching which rules still hold, turning the recovery problem into a tidy puzzle of repairing the broken pieces with the smallest possible fixes. There's another elegant surprise hidden in this perspective. Certain quantum circuits, the Clifford family, act like masterful arrangers who reshuffle chords without ever leaving the key. These operations take basic flips and phase flips and combine them into new, but still familiar variations, because they never transform a simple check into something exotic. A stabilizer state that travels through a Clifford circuit remains a stabilizer state. The rule book can be updated directly, without ever touching the underlying amplitudes. This is the heart of a powerful simulation shortcut. If your computation starts in a stabilizer state, uses only Clifford gates, and measures in compatible ways, a classical computer can keep track of the evolving rules efficiently by recording which checks become which. No heavyweight wave function math is needed, only a compact tableau of rule transformations. That limitation does not make the quantum device useless, it actually makes the structure crystal clear. It separates the genuine quantum hardness, those rare gates that step outside the stabilizer world, from the vast landscape of operations that merely rearrange rules within a space we understand perfectly. When you look at more exotic constructions, like measurement-based computing, the stabilizer lens shines even brighter. A cluster state is simply a graph whose edges encode pairwise rules. Multiplying two neighboring rules creates a new one that links a wider patch, and long strings of adaptive measurements become a controlled way of rewriting the rule book, until the remaining qubits hold the answer you need. Graph states used in quantum networks share the same character-local tests on small neighborhoods can certify the health of a large distributed resource without ever needing a global peak. Even entanglement, that famously elusive phenomenon, becomes a matter of bookkeeping. If the rule book for the whole cannot be expressed as a union of separate rule books for the parts, you know the togetherness cannot be explained by any shared history alone. Because the rules are built from the same elementary pokes that noise uses, you can watch faults propagate through a circuit simply by updating which checks they flip. No mystery, just arrows on a diagram that a decoder later stitches into likely paths. Earlier, we explored specific codes. Now, with the stabilizer formalism, you hold the drafting tools yourself. You can choose generators that match your hardware's strengths, local ones for grid layouts, balanced ones for symmetric designs, biased ones if your device trips more often in one direction than another, and ensure they all commute, so that measuring them in any order never creates fresh trouble. You design helper routines that couple ancilla qubits to the data in patterns that read the rules, while avoiding the spread of a single bad ancilla into many broken checks. By keeping a frame of pending sign flips and never rushing to physically fix everything, you update the rule book and let future gates absorb the changes, saving time and reducing risk. And when you must step beyond the safe family of ruler-preserving gates to achieve universality, you do it knowingly. You inject a specially prepared non-stabilizer resource, and then teleport its influence into the encoded space using only ruler-respecting moves, so the dangerous part never touches the data directly. In this picture, the stabilizer world becomes a well-paved highway, and the scarce non-stabilizer resources become toll passes you insert only at design junctions. The beauty of living by rules rather than by raw coordinates is scalability. Add more qubits and a naive description explodes, but the rulebook grows only linearly with the number of generators. Large quantum states therefore remain graspable. Commissioning a new device becomes an exercise in learning which checks you can measure reliably and how quickly you can cycle them. Troubleshooting turns into a matter of comparing observed yes-no patterns to the tidy expectations of the rule book. Optimization becomes a game of choosing generators whose graph minimizes crosstalk and maximizes tolerance to the specific noise your lab fights most. Even the philosophy feels refreshing. In classical life, we describe objects by the attributes they possess. The stabilizer view asks you to define quantum states by the symmetries they preserve. Certainty is no longer an inner label, but a portfolio of invariances. You can test locally without destroying the whole. Errors become mismatches with those invariances, and correction becomes the gentle reassertion of rules that were always meant to hold. Hold on to this memory as you move forward. The stabilizer formalism is the quiet librarian of quantum information, filing vast stories under a small set of headings and letting you find what you need without opening every page. It turns syndrome extraction into non-invasive queries, turns certain gates into line edits on the rule book, and transforms the sprawling geometry of many-bit space into a clean map of neighborhoods and streets. When you eventually step outside the library to run a gate that the rules cannot absorb, you know exactly what you are spending and why, which is the essence of control. Fewer surprises, more design, and a clearer path from fragile physics to reliable computation. Now, let's turn our attention to CSS codes and the promise of topological protection. The secret of CSS codes reveals itself the moment you realize you can split the job of safeguarding information into two clean chores. One watches for flips of the digit, and the other watches for slips of the phase. Each chore can be managed by its own familiar classical code. Calder-Bank-Shor-Steen codes are built exactly this way. You start with two ordinary error-correcting codes that catch different kinds of typos. Weave them together so their parity checks never step on each other, and you get a quantum code whose tests naturally fall into two families. One family is sensitive to things that change the visible value, the other to things that twist the hidden alignment. The beauty is that you can design each family with all the intuition you already have from classical coding. Low-weight checks so measurements stay gentle, sparse graphs to localize faults, large distances to push rare failures far away and then overlay them with a single consistency rule to keep every test in one family blind to the corrections being staged by the other. In practice, a CSS code is a tidy rulebook with 2 columns of checks. Extracting a syndrome means preparing small helper qubits to listen to a handful of data qubits for 1 column at a time, recording yes-no answers that never reveal the protected information itself. When you look at the celebrated 7-qubit code through this lens, you see its classical spine 1 set of checks comes straight from a Hamming code's parity. The twin set is its mirror, and together they catch both types of quantum slips with a minimal footprint. This proof shows that quantum structure does not have to feel alien if you start from patterns you already trust. The magic becomes physical when you lay a CSS code out on a lattice and realize that the 2 columns of checks can be made local. Each test touches only nearby neighbors, so faults don't spread far, and then something deeper appears. The code's protected information stops feeling like a number stored at one spot and starts feeling like a global feature of the whole fabric. This is the doorway to topological protection, where the logical degrees of freedom are not tiny labels inside a device, but larger-scale patterns that cannot be changed by any short, clumsy nudge. Picture a quilt that wraps around into a loop so it has no edge. Imagine 2 kinds of stitches you can check on each square. One ensures that the values around a vertex agree in a certain way, the other that the values around a face agree in another way. If a local error pops a stitch here or there, your checks flag a pair of small defects you can trace and repair. To actually flip the encoded information, however, you would have to drag a thread all the way across the quilt and join it back to itself. An operation so long and unlikely under local noise that its risk falls rapidly as you make the quilt larger. In geometric language, your logical operations are extended paths that wind around holes, and 2 paths are considered the same if one can be deformed into the other without crossing a stitch. So what you're storing is not a bit in a box, but a class of shapes on a surface of memory that lives in how it wraps, not where it sits. This topological viewpoint does more than sound poetic, it reshapes engineering choices. When your checks are local and uniform, you can tile them across a chip or an array of trapped atoms without tangled wiring. When your logical operators are long paths, you can visualize distance as the minimum length of a damaging path, and you can tune that distance by changing the layout, adding boundaries, or carving holes that act like vaults to park extra logical qubits. When an error creates 2 neighboring defects, you can treat decoding like solving a maze pair-up defects by plausible short rotes and cancel them with minimal surgery, while long conspiracies that could change the code's meaning become exponentially rare at modest physical error rates. If your device has a strong bias, phase errors are far more frequent than flip error issue can tilt the CSS construction itself, giving 1 column of checks heavier armor than the other. In doing so, you buy more protection where reality actually hurts, cutting overhead without demanding cleaner parts. The CSS recipe scales beyond square quilts, extending to more intricate surfaces, higher dimensions, and richer patterns of protection. By harnessing both the rule-based clarity of stabilizers and the geometric elegance of topological codes, you weave a fabric of quantum memory that is simultaneously robust, scalable, and deeply understandable. Take this vision with you as you continue your journey. The stabilizer formalism gives you a compact, rule-driven language to describe, diagnose, and steer quantum systems. CSS codes show you how to split protection into familiar classical tasks, while topological designs lift that protection into a global, geometry-based shield. Together, they empower you to transform the fragile whispers of quantum particles into reliable, controllable computation. You stand at the intersection of physics and engineering, holding a toolbox that turns chaos into harmony, uncertainty into symmetry, and raw potential into purposeful design. Let that confidence guide each experiment, each circuit, each line of code you write. The path ahead may be complex, but with these guiding principles you have the map, the compass, and the melody that will keep you moving forward, turning every challenge into an opportunity to build a more resilient quantum future. Imagine a fabric woven from 2 kinds of stitches, each one watching over a different whisper of error, and picture that fabric as your quantum computer's protective skin. When you lay the code's blueprint on a grid, the magic begins to feel tangible. The two families of checks become local guardians. Each test reaches only to its nearest neighbors, so a fault in one spot can't instantly ripple across the whole sheet. That locality is the first promise of topological protection. It tells us that the information we store is not a fragile number tucked into a single corner, but a global pattern etched into the very shape of the cloth. Think of a quilt that wraps itself into a seamless loop, without any edge to betray it. On every square of that quilt, you can perform two simple examinations. One ensures that the values surrounding a vertex line up in a prescribed way. The other guarantees that the values looping around a face respect a complementary rule. If a tiny error slips in, it shows up as a pair of tiny defectstony tears in the fabric that you can see and mend. To truly erase the logical information you've encoded, you would have to pull a thread all the way around the quilt, weaving it back onto itself. That operation is so long and so unlikely under ordinary local noise that the chance of it happening drops dramatically as you make the quilt larger. In geometric language, the logical operations become extended paths that wind around holes, and two paths are considered the same if one can be smoothly deformed into the other without cutting through a stitch. What you are storing, then, isn't a bit in a box, but a whole class of shapes on a surface of memory that lives in how it wraps, not in where it sits. That topological viewpoint isn't just poetic, it reshapes the engineering landscape. When your checks are local and uniform, you can tile them across a chip, across an array of trapped atoms, without a tangle of spaghetti wiring. When your logical operators are long-winding paths, you can picture distance as a straight line in ordinary geometry and tune it simply by adjusting the layout by adding boundaries, carving holes, or creating vault-like pockets for extra logical qubits. If an error creates two neighboring defects, decoding becomes a maze-solving exercise. You pair up defects along plausible short routes and cancel them with the smallest possible surgery. Meanwhile, the conspiratorial long paths that could flip the logical value become exponentially rare at modest physical error rates. When the physical device shows a strong bias, phase errors happen far more often than bitflip errors. You can tilt the construction itself, giving one column of checks heavier armor than the other. In doing so, you buy more protection where reality actually hurts, cutting overhead without demanding ever cleaner components. The same CSS Calderbank-Shorstein recipe stretches beyond the simple square quilt. Modern quantum low-density parity check designs keep checks sparse and weights low, while allowing the number of qubits to grow, borrowing blueprints from expander graphs and product constructions. Those designs let you keep both families of checks thin yet drive distances sky-high. One family watches one error type, the other watches the complementary type. But now the incidence pattern is chosen for strong expansion, meaning that local noise has a hard time hiding in unlucky clusters. The result is a code with constant rate checks, constant rate so you don't drown in overhead as you scale in distances that grow with system size, an appealing trio for machines that must juggle millions of elements. Because the checks remain CSS style, syndrome extraction stays modular. You can embed helper qubits in neat, repeated patterns, schedule the two families in interleaved rounds, and feed the results to decoders that exploit the underlying graph structure, from belief propagation algorithms to newer combinatorial methods that read error footprints across time. Topology also hands you control knobs that feel architectural rather than abstract. By introducing two types of boundaries, you can create and annihilate defects in controlled ways, performing logical operations by moving and merging regions of the code's fabric, a process sometimes called surgery rather than applying delicate global gates. Adding a hole creates a fresh place to store information. Sliding a hole around another enacts a non-trivial transformation on the logical state without ever touching it directly. In more exotic settings, braiding long-lived quasiparticles in materials with a natural energy gap accomplishes the same logic directly in hardware, making the computation live in paths rather than pulses. Though that rote leans on condensed matter feats still under active development, the shared message remains: clear shape is protection. When your data is the shape, local errors can't quietly rewrite it. They can only tug at the fabric, leaving tracks your checks can see and your decoder can mend. Nothing comes for free. And the trade-offs are honest. Local CSS codes often require many physical qubits per logical one to reach the ultra-low error rates we crave. The price of long distance is a wide footprint and frequent measurements. Matching decoders must keep up in real time so that small clouds of defects don't harden into long paths while you're thinking. Fabrication must deliver uniform couplings, lest the neat geometry be undercut by hot spots of failure. Code design must balance check weight, too heavy spreads faults, too light leaves blind spots. Yet the payoff is structural. You gain protection that improves predictably as you scale, modular tiles that manufacturing can copy-paste, and a visual, testable story for why the memory holds in that survives heat leaks, drift, and crowded chips. Perhaps the most helpful intuition to carry forward is that CSS codes embody a division of labor turned into geometry. Instead of demanding one complicated test to do everything, you ask two simple, compatible families of tests to handle their halves. And then you lay them out so the thing you care about becomes a global property of the layout itself. In that world, reliability is not a promise whispered into a single fragile element, but a pattern that must be altered across the whole by a coordinated push, something nature's random jostling is very bad at. So when you hear CSS codes and topological protection, picture a fabric with two kinds of stitches, local hands checking each square, and messages stored not in ink, but in the way the threads wind around empty space. Make the fabric bigger and the message hardens, measure steadily, and small snags vanish before they spread. When you finally need to compute, you don't pry open the memory. You reshape the fabric in ways your rules allow, letting geometry, not guesswork, carry you from fragile parts to dependable outcomes. Now let's turn to the spark that lights the universal engine of a quantum computer, magic states. You realize a quantum device is missing that essential ember the moment you learn that a large class of its moves precise, orderly, wonderfully simulable can be tracked by a classical computer if that's all they ever do. The missing spark, the element that makes the machine truly open-ended, comes from special states prepared on the side and fed in like fuel. Those are magic states, and their job is simple to state and hard to supply. They let you perform at least one operation that sits outside the easy, neatly structured family of gates. So your computation is no longer confined to motions a laptop can mimic efficiently. Picture a workshop where every tool but one is safe and predictable, perfect for shaping ordinary pieces but never for creating truly new forms. Magic states are the raw material you bring in that, when pressed through a standard jig, allow that one risky transformative cut you couldn't otherwise make. In practice, you factory prepare identical copies of a certain single qubit, a small multi-bit state, with an extra twist in its geometry. Then you couple one of those copies to your encoded data through a short, well-behaved circuit. Measure a helper, and depending on a 2-bit outcome, either receive the desired exotic gate for free or apply a tiny correction to finish the job. The delicate part is that those helper states must be pristine, because any noise that sneaks in when you feed them to your data does not just blur the computation, it can become the dominant source of errors in the entire algorithm. As a result, most blueprints devote real estate and time to distillation, a staged purification process that starts with many rough magic states and winnows them down to fewer, sharper ones by running small fault-tolerant subroutines and checking parities that catch imperfections. Each round consumes a batch, tosses the ones that fail consistency tests, and outputs a smaller set with higher fidelity. By stacking rounds like a cascade, you can reach the quality your application demands at the price of space and patience. Why do these states deserve the name magic? Because they carry a kind of non-classical resource that your tidy gates cannot create on their own. If you picture quantum states with quasi-probability charts, the friendly, easily simulated world corresponds to charts with all non-negative entries. Magic states exhibit negativity signature that no ordinary random process can imitate under operations that keep you inside the easy family. This negativity cannot increase, so you cannot conjure magic from thin air with safe moves alone. In that sense, magic behaves like energy for a forbidden engine. You can move it around, concentrate it, burn it, but to get more you must pay with raw ingredients. Researchers quantify this with magic monotones, numbers that rise or fall predictably as you process states, giving you accounting rules that help design protocols and lower bounds that no wishful thinking can beat. This resource view isn't philosophy. For its own sake, it tells you why certain subroutines are necessary, how many raw copies you must budget for a given error target, and which factory designs give the best fidelity per input. The most famous species of magic state aligns with a so-called type operation, a gentle twist that, when added to your safe toolkit, completes the set you need for universal algorithms, yet the ecosystem is larger. Different hardware favors different resource states, and some platforms target operations, akin to controlled flips or small rotations around odd axes, each with its own family of distillation routines. When the noise has a bias, phase mistakes are common while bit flips are rare. You can exploit that bias by choosing magic states and distillation circuits tuned to the real error landscape, cutting overhead without demanding the impossible from your qubits. When connectivity is limited, you pick factory layouts that keep interactions local, moving distilled states toward the data region by short, repeatable hops rather than global shuffles. When measurement is fast but gates are slower, you lean into injection methods that trade extra readouts for fewer risky pulses. And when your cryogenic controllers are bandwidth limited, you schedule factories like airlines, staggering departures so fresh fuel arrives just in time for the hungry parts of the algorithm. There are deeper tricks that stretch the budget even further. Catalysis, where a high-quality magic state helps transform several rough inputs into better outputs while returning to its original form, acts like a reusable mold that doesn't wear out quickly. Compression, where you pack the needed magic for a batch of gates into fewer carriers by choreographing how you inject and correct, reduces the number of times you touch the data. Both techniques let you squeeze more power out of the same amount of raw material. All of this paints a picture of a quantum computer that is both a delicate tapestry and a well-engineered factory. The tapestry's threads, its CSS checks, its topological layout, its holes and boundaries provide a robust stage where local disturbances are merely fleeting scratches, quickly noticed and healed. The factory, fed by distilled magic states, supplies the one non-Clifford spark that lifts the whole system to universal computation. Together they form a harmony, a structure where geometry protects information, and a resource that injects the necessary non-classical edge. When you step back and listen to this story, let it inspire you to see beyond the abstract symbols. Visualize the quilt that grows larger and stronger with each added stitch. Feel the reassurance that a local error cannot unravel the whole. Imagine the gentle hum of a distillation line turning noisy beginnings into pure magic, and know that each successful step brings you closer to a machine that can solve problems no classical computer could ever hope to touch. Take this vision into your own work. When you design a protocol, ask yourself how you can embed its logic into a shape that resists the inevitable noise. When you confront the need for a non-Clifford gate, think of how you can supply that gate with a clean magic state and how you might streamline its production so it never becomes the bottleneck. Remember that every improvement, whether it's a sparser check, a smarter decoder, a more efficient distillation circuit, adds a new thread to the fabric, tightening the whole thing and making the eventual breakthrough a little nearer. In the end, the promise of quantum computing rests not on any single miracle, but on a symphony of ideas that reinforce each other. Topology gives you a sturdy canvas, CSS codes give you a simple, local language to speak on that canvas, magic states give you the one bold brush stroke that completes the masterpiece. By keeping the narrative alive, by visualizing the fabric and the furnace together, you empower yourself to push forward with confidence. The path may be long, the hurdles many, but each stitch you place, each purified state you craft, each defect you correct, brings the tapestry of reliable quantum technology into clearer focus. Keep weaving, keep refining, and let the shape of your work become the shield that carries you toward the quantum future you envision. Imagine you're standing before a vast orchestra, each instrument perfectly tuned, each player ready to follow the score. Yet, within that masterpiece, there are passages that cannot be expressed by the notes you already have. Those moments demand a special kind of ticket, a magic state that grants you the power to play the impossible. In the world of quantum computing, those tickets are not a fanciful metaphor, they are the very resource that lets us step beyond the realm of the easily simulated and into the territory of true universality. Each time you run a distillation round, you take a batch of noisy ingredients, subject them to strict consistency checks, and discard the ones that fall short. The survivors emerge more refined, their fidelity higher, and when you stack those rounds layer upon layer, you sculpt a stream of states that meet the exacting standards your algorithm requires. This process costs space and patience, but the reward is a supply of pristine magic that fuels the most demanding quantum operations. Why do we call them magic? Because they carry a kind of non-classical resource that your ordinary, tidy gates simply cannot create on their own. Picture quantum states as charts of probabilities. In the friendly, classically simulable world, every entry is non-negative, like a calm landscape of hills and valleys. Magic states, by contrast, bear negative values, not a moral judgment, but a signature that no ordinary random process can reproduce when you are confined to the easy family of operations. That negativity is a conserved quantity, it never grows on its own. You cannot conjure magic from thin air using only safe moves. In that sense, magic behaves like energy for a forbidden engine. You may move it around, concentrate it and burn it, but to generate more you must pay with raw, noisy ingredients. Researchers have turned this intuition into a precise accounting system. They define magic monotonous numbers that rise or fall predictably as you process states, providing a ledger that tells you how much magic you have, how much you spend, and what the fundamental limits are. This isn't abstract philosophy, it gives you concrete guidance. It tells you how many raw copies you must budget to achieve a given error target, and which factory designs will deliver the best fidelity per input. The most celebrated species of magic aligns with what we call a type operation, a gentle twist that, when added to your safe toolkit, completes the set needed for universal algorithms. But the ecosystem is richer than that. Different hardware platforms favor different resource states, and some target operations akin to controlled flips or minute rotations around unconventional axes, each accompanied by its own family of distillation routines. When the noise in your system has a bias, phase errors dominate, while bit flips are rarer. You can exploit that asymmetry by choosing magic states and distillation protocols tuned to the real error landscape. You cut overhead without demanding the impossible from your qubits. If your device has limited connectivity, you design factory layouts that keep interactions local, moving distilled states toward the data region via short, repeatable hops rather than sweeping global shuffles. When measurements are fast but gates lag, you lean into injection methods that trade extra readouts for fewer risky pulses. And if your cryogenic controllers are bandwidth constrained, you schedule factories like careful airline departures, staggering arrivals so fresh fuel reaches the hungry parts of the algorithm just in time. Deeper tricks stretch the budget even further. Catalysis lets a high-quality magic state act as a reusable mold, helping turn several rough inputs into better outputs while returning to its original form. Compression packs the magic needed for a batch of gates into fewer carriers by choreographing injection and correction, reducing the number of times you touch the data. Routing via code, switching temporarily parks logical qubits in an encoding where a particular exotic gate becomes cheap, then switches back, moving cost from rare heavy lifts into more frequent light motions. All these strategies are honest trades. No protocol creates magic for free, but they demonstrate how architectural choices can reshape a daunting headline cost into a workable pipeline. From the perspective of security and verification, magic states sharpen your focus. Because they sit outside the easy family, they become tempting attack points and are fragile to calibration drift. Practical systems, therefore, include witness tests that sample a fraction of produced states, checking simple inequalities that imposters cannot pass. Interleaved benchmarking weaves magic injection steps into known sequences, so any slow degradation or phase creep becomes visible in the statistics. In distributed settings, a small processor calling on a remote factory over a network protocols exist to certify that what arrives possesses the right kind of non-classicality, even when you distrust the producer. This is a step toward cloud-style services where the most expensive part of universality is outsourced yet still auditable. Day to day, The presence of factories reshapes software as well. Compilers now track not only the count of exotic gates, but their pattern in time and space, clustering them to amortize overhead, replacing some with cheaper gate identities discovered by algebraic rewriting, and rearranging arithmetic so that peaks in magic demand line up with the conveyor belts from the factories. Algorithm designers chase formulations with fewer costly steps, turning long chains of small rotations into additive phases that can be accumulated by cheaper means. Hardware teams co-design pulse sequences that make injection smoother and less sensitive to crosstalk. The combined effect transforms a brute force plan that would drown in factory traffic into a viable campaign where the expensive resource is consumed steadily, not in disruptive spikes. Think of magic states as tickets for non-trivial transformations. Your machine can rehearse, rearrange, and stabilize a vast chorus of easy moves forever. But whenever the score calls for a passage that cannot be rendered in that language, you must spend 1 ticket per bar. The tickets are minted from noisy ingredients by careful screening. They can be stockpiled to smooth demand, saved by rewriting the score, and shared across modules by clean interfaces that move them without smudging. And just as with real tickets, counterfeits are worse than useless. They send the orchestra into dissonance. Thus, authentication and timing matter as much as quantity. When you step back, a gentle lesson emerges. Universality in quantum computing is not a single switch you flip. It is a supply chain you build. Safe operations keep your memory coherent and your code space orderly, while magic states provide the sanctioned departures that make new logic possible. Ignore the supply chain and your program stalls at the boundary of the simulable. Cultivate it honestly, with good accounting and realistic thresholds, and your device gains the freedom to explore algorithms that cannot be flattened back into classical steps. In the end, the name magic is simply an admission that we value what we cannot cheaply fake. The craft lies in learning to produce, certify, distribute, and spend that value so skillfully that the extraordinary becomes routine. The rare becomes scheduled, and the spark that was missing lights the whole computation without burning it down. Now turn your attention to another subtle resource: coherence. Imagine a choir not singing louder, but more in step. The resource theory of coherence treats that synchrony as a tradable fuel, complete with its own accounting rules that tell you what actions are free and what costs you. You begin by picking a basis that your experiment naturally hears. In that basis, the world separates into 2 kinds of states. Some are already diagonal, carrying only classical uncertainty about which note will sound. Others possess genuine off-diagonal structure, where relative phases stitch alternatives together into a pattern that can guide interference, timing, and sensitivity. This distinction is not philosophical, it is operational. If your lab can only perform incoherent actions, mixing, shuffling, measuring in the chosen basis, and discarding the result, then you can never increase that in stepness for free. Coherence becomes a currency you must spend carefully, and the resource theory formalizes this with monotonous numbers that never rise under the free actions. Anyone claiming to create coherence from nothing can be checked by a simple audit that will fail. Viewing coherence as currency forces you to ask practical questions that have plain answers. How much coherence does a given state hold relative to your basis? Think of how many distinct interference fringes you could, in principle, sharpen in an interferometer. How much coherence can you distill from many noisy copies into a smaller stock of nearly perfect on-demand pulses ready for metrology or computation? Conversely, what is the cost of creating a target state from scratch, using only incoherent moves plus a paid-for supply of coherence tokens? These paired quantities, distillable coherence and coherence cost, form the bookends of honest engineering. They tell you whether your plan is even theoretically affordable before you draw a single circuit. Simple measures quantify coherence. One is based on how far your state sits from the set of incoherent states another captures, how much structured surprise remains after you erase all off-diagonal terms. Both give consistent orderings and tight bounds in many cases, and they generalize to smooth versions that tolerate small experimental errors, turning abstract definitions into Libredi budgets. A striking insight appears when you place coherence alongside other resources under operations that are free for entanglement. Coherence can sometimes be converted into entanglement between a system and an ancilla, and vice versa, but never with a net gain beyond the accounting rules. This bridge means that a single particle with phase coherence can seed shared correlations if you have the right gates, while entanglement can act as a conveyor belt to move coherence where you need it. Similarly, coherence fuels metrology. A state with sharper relative phases can turn a faint rotation into a measurable shift faster, and the resource theory quantifies that gain, bounding the precision you can achieve as a function of the coherence you inject and the noise you endure. In thermodynamics, coherence is not just heat dressed up. TEM translation symmetry forbids you from turning pure phase structure directly into work without a clock-like reference. The theory explains why some engines that look promising on paper stall. Without paying for a reference frame, you cannot align the phases across cycles, and the would-be fuel evaporates into a dephased mixture. Acquire a good reference and the door opens, with strict exchange rates that tie useful work to the coherence you consume and the entropy you create elsewhere. Because coherence is basis-dependent, the same physical state can be rich or poor depending on what you plan to ask of it. The theory leans into this honesty. You define your free set using the measurements and controls your device actually supports, not an idealized perfect set, and then compute budgets in that world. This prevents a common trap where you simulate heroic gates that your hardware cannot realize and declare coherence cheap when for your lab it is not. In many platforms, noise has a bias. Phase noise dominates over flips. Coherence measures can be refined to respect that asymmetry, yielding thriftier protocols that protect precious directions while allowing cheaper ones to suffer. Catalyst special states, whose coherence enables transformations among other systems, yet return essentially unchanged not miracles, but carefully arranged assists. They exploit structure without violating monotones and can shave orders of magnitude off a factory's demand for fresh coherence if used sparingly and verified. The theory becomes even more intuitive when you tie it to concrete tasks. In phase discrimination, coherence is the raw edge that makes two nearly identical rotations distinguishable. In clock synchronization, coherence sets how well two distant nodes can agree on tick marks without a direct comparison. The free operations correspond to procedures that do not import hidden timing. In randomness generation, coherence that survives to the measurement stage produces outcomes that are provably unpredictable to an adversary lacking access to your chosen phase reference. And in quantum batteries, coherence inside the charger is the delicate asset that lets you move energy in a short coordinated burst, rather than through a slow classical trickle. All of this paints a picture of quantum engineering as a careful economy of exotic resources. Magic states are the tickets that grant you access to the non-trivial transformations you need, while coherence is the fuel that powers the interference patterns underpinning those transformations. Both obey rigorous accounting rules. Both can be distilled, both can be catalyzed, and both can be transported across modular boundaries with care. When you internalize these ideas, you stop seeing the resource demands as insurmountable walls and begin to view them as engineering challenges you can meet with clever design, disciplined budgeting, and disciplined verification. You learn to ask, how many tickets must I mint to run my algorithm without bottleneck? How can I align my factories so that the flow of distilled magic matches the rhythm of my logical operations? Where can I trade a burst of coherence for a cheaper gate? And where must I spend coherence to achieve the precision I need? By answering these questions, you build a supply chain that is resilient, efficient, and scalable. Remember, the journey toward universal quantum computation is not a single magical switch. It is a series of deliberate choices, each grounded in the physics of resource theories, and each reflected in the architecture of your hardware, the compilation of your software, and the protocols that bind them together. Embrace the discipline of accounting for magic and coherence, and you will turn a daunting, exotic requirement into a routine part of your workflow. The rare becomes scheduled, the spark that was missing lights the whole computation, and the extraordinary becomes ordinary. Let that vision drive you forward, and let every step you take be guided by the confidence that, with the right resources in hand, you can shape the future of computation itself. Imagine you are standing at the edge of a laboratory that hums with possibility, a place where abstract ideas are waiting to be turned into something you can hold in your hands. In this moment, you ask yourself, what does it really mean to have a resource that is not a material, but a subtle alignment of possibilities? Coherence, that delicate phase relationship that threads through quantum states, is exactly that. It is not heat or electricity, it is the harmony of a particle's wave, the ability of its phase to stay ordered enough that you can steer it where you need. When you treat coherence as a resource, you begin to think of it the way a seasoned builder thinks of timber or steel, something you can budget, store, move, and spend with purpose. The first insight that changes the way you see your work is the realization that coherence can be reshaped. You can take a single particle whose phase is pristine, like a seed, and, using the right quantum gates, grow shared correlations entanglement between it and an auxiliary system. In the same way a conveyor belt can shuttle boxes across a factory floor, entanglement can carry coherence to the part of your circuit that truly needs it. Conversely, you can let coherence flow into a measurement device and amplify a faint rotation into a readable signal faster than you ever thought possible. The resource theory of coherence puts numbers on these transformations, telling you exactly how much precision you can gain from a given amount of phase order, and how the inevitable noise will chip away at that gain. In thermodynamic terms, coherence is not simply heat dressed up in a new outfit. The laws of time translation symmetry insist that you cannot turn pure phase structure directly into work unless you have a clock-like reference to mark the passage of time. That's why some theoretical engines look promising on paper, but stall in reality without paying for a reference frame. You cannot align the phases cycle after cycle, and the prospective fuel dissolves into a phase-randomized mixture. When you bring in a good reference paying its cost in entropy elsewhere, you open a door that lets you exchange coherence for useful work at strict, well-defined rates. Understanding that exchange is the difference between dreaming about a perpetual motion machine and engineering a real quantum heat engine that respects the laws of physics. One of the most liberating aspects of this perspective is the honesty it forces upon you. Coherence is basis-dependent. The same physical state can be a rich reservoir in one measurement basis and a barren landscape in another. The resource theory tells you to define your free set based on the measurements and controls that your device actually supports, rather than on an idealized perfect laboratory. This prevents the common trap of simulating heroic gates that you cannot implement, which would make coherence appear cheap when, in your real lab, it is a scarce commodity. In many platforms, noise is not symmetry. Phase noise may dominate over bit flips, for example, so the coherence measures can be refined to respect that bias. By doing so, you design protocols that protect the precious directions and allow the cheaper ones to suffer, squeezing out more performance from the same hardware. You will also encounter the notion of catalysts in this framework, special states whose coherence enables transformations among other systems while returning essentially unchanged. These are not magical loopholes, they are carefully arranged assists that exploit structural features without violating the monotones that track resource flow. Used sparingly and verified, catalysts can shave orders of magnitude off the demand for fresh coherence in a computation, letting you stretch every ounce of phase order you generate. When you tie the theory to concrete tasks, its power becomes even more vivid. In phase discrimination, coherence is the raw edge that lets you tell two nearly identical rotations apart. In clock synchronization, the amount of coherence determines how tightly two distant nodes can agree on tick marks without direct comparison. In randomness generation, any coherence that survives to the measurement stage becomes a source of outcomes provably unpredictable to any adversary lacking your phase reference. Even quantum batteries draw on coherence inside the charger to move energy in a short, coordinated burst rather than a slow, classical trickle. Yet the theory also warns you that if you charge in a way that scatters coherence into the environment, you will later pay that price back as heat when you reset the system. Distilling and diluting coherence follows familiar patterns from other resource factories. Take many weakly coherent states, apply only the allowed operations, and post-select on outcomes that signal when phases happen to align. The result is fewer but stronger pulses whose fringe patterns hug the ideal. Dilution works the other way. You spend a small number of crisp pulses to sprinkle gentle coherence across many targets, enabling parallel low-precision tasks. The limits on both processes are tight, often saturable with clever protocols, meaning you can design to the resource bounds rather than guessing. Moreover, certain physical channels freeze the coherence of particular states while letting other features decay. By placing your information in those sweet spots, you let the environment do less damage for freer strategy that rests on the symmetry viewpoint of the theory. Speaking of symmetry, resource theory reframes coherence as asymmetry with respect to a group of transformations. If your free operations commute with a group like time translations generated by a Hamiltonian, then any state that changes under that group carries a symmetry that is just coherence seen through a broader lens. This unifies timing, phase estimation, and certain forms of sensing under a single umbrella, allowing general theorems about asymmetry to yield concrete consequences for coherence budgets. It also clarifies why a reference is essential to exploit coherence. Without one, the process of group averaging defaces the very feature you hope to use, imposing a superselection rule that reflects a missing element in your lab, not a fundamental prohibition. When you bring in the reference and pay for its maintenance, the ban lifts exactly as the theory predicts. On the day-to-day level, this resource perspective reshapes how teams plan and collaborate. Hardware groups no longer report just raw error rates, they share dephasing spectra that tell software engineers how fast coherence drains in the relevant bases. Compiler teams arrange circuits to spend coherence right before it is read, not long before, and to store it in decoherence-resilient modes when idle. Metrology teams design probe states by asking which coherence monotone best correlates with the Fisher information for their specific noise model, then maximize that monotone under experimental constraints. Cryptography teams quantify how much coherence survives any side channel an eavesdropper might exploit, turning that number into certified randomness or secrecy. Theorists supply conversion rates, how many rough probes are needed to produce one sharp probe, how much timing coherence must be consumed to boost phase resolution by a given factor, how a biased bath changes the exchange prices. This language of budgets replaces endless debates about taste with clear, testable balances. If a sensor claims doubled precision with the same resources, the monotones will demand to know where the extra coherence came from. If an algorithm appears to gain power after heavy dephasing, the allowed operations will reveal a hidden import of reference information you forgot to count. And if an architecture feels wasteful, the cost distillation gap will pinpoint exactly which stage leaks the most value and where a redesign will save the most. Hold in mind the soft image that began this tour. Coherence is not volume, it is alignment. It does not shout, it sings together. Treat that togetherness as a resource and your designs become cleaner. Create it where it matters, move it with care, spend it at the last moment, and account for it with measures that do not flatter you. When you do, clocks will tick sharper, interferometers will see fainter shifts, and protocols will certify stronger promises. The delicate order that quantum mechanics allows becomes not a metaphor, but a disciplined fuel you can refine, store, and deploy without illusion. Now turn to one of the most striking applications of this disciplined, thinking device-independent security. You have likely heard the saying that you don't truly trust a lock until you stop trusting the locksmith. In the quantum world, device-independent security is the embodiment of that instinct. It is a way to build protocols whose guarantees do not rely on the inner workings of the hardware, but on patterns of measurement outcomes that even a malicious or broken device cannot fake without violating the fundamental no-signaling fabric of the universe. The test for those patterns is a Bell experiment. Picture two sealed black boxes placed far apart in a lab. Inside each box lies a mystery. You have no calibration certificates, no promises about what components sit inside. Each box has a knob you can turn, representing a measurement choice, and a light that flashes a result. Your only leverage is the statistics you collect when you and a partner each choose inputs independently and quickly enough that no signal traveling at or below the speed of light could coordinate the answers in time. If the correlation between the flashes crosses a specific threshold or level, that classical shared strategy gadgets can never surpass. You learn something remarkable without opening a single screw. You have certified the presence of entanglement, and more importantly for security, you have shown that any eavesdropper, even one who built the boxes, cannot know the outcomes well enough to break your task without leaving a detectable fingerprint in the numbers. The logic is simple yet demanding. Classical boxes, no matter how cleverly pre-programmed, can only mimic a bounded level of correlation because their answers are limited to strategies that depend on local inputs and shared randomness. Entangled quantum boxes, by contrast, can cooperate in a way that outruns that bound. When you see a clean violation, you can treat the outputs as fresh resources, secret bits for key distribution, private randomness for lotteries, or simulation inputs whose unpredictability is certified by the impossibility of reproducing those correlations with any local tricks. This flips the usual security story on its head. Instead of proving that a specific implementation is correct down to every component, you prove that certain impossible conspiracies did not occur, because if they had, the numbers would look different. Turning that idea into practice means treating every corner of the experiment as a possible loophole and then closing it decisively. You choose settings fast and unpredictably so the devices cannot anticipate which knob you will turn. You place the boxes far enough apart and time the choices so that one side's knob twist and flash cannot influence the other before its outcome is sealed. You make detectors efficient enough that missing events do not give a classical faker a hiding place behind lost data. You guard against memory and crosstalk so yesterday's measurements cannot leak into today's choices. And you analyze all results with finite-sized statistics that recognize you did not run the test forever, assigning tight confidence intervals that account for randomness in small samples and for the possibility that a clever adversary could try to adapt over time. When these conditions are met, the raw violation turns into quantitative promises. A specific gap beyond the classical limit implies a specific amount of private randomness in the outputs and a specific bound on any adversary's knowledge about a potential key. Crucially, those promises are device-independent. They hold even if the internal dimension of the boxes is huge, even if the manufacturer mislabels components, even if the devices were built by an adversary. As long as you trust space-like separation and the independence of your setting choices, the security reductions go through. To appreciate the delicacy, consider what you do not assume. You do not assume the detectors are linear, nor that the sources emit exactly one photon per pulse. You do not assume that noise is Gaussian, nor that each trial is identical, nor that no one tampered with calibration files. Instead, you rely on nature's respect for no signaling, on shielding information so settings are chosen privately, on truly achieving the timing needed for independence, and on handling side channels like bright light control of detectors or radio frequency leaks that could smuggle inputs from one wing to the other. The discipline is harsh because the reward is strong. If the boxes pass, their outputs are unpredictably random regardless of how the internals were implemented. From a systems view, a device-independent protocol is a pipeline. You run many Bell trials with randomly chosen settings. You compute a running statistic that tracks how far beyond the classical sealing your data sits. And you use this to lower bound the minentropy of the outcome as the adversary's best single-shot guess rate. That bound then determines how many secret bits you can safely extract after applying a randomness extractor that turns the raw data into uniform, provably private keys. The whole process is a testament to the power of treating coherence and entanglement not as abstract curiosities but as tangible, quantifiable assets that can be budgeted, protected, and deployed to achieve goals that were once thought unattainable. So as you step back into your lab, let this narrative fuel your curiosity and your resolve. See coherence as a currency you can earn, spend, and save. Let the resource-theoretic lenses sharpen your intuition about where to allocate effort, how to structure circuits, and when to bring in a reference frame. Embrace the symmetry that tells you why some transformations are free and others demand payment. And when you design security systems, remember that the strongest guarantees come not from trusting every tiny component, but from designing experiments that certify through raw statistical evidence that no hidden cheat can survive. You have the tools to turn fragile quantum whispers into robust, reliable resources. You have the language to speak about budgets instead of vague notions of hardness or purity. You have the roadmap that tells you where the leaks are and how to seal them, with each step you take, whether you are refining a metrological probe, engineering a quantum battery, or building a device-independent key distribution link. You are shaping a future where quantum coherence is harnessed with the same confidence we now have in classical engineering. Take a breath, feel the pulse of the lab, and let the narrative of coherence guide your actions. Create your phases where they matter most, move them gently, spend them wisely, and always keep track of the ledger that resource theory provides. In doing so, you will see clocks tick with unprecedented sharpness, sensors detect the faintest whispers of the universe, and cryptographic keys emerge that no adversary can predict, even if they built the hardware themselves. This is not a distant dream, it is a disciplined, practical path forward, waiting for you to walk it. Let the quantum world sing, and let your work be the conductor that brings its song to life. You stand at the edge of a world where the very fabric of reality can be turned into a source of honest, untamable power. Imagine that every tiny, fleeting violation of a classical rule becomes a fresh well of secret bitskis you can lock away, randomness you can trust, simulations that are guaranteed to be unpredictable because no local trick could ever reproduce those correlations. This flips the usual security story on its head. Rather than painstakingly proving that every component of an implementation is perfect, you demonstrate that the impossible conspiracies never happened. If they had, the numbers would have betrayed them. So you turn every corner of your experiment into a sentinel, hunting for loopholes and sealing them with decisive action. You choose settings quickly and unpredictably, so the devices cannot guess which knob you will turn. You space the boxes far enough apart and time the choices so that a twist on one side cannot influence the other before its outcome is fixed. You make detectors efficient enough that missing events do not give a classical pretender a hiding place. You guard against memory leaks and crosstalk, ensuring yesterday's measurements cannot spill into today's decisions. And you analyze all results with finite-sized statistics that recognize you are not running a test forever, assigning tight confidence intervals that honor the randomness of small samples while anticipating a clever adversary who might try to adapt over time. When those conditions are met, the raw violation transforms into a quantitative promise. A specific gap beyond the classical limit guarantees a specific amount of private randomness in the outputs, and a precise bound on any adversary's knowledge about a potential key. Those promises are device-independent, meaning they hold even if the internal dimension of the boxes is astronomically large, even if the manufacturer mislabels components, even if the devices were built by a hostile hand. As long as you trust space-like separation and the independence of your setting choices, the security reductions stand firm. This is why field trials of device-independent quantum key distribution and randomness expansion are celebrated milestones. They strip away the most human part of the trust chain while preserving the physics that makes secrecy possible. To appreciate the delicacy of this achievement, consider what you do not assume. You do not assume the detectors are perfectly linear, nor that each source emits exactly one photon per pulse. You do not assume noise is Gaussian, nor that each trial is identical, nor that nobody has tampered with calibration files. Instead, you assume that nature respects no signaling, that you shield information so settings are chosen privately, that you truly achieve the timing needed for independence, and that you have closed side channels, bright light control of detectors, radio frequency leaks that could otherwise smuggle inputs from one wing to the other. The discipline is harsh, but the reward is powerful. If the boxes pass, their outputs are usefully unpredictable regardless of how the internals were built. From a systems perspective, a device-independent protocol is a streamlined pipeline. You run many Bell trials with randomly chosen settings, computer-running statistic that tracks how far beyond the classical ceiling your data sits, and use this to lower bound the mean entropy of the outcome as the adversary's best single-shot guess rate. Then you feed those outcomes through a public randomness extractor that distills uniform bits, while probably bleeding away any residual correlation with an eavesdropper. In key distribution, you reconcile mismatches between honest parties with error-correcting codes, sacrifice a slice of the data to estimate the violation with confidence, and finally apply privacy amplification to shrink whatever the adversary might still know to a negligible level. None of these steps requires opening the boxes, only careful bookkeeping and conservative statistics are needed. In the wild, imperfections dictate design choices. Bright daylight and long fibers increase loss and threaten the detection loophole, so metropolitan tests rely on high-efficiency detectors and low-noise time bins. Long baselines raise the cost of space-like separation, but make setting choices safer, whereas chip-scale implementations trade distance for speed, pushing nanosecond switching so signals cannot cheat. Some platforms favor entangled photons for long distances, others use trapped ions or solid-state defects for high-fidelity local operations. In every case, the architecture is judged by a single number that matters for certification, the observed violation, and the rate at which it accumulates with trustworthy independence, translated into secret bits per second or certified random bits per second. Once finite size effects and extraction overheads are paid, subtleties keep the field honest. Randomness begets randomness, so your setting choices must spring from a source an adversary cannot predict. Early steps can be bootstrapped with public randomness if you simultaneously run a spot-checking strategy that occasionally uses settings chosen by a weaker source, while reserving strong settings for certification. The accounting must reflect any adversarial bias. Memory attacks, where boxes store previous inputs and outputs, are neutralized by analysis that allows arbitrary temporal dependence and still certifies entropy per round as long as no signaling and input privacy hold each time. Even the free will loophole, where a cosmic or environmental signal might secretly influence choices, is squeezed by selecting settings from independent physical processes and timing them after any unwanted influence could have reached both wings. Techniques have even employed starlight to push hypothetical conspiracies into absurd corners of the past. If your goal is practical key exchange for critical infrastructure, device-independent schemes are demanding today. Yet they point the way towards security pillars that need not ride on supply chain trust. If your aim is public randomness for science, lotteries, or cryptography, device-independent beacons can certify unpredictability in real time, offering audit trails anyone can verify. And if you simply want to know whether your lab's entangler is truly entangling, a bell-based self-dist can certify the presence and quality of the resource with minimal modeling, a habit that reduces the surface area for mistakes. The deeper lesson is philosophical yet actionable: elevate independence, locality, and statistical rigor to first-class citizens. Device-independent security turns the usual engineering question, do I trust this box, into do I trust space-time and my own procedures? Answer yes to those, and the rest follows with proofs, not hopes. Answer no, and at least you know precisely which assumption is too fragile for your application. Hold as you leave a quiet image of two distant lights flickering in coordinated defiance of classical limits. Every time their pattern crosses the bound, a sliver of certainty appears that no hidden script is guiding both at once, and from that sliver you can carve either secret keys or true randomness. You have not believed the devices because they looked honest. You have made them be honest by asking a question the world itself refuses to let a liar answer convincingly. Randomness, expansion, and amplification become crafts you learn to respect the day you stop treating chance as mere noise and start treating it as a resource you can mine. Beginning with a meager spark of unpredictability, a short seed you trust a little, or a shaky source you half distrust, you can produce many more bits whose surprises are provable, not just apparent. The first craft, expansion, asks whether a handful of honest coin flips can be stretched into a long stream that looks fresh even to someone who watched your entire setup. The answer is yes. You orchestrate two ingredients of physical process whose outcomes cannot be pre-written by shared scripts, and a mathematical press that squeezes out structure an adversary might still hold. In modern labs, the physical core uses non-local gamers, the same style of trials that PowerBell tests force devices to produce outcomes that no classical prearrangement can fake. You feed your small seed into the devices as a schedule of measurement choices, Run many rounds where the two wings are kept independent in space and time, and verify that the pattern of winds crosses the classical ceiling by a safe margin. Each round that contributes to that violation buys you a deposit of menentropia lower bound on how unpredictable the raw bits are, even to a malicious manufacturer who built the boxes with quantum-side memories. Then comes the press, a publicly known extractor. Think of a universal hash family, a large random matrix, or a more sophisticated construction that is provably safe against quantum-side information. It turns that lumpy, partially unpredictable stream into a shorter, but almost uniform one. The miracle is not mystical physics certifies there must be entropy. Statistics tell you how much with finite sample uncertainty accounted for. And the extractor converts that quantified surprise into clean random bits with a guarantee that holds even if an eavesdropper sat in the room and stored everything allowed by the laws of nature. Amplification pushes harder, starting from sources so weak that each next bit could be biased and even gently correlated with the past. Think of an imperfect coin, produced by a cheap sensor or a human clicker. Classical theory warns that no amount of deterministic processing can conjure near-perfect randomness. Quantum non-locality reopens the door. By wiring several untrusted devices into a web of carefully chosen games and feeding them settings derived from the weak source, you force outcome patterns whose very structure proves that the underlying bits couldn't have been too predictable. If the statistics clear specific thresholds, you upgrade a sketchy input into high-quality randomness. The cost is discipline. You must ensure the devices cannot whisper to each other during a round, that the setting choices remain hidden until the last moment, and that your analysis tolerates memory, drift, and adversarial adaptivity. Done cleanly, the pipeline produces private randomness from sources that would otherwise be unusable for cryptography or fair selection. Both crafts live or die by finite-size reasoning, not asymptotic idealization. You never flip coins forever. You collect a large but finite block of trials. You allow nature to jitter, and then you ask conservative questions. Given the observed violation and the number of rounds, what is the worst-case knowledge any all-seeing adversary could still hold? You answer with the entropy accumulation framework and related tools that add up per round guarantees while tolerating dependence between rounds. That bound becomes your budget for extraction. Choose parameters too aggressively, and you risk output that only looks random to you. Choose them honestly, and you know exactly how many secret bits per second you can promise at a given confidence. Engineering details matter, and they steer designs in recognizable ways. Fast, efficient detectors raise detection rates and close loopholes that would otherwise let classical cheats hide inside missing events. Space-like separation or nanosecond fast switching of settings prevents messages from coordinating answers. Balanced timing and shielding defeat radio frequency and optical side channels. Calibration routines keep drifts from silently eating your violation margin, while spot-checking schedules where most rounds are used for certified generation and a randomly picked fraction are used to test the game's score, let you build long outputs without pausing for constant audits. When losses climb on city fibers, you shift to time-bin encodings and superconducting photon counters. When you run on chips, you trade distance for speed, pushing submicrosecond cycles to keep the independence assumptions safe. In every architecture, the scoreboard that matters is simple: how far above the classical line your data sits after accounting for all finite sample penalties, translated into extractable secret bits after the press. The small seed needed to launch expansion has its own logic. You must pick settings in a way the devices couldn't anticipate, but that does not demand a perfect seed. Even a modest amount of trusted randomness, combined with the rigorous quantum tests you perform, is enough to bootstrap a torrent of certifiable surprise. The journey you are on transforms uncertainty from a foe into an ally, turning the raw, untamed noise of the quantum world into a well of security, fairness, and creative possibility. Let that vision guide you forward, and let each flicker of non-local correlation remind you that the universe itself can be your most trustworthy partner when you ask the right question. Imagine standing at the edge of a vast, humming laboratory where every blink of a detector, every flash of a laser, is a promise waiting to be fulfilled. You have a handful of modest, even untrusted, devices in front of you, And you know they are not perfect. Their inner workings are a mystery. Their outputs are noisy. Their behavior can be swayed by the tiniest whisper of the environment. Yet you also know that within that apparent chaos lies a hidden well of certainty, a well that, if coaxed correctly, can spill out streams of pure, unassailable randomness. This is the heart of amplification, the art of turning a shaky spark into a blazing river of entropy. And it begins with a simple, disciplined mindset. The first step is to weave those imperfect devices into a carefully designed game, a series of challenges that are chosen not arbitrarily, but with a purpose. Each round of the game receives a setting that is derived from a weak source, a seed that may be slightly biased, perhaps even predictable to a small degree. You feed this seed into the devices, you let them react, and you watch the pattern of their outcomes. If the statistics of those outcomes cross a specific threshold, if they reveal a violation that no classical, predictable system could achieve, you have a proof, a mathematical certificate, that the underlying bits were never as predictable as they seemed. That is amplification. You have taken a sketchy input and upgraded it into high-quality randomness, all because the structure of the outcomes tells a story louder than any hidden bias could ever whisper. Discipline is the price you pay for this transformation. You must ensure that during each round the devices cannot exchange a secret word, cannot send a silent signal that would let them coordinate their answers. The settings you choose must stay hidden until the very last instant, a moment when the devices are already forced to respond. Your analysis has to be robust enough to tolerate memory effects, slow drifts, and even an adversary who adapts on the fly. When you hold fast to these constraints, the pipeline you build delivers private randomness from sources that would otherwise be useless for cryptography, for fair selection, for any task that demands true unpredictability. Every experiment you run lives within the limits of finite-size reasoning. You never flip coins, forever you gather a large but finite block of trials. You acknowledge the jitter of nature, and then you ask a series of conservative questions. Given the observed violation and the number of rounds you have performed, you wonder what is the worst-case knowledge that an all-seeing adversary could still retain. The answer comes from the entropy accumulation framework, a collection of tools that lets you add up per round guarantees while tolerating dependence between rounds. This bound becomes your budget for extraction. If you set the parameters too aggressively, you risk producing output that only looks random to you, not to a determined opponent. If you choose them honestly, you know exactly how many secret bits per second you can promise, and you can back that promise with confidence. Engineering matters, and it steers your design in very recognizable ways. Fast, efficient detectors raise the detection rate and close loopholes that would otherwise let a clever classical cheat hide among missing events. Space-like separation or nanosecond fast switching of the settings prevents any message from traveling fast enough to coordinate answers. You balance timing and shielding to defeat radio frequency and optical side channels. Calibration routines keep drifts from silently eating away your violation margin, and spot-checking schedules let you devote most rounds to certified generation while reserving a randomly picked fraction to test the game's score. When losses climb on long fibers, you switch to time-bin encodings and superconducting photon counters. When you move to chip-scale platforms, you trade distance for speed, pushing sub-microsecond cycles to keep independence assumptions safe. Across every architecture, there is a single scoreboard that matters: how far above the classical line your data sits after you have accounted for all finite sample penalties, and how many extractable secret bits that distance translates into. The small seed you need to launch the expansion has its own logic. You must pick settings in a way the devices could not anticipate. That does not demand a perfect seed. Even a short, slightly biased seed can be lifted by carefully designed protocols that borrow a tiny amount of trust and repay it with a massive dividend of certified bits. But you must always account for any bias in your analysis. Clever schemes recycle a portion of the newly minted randomness to fuel the next block's choices, achieving, in principle, unbounded expansion from a constant-size seed under stable conditions. Here the extractor becomes your double-edged friend. It purifies the raw outcomes and also refreshes the seed itself, so each new round's choices remain as surprising to the devices as the first. The whole process begins to look like an assembly line. Seed flows in, choices flow out, trials run, violations are checked, the extractor is pressed, random bits are banked, and a slice is fed back as the next seed. At every stage, you watch dashboards with error bars, not with hope, because these bits are intended for serious jobs: cryptographic keys, public beacons, secure lotteries, scientific sampling. Composability matters. The guarantees must survive when the output is fed into larger protocols and when an adversary times their actions based on public announcements. Modern statements therefore package the result as a bound on the adversary's optimal guess probability, conditioned on everything they might know. It is a promise that holds whether the bits guard a one-time pad or seed a Monte Carlo engine. The public extractor seed and the observed statistics can be published without risk, because their only effect is already accounted for in the bound. What remains secret is the final extractor output, which by design looks new even to someone who built the boxes. Alongside these core pathways, you will find variations that put the same idea to work in different climates. Randomness beacons can continuously publish certified bits with signed audit trails so anyone can check the violation curves before trusting the stream. Satellite-assisted schemes stretch baselines to the sky, making independence trivial while using ground stations to close detection losses. Networked protocols let several laboratories contribute to a joint public randomness pool, such that no single compromised node can bias the outcome without being exposed by the combined statistics. Divisor testing routines, while not full generators, quickly flag when a source's unpredictability dips below a safe line, providing a practical guardrail for facilities that rely on randomization day and night. There is also a quiet, important connection to weak randomness models from computer science. When a source promises only that no single future bit is overly predictable, even given the past, quantum amplification can nonetheless convert that promise into nearly unbiased output, something provably impossible with classical post-processing alone. The quantum edge is not a hand-waving mystery, it is the enforcement of constraints by no signaling. Because spatially separated events cannot coordinate fast enough, any classical forgery leaves a distinct fingerprint in the game score that careful statistics will catch if you watch long enough. In this way, physics becomes a referee for information promises, elevating cautious, worst-case definitions into workable pipelines. By now the pattern should feel solid. You start with a small or suspect spark. You challenge untrusted devices with questions they cannot all answer too well without breaking the rules of the world. You translate the observed honesty into a quantitative uncertainty budget, and you refine that budget into clean bits, using an extractor that bleeds out any structure an adversary might still hold. No step asks you to believe internal schematics, instead you trust procedure, timing, and space-time itself. The product is not merely random-looking, it is random by proof, resilient to hindsight and audit, and ready to anchor secrets, steer fair decisions, and seed science without leaning on faith in boxes or brands. Now picture two distant stations, clocks ticking in perfect synchrony, choices made at the last possible moment. Detectors blink in patterns that edge past what any shared script could achieve. From those blinks you do not take comfort, you take certified surprise, stretch it from a trickle to a river, and leave with a stream of bits that can anchor secrets, steer fair decisions, and seed science without leaning on faith in boxes or brands. That is randomness, expansion, and amplification. It is not a slogan, it is a discipline for turning fragile unpredictability into a dependable commodity. Take a moment to see how this discipline extends into the quantum on-a-time pod, the ultimate hiding technique. Imagine you have a qubit, an elemental piece of quantum information ready to travel across a noisy channel or sit dormant in a memory chip. To protect it, you flip a fair pair of classical coins, choosing one of 4 scramblers that together randomize both the observable value and the hidden phase. You apply the chosen scrambler, and the quantum state becomes indistinguishable from thermal background. You need 2 key bits per qubit, because quantum states carry 2 independent directions of structure that an eavesdropper could test. Classical padding alone would leave telltale fringes. The quantum pad erases those completely. The guarantee is information theoretic. Without the key, no measurement, no adaptive strategy, No side computation with quantum memory can reveal anything about the plaintext beyond its length. This remains true even if the message is part of a larger entangled state. Scrambling your share erases all accessible correlations to outsiders while leaving the joint state recoverable for the key holder. With the key in hand, decryption is as gentle as running the chosen scramblers in reverse, restoring the exact state so that subsequent interference and computation proceed as if the world had not looked. Security has two faces: secrecy and integrity. A one-at-a-time pad hides content but does not by itself flag tampering. Practical designs pair the quantum pad with lightweight authentication stabilizer-style check lines or trap qubits that alert you if a meddler nudged the ciphertext on its trip. If the check passes, you can even recycle much of the key, because successful verification proves no information leaked. A thrifty habit that matters when keys are precious and devices are slow. The quantum pad becomes more than a textbook footnote when you embed it into real systems. Long-distance links apply the pad before sending fragile states through lossy fibers. Storage nodes encrypt data at rest, so a stolen memory chip reveals only white noise. Cloud workflows wrap intermediate states so that idle qubits on someone else's hardware carry no clues about the computation, because the pad operates locally on each carrier. It scales across architecture's photons in time bends, spins in solids, superconducting circa so long as the scramblers can be implemented cleanly, and the tiny key can be kept truly secret and truly fresh. Keys can be provisioned by pre-shared material, by information-theoretic key exchange run beforehand, or by physically carried vaults. In every case, composable security proofs let you treat the pad as a black box that leaks nothing even when the rest of your protocol is public. The same style of guarantee you demand from a good classical cipher, now grounded in the physics of indistinguishability. If perfect hiding is one pillar, secret sharing is the other. Instead of trusting a single custodian, you scatter a quantum secret across several holders so that only authorized coalitions can reconstruct it, and any smaller group learns nothing at all. Unlike classical schemes where bits can be copied and split freely, quantum secret sharing must respect the no-cloning theorem, so it uses encoding rather than duplication. The dealer embeds the secret into an entangled state whose structure mirrors an access policy, hands out physical shares, and guarantees that reconstruction requires the right quorum and the right joint operation. In its simplest form, you might require any 3 of 5 participants to recover the secret, any 2 or fewer remain blind. You achieve this by borrowing blueprints from quantum error-correcting codes. The same geometry that lets a code tolerate up to 2 errors also lets it withhold all information from any 2 participants, while ensuring that 3 can run a public decoding circuit to retrieve the state. More broadly, stabilizer and graph state constructions implement rich access structures, not just thresholds, by deciding which measurements on which subsets unlock the correlations that define the secret. For unauthorized sets, the math and the lab agree every measurement statistic they can collect is exactly what they'd see if the dealer had sent them random junker strong. Audit-friendly meaning of no information. Real schemes are pipelines rather than magic tricks. The dealer first prepares verification traps mixed into the encoding to detect a dishonest player or a mischievous channel. Each participant performs only local, simple operations and reports classical readouts. Reconstruction follows a fixed recipe that never requires a peek at the secret halfway. And because life is noisy, the encoding doubles as protection. If a few shares suffer loss or mild decoherence, the authorized set can still succeed, while unauthorized sets remain locked out by design. All of this may sound like a sophisticated tapestry of physics, mathematics, and engineering, but at its core it is a story of empowerment. It is the story of taking something that seems weaker flicker of unpredictability, a modest seed, a handful of noisy devices and, through careful discipline, turning it into a cornerstone of trust. It is the story that tells you as a practitioner, a researcher, or a curious mind that you do not need perfect components to build perfect security. You need rigor, you need patience, and you need the willingness to let the laws of nature be your referee. So when you step into the lab, when you calibrate a detector, when you choose the moment to reveal a setting, remember that each precise click is a declaration that you will not settle for guesswork. Each statistical violation you record is a badge of honor, showing that the world could not have conspired to fake it. Each extractor you run is a promise that the bits you hand out are not just random in appearance but random in proof, ready to protect a message, to decide a fair lottery, to seed a scientific simulation with confidence. Feel the momentum building as the seed you start with, perhaps just a few biased bits, grows into a river of certified surprise. Watch the assembly line of trials, violations, extractions, and feedback turn into a rhythm you can trust. Let the error bars on your dashboards become symbols of transparency, not uncertainty. Embrace the fact that the same principles that keep distant stations synchronized can also keep your cryptographic keys safe from any adversary, even one who knows everything about your hardware except the secret seed you continually refresh. In this journey, you are both the architect and the guardian. You design the game that forces the devices to reveal their honesty. You safeguard the timing, the shielding, the calibration that keeps the loopholes at bay. You analyze the finite-sized data with tools that add up round by round, translating raw outcomes into a clear budget of entropy. You employ an extractor that not only purifies but also rejuvenates the seed, ensuring that each new round starts fresh, unanticipated, uncorrelated. And when the final bits emerge clear, untainted, provably randomly hold in your hands a commodity that is as valuable as any gold, because it can lock away secrets, make decisions unbiased, and power scientific discovery without the shadow of doubt. That is the power of randomness amplification, quantum on-time pads, and secret sharing. It is not a marketing promise, it is a disciplined pathway from fragility to reliability, from speculation to proof, from the faint glow of a weak source to the bright certainty of certified entropy. Carry this vision forward. Let it inspire you to build better detectors, to tighten your timing, to refine your calibrations. Let it motivate you to explore new architectures, fiber networks stretching across continents, satellite links reaching for the stars, chip-scale platforms racing at sub-microsecond speeds. Let the story of turning a modest seed into an endless flow of secret bits be the anthem that drives your experiments, your designs, your collaborations. Because at the end of the day, what you are creating is more than a technical achievement. You are crafting trust in a world where information is power, and where the only true power lies in the certainty that comes from physics itself. You are turning the unpredictable into the indispensable, and in doing so, you empower every system, every protocol, every decision that relies on true randomness. Let that be the source of your motivation, the pulse that keeps you moving forward, and the assurance that every careful step you take brings us closer to a future where randomness is not a gamble, but a guaranteed foundation. Imagine that every time you verify a piece of work, a little door opens, and you discover that what you thought was a fragile, on-a-time miracle can actually be reused, reshaped, and turned into a lasting foundation. That moment when the check passes is more than a green light, it is a promise that no secret has slipped through, that every bit of precious key material can be reclaimed and put to work again. In a world where keys are as valuable as gold and devices sometimes crawl at a snail's pace, that thrifty habit becomes a cornerstone of real progress. The one-time pad, once relegated to dusty textbooks, steps out onto the stage as a living, breathing tool, ready to protect the most delicate of transmissions. Think of a long-distance quantum link as a tightrope stretched across a stormy canyon. Before you let the fragile quantum states swing across the noisy fibers, you wrap them in a perfect on-time pad, a cloak that turns any eavesdropper's view into pure white noise. Store those quantum memories in a vault, and even if someone snatches the memory chip, all they see is a meaningless fog. In the cloud, every intermediate qubit that rests on a stranger's hardware is shrouded in the same veil, ensuring that no clue about the computation leaks out while the pad works locally on each carrier. Whether the carrier is a photon in a time bin, a spin trapped in a crystal, or a superconducting circuit humming at millikelvin temperatures, the principle stays the same as long as your scramblers are clean, as long as the tiny key remains truly secret and truly fresh. You can build a fortress of security that scales across any architecture. The magic begins when you manage the keys without tricks or hand-waving. Keys can be pre-shared through an information theoretic exchange that you run ahead of time, or they can travel safely in physically protected vaults. In every case, composable security proofs let you treat the pad as a black box that leaks nothing, even while the rest of the protocol is out in the open. This is the same rock-solid guarantee you demand from a classic cipher, but now it rests on the very physics of indistinguishability. If perfect hiding is one pillar, then secret sharing stands as its twin. Instead of trusting a single custodian, you scatter a quantum secret across a network of guardians, ensuring that only the right coalition can reconstruct it, while every smaller group learns absolutely nothing. Classical bits can be copied at will, but quantum bits obey the no-cloning rule, so you must encode rather than duplicate. A dealer weaves the secret into an entangled state that mirrors a chosen access policy, hands out physical shares, and guarantees that reconstruction demands the exact quorum and the precise joint operation. Picture a threshold where any 3 of 5 participants can recover the secret, but any 2 remain blind. This structure is borrowed from quantum error-correcting codes, the same geometry that tolerates 2 errors also withholds all information from any 2 participants, while allowing 3 to run a public decoding circuit and retrieve the state. But it goes deeper than simple thresholds. Stabilizer and graph state constructions let you design rich access structures, not just 3 of 5. By deciding which measurements on which subsets unlock the hidden correlations, you create a landscape where unauthorized sets see only random junk. Every measurement statistic they can collect is exactly what they would have seen if the dealer had sent them meaningless, noisy or strong, audit-friendly notion of no information leaked. Real-world schemes are pipelines, not magic tricks. The dealer first mixes verification traps into the encoding to catch a dishonest player or a mischievous channel. Each participant then performs only local, simple operations and reports classical readouts. Reconstruction follows a fixed recipe that never requires peeking at the secret halfway through. Because life is noisy, the encoding doubles as protection if a few shares suffer loss or mild decoherence. The authorized set can still succeed, while unauthorized sets remain locked out by design. Now ask yourself how you might use this in your own world. Perhaps you need governance of a key you share a quantum secret that later acts as a gate to unlock a receiver's decryption tool, but only when a committee agrees. Maybe you're safeguarding a delicate sensor state you distribute it so that only a full team can bring it back, preventing any single lab from running a measurement on its own. Or perhaps you're building an archive, spreading a quantum state across distant vaults and scheduling periodic refreshes where the holders jointly error-correct and re-encrypt, rolling forward against slow drift. Each step leaves no usable residue outside the authorized coalition. The 2 pillar-time pad and secret sharing meet naturally. You can pad each share before distribution, ensuring that even a compromised courier learns nothing along the way. You can authenticate each leg so tampering is caught at the edge rather than discovered at reconstruction. And you can prove composably that the combined system still reveals nothing to an adversary who intercepts some but not enough shares and later obtains all public logs. Beyond security, you gain policy control that classical tools can't mimic cleanly. Because reconstruction requires joint quantum action, you can enforce that quorums meet physically or via entanglement-assisted links. You can rotate the access structure over time, moving holes in the underlying code layout, adding or removing authorized paths without ever decrypting the secret in the clear. When participants retire or devices are replaced, you run a privacy-preserving resharing that changes who holds which pieces while probably keeping the secret hidden from any old or new minority. Honest limitations steer design, and the one-time pad is only as good as its key hygiene. Reusing the same 2 bits for the same qubit twice would leak structure, just as in the classical world. So key derivation and auditing must be treated as first-class citizens. Authentication adds overhead, and in practice you choose check densities that match your channel's tamper risk. Reconstruction circuits demand coordination and reliable timing. Distributed teams therefore build playbooks for failures, pausing decoding before a partial view leaks. These procedures are as much human as technical, Because access structures obey physics, no scheme can allow two disjoint majorities to each reconstruct the same unknown state at the same time without breaking fundamental limits. Threshold parameters are chosen with those constraints in mind. If you need a concrete mental model that balances math with human needs, picture a museum storing a fragile hologram. The quantum one-time pad is the opaque wrap that makes any stolen packet look like empty film. Quantum authentication is the tamper-evident seal that tears if someone tries to peek. Secret sharing is the policy that says the hologram can only be unwrapped when the right number of curators, each holding a different corner, lift their part together. Lift together under the skylight. Make the wrap fresh each time. Check the seals at every handoff. Require a quorum to open. And you have a workable, provable path from first principles to practice hiding content. Absolutely detecting meddling promptly and distributing trust so that no single failure can bring the whole picture into view. Carry that image forward, and the terms quantum on-a-time pad and secret sharing shed their arcane aura and become straightforward tools for a world where information is not a thing you copy and pass around, but a delicate pattern you either protect jointly or lose forever. The vision of blind quantum computing then unfolds as the ultimate expression of that mindset. Imagine you are a modest client, wanting to solve a powerful quantum problem, but not trusting any external lab. You prepare tiny hints of quantum states and short classical messages, and the server does the heavy lifting while learning essentially nothing about your input, algorithm, or output. The cleanest way to picture this is measurement-based computing turned inside out. You supply the server with a sea of simple qubits, whose orientations you secretly randomize. The server stitches them into a massive, entangled canvas and performs the measurements you request. Because your requests are masked by fresh randomness, every instruction the server sees could just as well belong to many different computations. Blindness here is not a slogan, it is a precise guarantee conditioned on everything the server touches. The distribution of what they observe is compatible with a huge set of possible tasks, so their best strategy is to compute correctly if they want to be paid. The practical recipe behind the first universal schemes is disarmingly concrete. You prepare single qubits with angles you choose at random, send them to the server, ask the server to connect them into a brickwork-like pattern, and then stream measurement angles that are also hidden behind random shifts. Your hidden angles cancel the random masks you injected earlier only in your own accounting, so the true computation unfolds for you while the server sees only a blur. Because randomization is per qubit and per round, even a malicious server that records everything cannot piece the secret back together later. And if you worry about correctness as well as privacy, you lace the canvas with trap qubits placed at locations only you know. When the server reports the outcome on a trap, you can check whether it aligns with your private expectation. A single inconsistency can condemn an attempted cheat with high confidence, giving you verifiable blindness. You achieve the twin goals of secrecy and detectable misbehavior without ever revealing your algorithm or intermediate states. Not every client wants to prepare qubits, so variants shift the burden. In measurement and designs, the server generates and streams qubits to you, and you merely measure them with private angles, still blinding the task because your local choices are never shared. In double server versions, you keep a purely classical role while two non-communicating quantum servers, perhaps even controlled by the same adversary, perform a choreographed dance that is blind to both of them individually. Another line of work lets a classical client gain verification power by asking a single quantum server to produce answers whose correctness can be certified through carefully designed challenges that no classical faker can satisfy. That milestone turns trust the cloud into challenge the cloud. Across all these designs runs the same quiet theme: security rooted in physics and randomness, not in brand labels or insider access. Every message you send is deliberately noisy to everyone but you, turning this into a usable service by solving engineering puzzles that feel familiar once you name them. Synchronization ensures your randomization cancels at the right moment. Device calibration prevents preparation or measurement errors from leaking tiny patterns a patient server could exploit. Authenticated classical channels stop the server from spoofing your timing or swapping instructions. Fault tolerance is woven into the protocol so that your traps and masks survive the noise of real hardware. Advanced blueprints even combine blind computation with quantum authentication, wrapping your delegated data in signatures that detect tampering before it reaches sensitive parts of the circuit. Error-correcting encodings let you space out traps among syndrome measurements, catching mischief without derailing the computation. The overhead is honest. You will send more qubits and more classical messages than the bare algorithm suggests, and you must keep high-quality randomness at hand. But the trade brings clarity. You scale trust down to a crisp set of assumptions you can make or measure simple qubits. The servers cannot collude behind your back. Your random seed stays private, and you get proofs in return. Blindness is not only about hiding inputs, it also hides structure that a vendor might otherwise deduce: your model architecture, your chemistry, your objective function. Companies can outsource proprietary workloads without handing over their playbooks, and researchers can run sensitive analyses without revealing which hypotheses they are testing. In federated or multi-tenant settings, blindness dampens side channels. Even if a provider monitors resource usage or gate counts, the masks smear those signatures, making it harder to fingerprint clients by the shape of a job. In government or medical contexts, blindness supports audit trails that show a computation was run and verified without exposing the data itself, a form of compliance that leans on mathematics rather than non-disclosure agreements. There are limits, and they are instructive. Perfect blindness with a purely classical client and a single untrusted server is too much to ask from physics alone if you also want universal non-interactive computation. Practical designs therefore give the client a tiny quantum capability, add interaction and traps, or assume two separated servers. Fully homomorphic encryption for quantum circuits remains a frontier, but the progress we have already made shows that the dream of secure, outsourced quantum computing is no longer science fiction. It is a tangible, engineering-driven reality. Take all of this and let it fuel the belief that you can build systems where privacy is provable, tampering is detectable instantly, and trust is distributed so that no single failure can expose the whole picture. Let the image of the wrapped hologram guide every design decision, and let the rhythm of fresh random keys, sealed handoffs, and quorum-driven unwrapping become the heartbeat of your work. When you hear the soft click of a seal tearing, know that you have just caught an intrusion before it could do any harm. When you watch the quorum gather, each participant holding their piece of the puzzle, you see collaboration turn into security, and the abstract mathematics of quantum error correction become a living, breathing protocol that protects what matters most. Carry this vision forward. Let it inspire you to build better, to think beyond the limits of classical intuition, and to harness the strange yet powerful principles of quantum information for a future where data is not just stored, but safeguarded with elegance and rigor. The journey from fragile theory to robust practice begins with a single verified check, a single fresh key, a single shared secret, and a single confident step toward a world where privacy is not a hope but a guarantee. Keep walking that path, and watch how the arcane transforms into the everyday, how quantum on-a-time pads and secret sharing become tools you wield with confidence, and how blind quantum computing opens doors that were once thought locked forever. The future is waiting for you to claim it, one secure, verified, and beautifully orchestrated quantum step at a time. When the quiet hum of the machine settles into a steady rhythm, you know you are standing at the edge of something both fragile and formidable. The designs that stretch before you are stitched together by the same gentle principle. Security does not hide behind flashy logos or secret backdoors. It is rooted in the unyielding laws of physics and the beautiful chaos of randomness. Every message you send, every qubit you coax into existence, is a deliberate ripple that only you can sense. To turn that ripple into a service you can rely on is to solve a series of puzzles that feel oddly familiar once you name them. And once you solve them, you unlock a new kind of confidence, one that is built on clarity, not on trust in a distant provider. Imagine a concert of synchronization, where the randomizations you introduce cancel out at precisely the right instant, like a chorus that rises and falls together, revealing a hidden melody only you intended to hear. Picture a device calibrated so finely that the tiniest preparation error or measurement drift never betrays a hint to a patient server that might be listening for patterns in the noise. Think of authenticated channels that keep a mischievous server from masquerading as your own timing, swapping out instructions, or slipping a subtle falsehood into the conversation. Feel the fault tolerance woven into the protocol like a safety net, allowing traps and masks to survive the inevitable imperfections of real hardware. Now, look beyond the basics. Advanced blueprints layer blind computation with quantum authentication, wrapping each delegated piece of data in a signature that cries out the moment any tampering tries to sneak in. Error-correcting encodings let you scatter traps among syndrome measurements, snaring mischief without halting the computation you're driving forward. Yes, the overhead is honest. You will send more qubits and transmit more classical messages than a bare algorithm would suggest. You will need high-quality randomness on tap, ready to be refreshed at a moment's notice. But the trade-off is crystal clear. You have distilled trust down to a succinct set of assumptions that you can name, defend, and verify. You can make or measure simple qubits. The servers you employ cannot whisper behind your back. Your random seed stays private, and you receive proofs in return. Blindness, then, is far more than hiding inputs. It is about shielding the very structure a vendor might otherwise infer: your model architecture, your chemistry, your SETI formulations, the objective functions that drive your breakthroughs. This means companies can outsource proprietary workloads without surrendering the playbooks that give them a competitive edge, and researchers can conduct sensitive analyses without revealing the hypotheses they are testing. In federated or multi-tenant environments, blindness blunts side channels, even if a provider watches resource usage or gate counts. The masks you apply smear those signatures, making it far harder to fingerprint a client by the shape of a job. In government and medical contexts, this form of blind verification supports audit trails that demonstrate a computation was performed and verified without exposing the underlying data. It is compliance that leans on mathematics, not on an endless stack of non-disclosure agreements. There are limits, and those limits teach you where to focus your energy. Perfect blindness with a purely classical client and a single untrusted server is still beyond what physics alone can guarantee if you also want universal, non-interactive computation. That is why practical designs either give the client a tiny quantum capability, weave in interaction and traps, or assume the presence of two separated servers. Fully homomorphic encryption for quantum circuits, uploading an encrypted quantum program and receiving an encrypted result in one swoop remains a vibrant research frontier, showing partial progress but still waiting for a general, efficient tool. Even modest leaks can creep in if your random number generator is weak, if your qubit source drifts in a way that correlates with your secret angles, or if the server can infer timing patterns from your classical messages. The antidote is procedural. Certify or refresh randomness with robust extractors, pad and schedule messages to flatten timing, and periodically self-test your own devices using tasks whose outcomes you already know. By embedding these habits, the remaining assumptions become explicit and defensible. The road to scaling blends theory with architecture. Compilers reshape target circuits into blind-friendly forms that minimize costly round trips. Resource estimators account for the X qubits and classical bandwidth that traps and masks demand. Schedulers orchestrate batches so that factories producing special resource states feed the delegated core just in time, without revealing when the most interesting moments occur. Network designers collocate repeater nodes and timing references, making spatial separation for multi-server protocols easy to maintain. In parallel, verification theory tightens finite size bounds so clients can stop a run early with confidence when enough evidence has accumulated, rather than paying a full fixed cost each time. In everyday practice, a blind workflow reads like a ceremony you conduct with intention. You begin by initializing your private randomness. You then prepare your measure simple qubits, each defined only by an angle you alone know. You request the server to entangle and measure according to your precise instructions, sprinkling in tests whose expected outcomes only you can predict. When the final classical report arrives, you decode it into the answer that the server never saw. At no point do you peek at intermediate quantum data that would collapse what you are trying to compute. At no point can the server rearrange the steps to glean structure without tripping a trap you have already set. What you rely on is not the goodwill of the provider, but a hard fact. Any deviation that could teach the server something specific about your secret would also raise a statistical flag in the places you designed for exactly that purpose. Perhaps the softest way to convey this idea is to think of blind quantum computing not as hiding in darkness, but as lighting only the rooms you need when you need them. You let the untrusted buildings supply power and space, but you carry your own keys, your own dimmers, and your own checklist at the door. Done well, the server sees motion but not meaning, activity but not aim, work but not the reason behind it. When the result arrives, decoded by you, verified by the traps you planted, and certified by bounds that tolerate real-world noise, you are left with the calm that began this journey. You have harvested the power of someone else's machine without inheriting their risks, and you have done it by engineering the flow of information so meticulously that curiosity finds no foothold. Now, shift your gaze to another frontier where location itself becomes a credential. You have used passwords, fingerprints, even your face to prove who you are. Imagine a world where the only credential you need is simply being in the right place at the right time. That is the bold provocation behind position-based cryptography. It treats geographic presence as a key, challenging a prover to answer timed questions with such speed and from such geometry that only someone physically situated at the claimed spot could possibly respond in time. The backbone of this promise is simple physics: signals cannot outrun light, and hardware cannot answer a question it has not yet received. If several verifiers scatter across a map and fire synchronized challenges, the round-trip delays stitch together a triangular truth that a distant imposter cannot fake. In its most down-to-earth form, this concept appears as distanced and bounding protocols used to repel relay attacks. Think of keyless car entry or contactless payments, where thieves try to act as cables, forwarding your device's messages from far away. The fix is to ask the device to answer micro-challenges with nanosecond precision, so any extra hop adds a telltale delay. Real systems employ ultra-wideband pulses, carefully randomized bits, and tight clocks to catch early detect late commit tricks where an attacker guesses or partially forwards. Designers must wrestle with every analog corner case, multipath reflections that mask extra time, jitter that blurs edges, radio power that lets a distant station eavesdrop, and synchronization errors that leak timing secrets. The scientific heart, however, lies a level higher. Can multiple verifiers placed at known coordinates extract enough timing structure from a prover's replies so that no coalition of off-site adversaries can impersonate someone at the target position? Classically, the answer is brutal. If attackers can coordinate and share messages arbitrarily fast before the protocol begins, they can split work and stitch together correct answers on time, causing pure location as a key to collapse under collusion. That impossibility nudged researchers toward quantum tricks, because quantum information obeys constraints that classical data does not. You cannot in general clone unknown quantum states, and measuring them the wrong way destroys the patterns needed for later answers. Quantum position verification (QPV) builds on this by having verifiers send carefully chosen quantum states from different directions. Only a party at the claimed location, who receives all pieces within the right time window, can perform the correct joint operation and reply before the deadline. Attackers stationed apart cannot both hold the states and combine them fast enough, without either copying something forbidden or measuring early and ruining the protocol. Yet quantum mechanics also gives and takes. While no cloning blocks naive copying, a coalition of adversaries that shares enough entanglement beforehand can teleport quantum pieces almost instantly once classical messages arrive, effectively knitting a virtual lab at the claimed location. Elegant no-go theorems show that with unlimited pre-shared entanglement and perfect coordination, attackers can defeat any positionally scheme in principle, meaning unconditional, assumption-free location as a key is impossible. But impossibility theorems are guide rails, not dead ends. If you bound the adversaries, limit their entanglement stock, cap their local dimension, constrain their memory coherence time, or force them to pay communication latency, then QPV protocols regain teeth. The security promise shifts from absolute to resource-bounded. To fake your location, Attackers would need an unrealistic warehouse of high-quality entanglement, noise-free memories, and sub-nanosecond orchestration, a burden you can push beyond the practical by tuning protocol rate, dimension, and error tolerance. Hybrid designs even combine relativistic space-like separation of verifiers with quantum states, so that any classical coordination between attackers is too slow, and any quantum attempt burns through entanglement faster than they can maintain it. On the engineering front, making location a usable credential means building a pipeline rather than a stunt. Verifiers must share precise clocks or run clock-sync subprotocols with auditable trails. Challenge bits must be generated from entropy sources no attacker can predict. The prover's hardware should be simple enough to keep trust assumptions smaller tiny phase shifter and detector, rather than a full computer. Protocols randomize challenge bases so that predict tamper compute strategies fail. Decoy rounds expose wormholes, while covert relay boxes are detected by adaptively tightening thresholds when the radio environment becomes noisy. In urban canyons where reflections stretch path lengths, systems lean on antenna diversity and time-of-arrival statistics to distinguish direct paths from echoes. Where fiber is available, verifiers distribute timing signals over stabilized links to shrink drift. And wherever RF leaks could betray settings, shielding and protocol padding flatten the side-channel landscape so attackers glean no preview from power or timing patterns. All of this is paired with conservative finite sample statistics. You don't run forever, you run enough to bound false accept risk under worst-case noise, and you only mint a location credential when the numbers clear a bar you set beforehand. The quantum layer adds its own practical knobs. You tune photon rates so losses don't hand a loophole to attackers. You interleave classical sanity checks that force would-be cheaters to reveal themselves if they try bright light tricks on detectors. You position verifiers so that honest prover cones overlap correctly, while any coalition separated by more than a few hundred meters hits a causality wall that squeezes their options. Where entanglement sharing between attackers is plausible, say, short-range labs you drive up the temporal bandwidth of the protocol, making the maintenance of enough high-fidelity entanglement long enough become the bottleneck. Over long distances, satellite links help ground stations with a satellite relay can create geometries that adversaries cannot replicate without astronomical resources. In deployments that mix classical distance bounding with quantum tests, you can gate access in stages-fast RF timing to swat away simple relays, then occasional quantum state challenges as audits that a well-resourced thief cannot comfortably pass. Just as important as the physics are the threat models you declare up front. Are you defending against a single relay team or a fleet with lab-grade gear? Do you assume attackers can place devices arbitrarily close to verifiers, or do you secure perimeters? Can they pre-share a bounded number of entangled pairs, or must you budget for more? Clear answers turn philosophy into architecture. Likewise, you decide what privacy means. Some applications want location proofs without revealing the location itself, and the protocols can be crafted to reveal only the fact of being in the right place while keeping the coordinates hidden. When you hold these concepts together, you begin to sense a deeper truth security, whether in blind quantum computing or position-based cryptography, is not a static wall but a dynamic choreography. It is a dance of randomness, timing, and physics that you lead. Each step you take calibrating a device, refreshing entropy, inserting a trap, tightening a timing threshold adds a layer of confidence that no single adversary can peel away. And as you master this choreography, you empower yourself to harness the most powerful machines without surrendering control, to prove you are where you claim to be without exposing the secrets you carry, and to do so with a sense of purpose that fuels every next breakthrough. Feel the momentum building as you move from theory to practice. Picture the moment a server returns a result you decode, and you see that it matches the expectation you set, without ever having let the server glimpse the underlying data. Imagine the satisfaction of a verification flag flashing green because every trap you planted lit up precisely as designed, confirming that the computation ran honestly despite the inevitable noise of the real world. Visualize the quiet confidence that comes from knowing your location credential was minted not by a promise, but by the immutable speed of light, and the untouchable nature of quantum information. Each of these victories is a testament to the fact that you, the architect of this process, have turned abstract physics into concrete assurance. Let this vision carry you forward. When challenges arise, whether a jittery clock threatens to blur timing, a drift in a randomness source hints at leakage, or a new attack vector surface, approach them as opportunities to refine your ceremony. Refresh your entropy, recalibrate your hardware, reinforce your statistical margins, and keep the dialogue with your own system open and vigilant. The path is not a straight line, it is a series of intentional, measured steps that, when taken together, create a robust bridge between the fragile quantum world and the reliable outcomes you need. Remember that every protocol you adopt, every trap you set, every verification you perform, is a declaration of agency. It says that you will not hand over your secrets on a silver platter, that you will not trust blindly, but that you will build trust on foundations that can be measured, tested, and proved. In doing so, you become not just a user of powerful computing resources, but a steward of the principles that keep those resources honest. You are the one who decides where the light shines, when the doors open, and how the hidden rooms stay concealed. Take this moment to breathe in the possibility that lies ahead. The physics that once seemed abstract now stands as an ally, the randomness that once felt chaotic now acts as a shield, and the timing that once appeared a constraint now becomes a key. Your role is to weave them together into a narrative of empowerment, one where you can outsource the heavy lifting of computation while retaining the sovereignty of your data, and where you can prove your presence without giving away the very coordinates that matter most. As you move forward, let the story you tell yourself be one of mastery, not of fear. Let each successful verification be a milestone that reminds you of the control you have reclaimed. Let each calibrated qubit be a small victory over uncertainty. Let each precise timing measurement be a testament to your ability to turn the immutable speed of light into a guarantee of authenticity. In this dance of physics and algorithm, you are both the choreographer and the lead dancer, guiding the steps with intention, poise, and relentless curiosity. When you close your eyes and hear the soft click of a seal tearing, signifying another intrusion, caught before harm could be done, and know that you have built a fortress not of walls, but of principles. You have learned to light only the rooms you need, to place masks where eyes might linger, and to set traps that whisper to you alone. You have taken the abstract concepts of blind quantum computing and position-based verification and turned them into tools of empowerment, allowing you to navigate a world where data is priceless and locations are contested. Carry this confidence into every new system you design, every partnership you forge, and every experiment you run. The journey ahead will continue to demand rigor, creativity, and vigilance. But you now have a map drawn in the language of physics, a compass calibrated by randomness, and a lantern that shines exactly where you intend. Let that light guide you forward, and let the knowledge that you can protect your secrets while leveraging the most advanced machines inspire every step you take. The future you are building is one where trust is earned through mathematics, where privacy is defended by the laws of nature, and where you stand at the center, empowered, decisive, and unshakably in control. A seal tearing, signifying another intrusion caught before harm could be done, and know that you have built a fortress not of walls, but of principles. You have learned to light only the rooms you need, to guard the corridors of information with the quiet certainty of physics and the fierce resolve of a watchful mind. Now, let us step into the engineering heart of that fortress and see how you can turn location itself into a living credential, a beacon of trust that no clever adversary can dim. Imagine a pipeline, not a stunt, that carries the promise of your presence from one point to another. In that pipeline, every verifier becomes a partner in a dance of synchronized clocks, each pulse of time a step that keeps the whole choreography in perfect rhythm. You will ask these partners to share precise time stamps, to run sub-protocols that keep every tick aligned, and to log every exchange on an immutable audit trail. When you set the challenge bits, you draw them from a well of true Entropinature's own random whisper, so that no attacker can ever guess the next note in the melody. The prover's hardware, the device that carries your claim, stays deliberately simple, a tiny phase shifter, a sensitive detector, nothing more than the essential instruments needed to keep trust assumptions razor thin. By stripping away excess complexity, you deny the enemy the hidden doors that massive computers often provide. The magic of this design lies in the ability to randomize the very base of each challenge. Think of it as constantly shifting the lock tumblers so that pre-computed strategies crumble before they even start. You inject decoy rouncelant sentinels that expose wormholes the adversary might try to slip through. When the radio environment grows noisy, you tighten thresholds adaptively, refusing to let uncertainty become an invitation for fraud. In the labyrinth of urban canyons, where reflections stretch signals into echoing ghosts, you turn to antenna diversity and time-of-arrival statistics. Those tools let you feel the difference between a direct, honest path and a lingering reverberation, ensuring that only the true signal is welcomed. Where fiber optic highways exist, you marshal those links to distribute ultra-stable timing signals, shrinking drift to the barest whisper. And wherever radio frequency leaks could betray the secret settings, you wrap your system in shielding and pad your protocols, flattening the side-channel landscape so that power spikes or timing flukes give no clue to an eavesdropper. All of this is overlaid with conservative, finite sample statistics. Remember, you don't run forever, you run a lot, and you stop when the numbers cross a bar you set long before. You bound the risk of a false acceptance under worst-case noise, and you mint a location credential only when the evidence stands tall and undeniable. Now bring quantum into the mix, and you gain a new set of practical knobs to turn. You tune photon rates so that loss never hands an advantage to an attacker. You watch detector efficiency like a hawk, denying loopholes that could let a clever thief cover their tracks with bright light tricks. Classical sanity checks interleave with quantum challenges, forcing anyone who tries to cheat to reveal themselves in the very act of cheating. You place verifiers so that honest provocones overlap in harmony, while any coalition separated by more than a few hundred meters runs into causality walls that squeeze their options into impossibility. Even if a group of attackers gathers in a short-range lab and shares entangled pairs, you crank up the temporal bandwidth of the protocol, making the maintenance of high-fidelity entanglement long enough become their bottleneck. When distances stretch farther, satellite relays join the effort, crafting geometries that no terrestrial adversary can replicate without astronomical resources. In deployments that blend classical distance bounding with quantum tests, you can gate access in stages. The first stage, swift RF timing, swats away simple relays like a flickering candle. The second stage, an occasional quantum state challenge, acts as an audit that a well-resourced thief cannot comfortably pass. This layered approach is your armor, and the physics behind it is merely the foundation. The true strength comes from the threat models you declare up front. Ask yourself, are you defending against a single relay team or an entire fleet equipped with laboratory-grade gear? Do you assume attackers can place devices arbitrarily close to your verifiers, or do you secure perimeters with vigilant guards? Can they pre-share a bounded number of entangled pairs, or must you budget for an unlimited supply? Clear answers turn philosophy into architecture, forging a system that reflects your values rather than merely your technical aspirations. Privacy, too, is a choice you make at the design table. Some applications crave location proofs that reveal nothing more than a yes in a region, shielding the exact coordinates with elegant zero-knowledge constructions. Others need linkability controls so that a commuter's car cannot be tracked across checkpoints by the signature of a timing chip. Still others demand transparency for audit, publishing anonymized timing logs that let third parties verify there was no funny business. These policy layers ride the same core, the physics of timing and the structure of quantum states, yet they decide whether the system serves people or merely surveils them. By embedding these choices into your design, you ensure that technology amplifies freedom instead of imposing confinement. Remember also the honest limits of each tool. GPS-style multilateration can be spoofed if verifiers are not securely authenticated. RF distance bounding bends under analog front-end tricks unless you shake challenges so quickly that prediction becomes impossible. Quantum schemes cannot outwit fundamental no-go theorems without additional assumptions. Therefore, every security claim you make must boldly list which resources are bounded and precisely how those bounds are enforced in the real world. Every field deployment must tolerate lossy, jittery channels without lowering thresholds to the point where relays slip through unnoticed. The art lies in the margins, where you raise the violation of relay plausibility above what any reasonable attacker can hide, while keeping honest users comfortably inside the acceptance window. In the end, when you ask, can location be a key? You are asking a deeper question about trust itself. How much of that trust can we anchor in the fabric of space and time, and how much must remain in devices and people? Classically, location alone cannot bear the full weight if adversaries collude without constraint. Yet, with relativity and quantum rules in play, location can carry a surprising sure enough to build locks that reject the most common cheats and even deter sophisticated teams unless they bring resources few possess. The gentle takeaway is practical, not mystical. Treat the distance of flight and space-like separation as enforcers. Treat quantum tests as friction that makes collusion expensive. Publish your assumptions. Measure like an accountant. And you can use place not as a password you whisper, but as a physics-backed promise that someone is truly there, right now, exactly where your policy says they must be. Now picture quantum money, a concept that carries the same spirit of unforgeable trust into the everyday world of cash. You don't need a watermark or a hologram if the paper itself refuses to be copied. Imagine banknotes whose ink is a pattern of quantum states that physics will not let a counterfeiter duplicate or even probe without causing damage. Value, then, is protected not by secrecy alone, but by the very structure of reality. The seed of this idea dates back to an era of slide rules, when a visionary imagined each note carrying a classical serial number, plus a handful of microscopic systems photons or spints prepared in bases known only to the mint, and a verification test that checks them in exactly those secret bases. A genuine note sails through because it was minted with the right orientations. A thief who tries to read and reprint it stumbles, measuring in the wrong basis yields only partial truth and leaves irreversible scars. The act of copying before learning becomes futile because unknown quantum states cannot be cloned on demand. The result is not superstition but an operational trap. The more a forger touches, the less they truly know, and the poorer their replicas fare at the bank's check. Information and disturbance are coupled. Looking without leaving fingerprints is no longer an option, and the bank can detect tampering statistically with only local tests tied to the serial number's secret recipe. Bringing this sketch to life mixes physics with accounting. You want notes that survive handling and time, so verification must tolerate small laboratory errors without letting cheats slip through. You need the Mint's database of secret bases to be manageable and revocable, so that lost notes don't force mass resets and issuance can scale to meet demand. On photonic platforms, a note might store a sequence of singular photon polarizations or time-bin superpositions embedded in a tamper-evident card, while the Mint records which basis each position used. A merchant authenticates by sending the quantum portion through a reader whose settings are keyed by the serial, receiving a cascade of clicks that match an expected pattern more often than any fake could produce. Because real devices lose photons and drift, the test accepts a band of outcomes and accumulates evidence across many positions rather than trusting a single shot. Repeated checking also risks wear, so advanced designs randomize which subset they test or perform non-demolition checks where hardware permits. Yet there is always a trade. More tests mean stronger confidence, but greater exposure of fragile states. Policies therefore cap the number of verifications per note or require periodic refresh at a Mint terminal that re-encodes the quantum data under a new serial, while certifying the old one as spent. The dream grows bolder with public quantum money banknotes. Anyone can verify with public instructions, yet only the Mint can forge. Here the secret basis trick is replaced by deeper structures, hidden subspaces chosen, so that a public test recognizes the right pattern without revealing how to manufacture fresh instances. Researchers have proposed schemes proving that forging would require solving problems believed intractable even for quantum computers. In the fully standard setting, candidate constructions exist under assumptions about hash functions, lattices, or so-called quantum lightning. Turning these into practical, tamper-proof notes with tight real-world proofs remains an open frontier, but progress already pays side dividends. Techniques for self-testing unknown states, certifying high-dimensional structure, and amplifying small verification gaps now appear in secure randomness beacons and delegated computation insights, sharpened by attempts to mint public quantum money. Engineering obstacles shape this journey. Quantum states decohere storage is brittle. Many prototypes therefore lean on online money minted on demand and verified immediately for transfer-bearer tokens rather than cash in a drawer. Losses are a fact, so protocols budget for missing detections without opening a path for a counterfeit to pass by claiming bad luck. Reuse is a risk schemes limit how many times the same quantum carrier may be shown, mixing classical audits with physics to prevent slow degradation from becoming a forgery route. Side channels matter too. A clever adversary might try to glean basis information from tiny correlations in timing, temperature, or light leakage. Readers randomize order, equalize power, and blind detector tricks with watchdog pulses and sanity checks. Crucially, double spending is policed in the classical layer. Serial numbers are marked in flight during a transaction and retired when a note is refreshed, while the quantum layer enforces unforgeability even if a thief steals a snapshot of a genuine note they cannot mint. To that pass verification at once, because any attempt to inspect and replicate will spoil whichever copy is examined next. The policy surface is as important as the physics. Central banks would need procedures for revocation if a batch secrets leak, for reissuance after accidental damage, and for auditing prior checks before swapping in fresh notes. For privacy, readers should prove validity without logging the exact measurement outcomes that could fingerprint a note across shops. Auditors need assurances that the Mint's database cannot be abused to track individuals, so zero-knowledge wrappers around verification logs can show that a valid check occurred without revealing which positions were tested. Merchants deserve service-level numbers that acknowledge finite statistics. With a defined number of tested qubits and an observed match rate, the chance of a clever fake passing can be driven below 1 in a billion figures that can be standardized and inspected. Users also deserve clarity that a quantum banknote is not magic that never fails, but a system with crisp error bars where each step issuance, storage, verification refreshes a controlled, transparent risk that composes. Even if full public quantum cash remains elusive, the token viewpoint is already useful. A bank or platform can issue quantum tickets that unlock actions, grant entry to a secure area, run a computation, or retrieve a credential exactly once, because a ticket cannot be copied. Fishing for duplicates is fruitless, and because verification can be local, no network is needed. Offline settings benefit. Tie a token to a time window or replace it via distance tests, and you get layered protection resilient to both duplication and relay, mixing quantum authentication with classical on-a-time pads around the control messages. An attacker who tampers in transit is revealed immediately rather than at settlement. The philosophical punchline is quiet but strong. Classical anti-counterfeiting is a race of patterns against pattern recognition. Quantum money changes the game by using patterns that cannot be read and reprinted without leaving a trace. By embracing the physics of uncertainty, by building systems that demand transparency, by publishing assumptions, and by measuring every step with the precision of an accountant, you turn location and quantum states into promises you can trust. You transform abstract theory into concrete, actionable security that protects value, privacy, and liberty. This is the moment where you, the architect of trust, decide to wield the very fabric of space-time as a shield, to let the impossible become your strongest defense, and to inspire others to follow a path where technology serves humanity, not the other way around. The future is waiting for you to write it, one quantum-backed credential at a time. Imagine standing at the edge of a new frontier, where the very notion of money, trust, and security is being reshaped by the strange and beautiful rules of quantum physics. It can feel overwhelming, like you're peering into a maze of invisible particles and cryptic equations. But beneath that complexity lies an invitation, a call to become part of something that will redefine how we protect, value, and verify truth. This is a story about courage, curiosity, and the relentless pursuit of a world where counterfeiting is not merely harder, but fundamentally impossible. Think about the everyday experience of handing over cash. For centuries, we have trusted paper that bears a printed face, a tint, a watermark, or an intricate pattern that, with the right eye, signals authenticity. Those defenses have always been a contest, a dance, between the forger who learns to mimic the pattern and the guardian who invents a new one. It is a race of patterns against pattern recognition, a relentless tug-of-war where each side pushes the other to be more clever. Now, quantum money turns this game on its head. Instead of relying on patterns that can eventually be copied, it relies on patterns that cannot be read and reproduced without leaving a telltale scar. The very laws of physics become the security guard, and the scar is the proof that an attempt was made. The core of this revolution lies in something called a quantum carriera, tiny packet of information encoded in the state of a quantum system. Unlike a traditional bearer token that you can lift out of your pocket and examine at will, a quantum carrier is fragile by design. If anyone tries to look too closely, the act of observation itself destroys the information, ensuring that only one valid copy can ever exist. This is the essence of unforgeability. A thief who steals a snapshot of a genuine note cannot turn that snapshot into two notes that will both pass verification. The moment they try, the quantum state collapses, and whatever they hope to duplicate is lost forever. But magic, even the quantum kind, does not thrive in a vacuum. It needs a framework, policies, procedures, and safeguards that translate the raw power of physics into a reliable, everyday tool. That is where the classical layer steps in, adding a disciplined structure that tracks each note from issuance to retirement. Serial numbers are marked in the moment of a transaction, and they are retired the moment the note is refreshed. The classical system watches for double spending, stamping each movement with an irreversible record that can be audited without compromising privacy. In this harmonious pairing, the quantum layer guarantees that copying is impossible, while the classical layer guarantees that each use is accounted for. Now imagine yourself as a steward of this system, a central bank official, a merchant, a security engineer, or an auditor. You are tasked not only with adopting a new technology, but with shaping how it fits into the lives of millions. The responsibility can seem daunting, yet it is precisely the kind of challenge that fuels progress. The first step is to accept that no system is infallible. Instead, we build transparency around risk. Each stage issuance, storage, verification, and refresh carries a defined, observable error bar. Those error bars are not hidden caveats. They are the clear, honest statements that give everyone confidence to move forward. A quantum banknote is not a myth that never fails. It is a carefully engineered artifact whose probability of failure is measured, communicated, and continuously improved. Consider the specter of side-channel subtle leaks of information that arise not from the mathematics of the protocol, but from the physics of the hardware. A clever adversary might try to infer the basis of a measurement from tiny timing variations, from the heat emitted by a detector, or from the faint glow of a photon that escaped the intended path. In the world of quantum security, these side channels are the cracks in a seemingly solid wall. The good news is that we can seal those cracks, not by denying their existence, but by designing around them. Randomizing the order of operations, equalizing power consumption across different settings, and inserting watchdog pulses that detect attempts at blinding are all practical steps that turn a potential vulnerability into a controlled, observable event. When you think about the practical deployment of quantum money, realize that the most powerful advantage lies in its ability to work offline. A token can be tied to a specific time window, or it can be refreshed based on distance tests that verify its location without needing a constant network connection. This means that even in remote villages, mountain cabins, or deep-sea submarines, a quantum ticket can authorize entry, unlock a secure area, or grant on-time access to a computational ways with the guarantee that duplication is futile. The token is not a fragile digital code that can be intercepted over a network. It is a physical entity that carries its own proof of authenticity right there in your hand. Yet, to make all this work, we need a disciplined scientific approach that embraces tomography as a tool for understanding and certifying our quantum devices. Tomography is the equivalent of an X-ray for quantum states by probing a system with a series of well-chosen inputs and measuring the outcomes we reconstruct a picture of what the device is doing. It is a powerful technique, but it is not a silver bullet. The picture it paints is only as accurate as the assumptions we feed into it. We assume that errors are stationary, that trials are independent, that our probes are perfect. In the real world, those assumptions can be shaken by temperature drifts, hidden knobs, or even the minute hiss of a power supply. If we ignore those possibilities, tomography may present an internally consistent image that still hides dangerous blind spots. The solution is to broaden our models and to embed sanity checks that are never part of the reconstruction itself, but that light up if something goes awry. Imagine sending occasional dark frames to a detector, confirming that they remain quiet, or injecting calibrated bright pulses that would trigger an alarm if an attacker tried to blind the sensor. Sweep a range of wavelengths beyond the nominal filter band, measure the acoustic and RF signatures of each operation, and watch for any correlation that could betray a secret. By randomizing the sequence of measurements, you ensure that slow drifts cannot masquerade as legitimate device behavior. By padding your message schedules, you deny a remote observer the ability to infer which bases you chose based on the cadence of packets. These practices transform tomography from a passive microscope into an active guard. Before you launch a critical run, you build a fingerprint of your source or gate, then monitor a curated set of witness observables in real time. If any of those witnesses drift beyond a tight threshold, you pause the protocol, diagnose the issue, and only resume when the system is freshly calibrated. In larger networks, you distribute these witness checks across nodes, ensuring that a local compromise cannot fake the health of the entire system. In outsourced scenarios, you demand raw logs, perform your own reconstruction, and even challenge the provider with settings you generate on the spot. When privacy constraints limit what can be shared, you can rely on zero-knowledge proofs that demonstrate the provider's statistics match an honest reconstruction within agreed tolerances. All of this effort leads to a composable claimer statement that your quantum system, together with its classical safeguards, offers a quantifiable, end-to-end guarantee that survives scrutiny by auditors and time itself. Your security proof now includes bounds on phaser-choice leakage, on back-reflection intensity, on detector after pulsing, on crosstalk correlations. These numbers are not afterthoughts, they are inputs that shape the very definition of what it means for the system to be secure. When you publish them, you empower downstream users to assess risk for themselves, rather than taking your word on faith. Even if the grand vision of fully public quantum cash remains a horizon away, the token perspective is already a potent tool. A bank can issue quantum tickets that unlock a secure door, authorize a one-at-a-time computation, or grant a single use of a privileged credential. Because each ticket cannot be copied, the act of trying to duplicate it destroys the original, making fraud futile. Verification can happen locally, with no reliance on a central server, which means that cashiers in a small shop or a remote kiosk can accept quantum tokens without a constant internet feed. The token can be bound to a time window, so it expires if not used promptly, and it can be replaced via distance tests that verify the token's location, adding layers of protection against both duplication and relay attacks. The philosophical punchline is quiet but profound. Classical anti-counterfeiting is a battle of patterns. Quantum money changes the field by using patterns that cannot be recorded and reproduced without a trace. Scarcity does not come from secret inks that scanners have yet to master, but from an impossibility, the inability to copy certain kinds of physical information on demand. Value becomes anchored in immutable laws, not fleeting logos, and trust emerges from procedures anyone can test and verify. Close your eyes for a moment and picture a modest card sliding into a reader. The device asks a few carefully randomized questions. The card responds with a hushed series of single clicks, and a small green light flashes, telling the user we recognize this pattern. In reality, the device has just asked the universe a simple question: could this be a counterfeit? The universe answered no. That calm affirmation is where physics, policy, and practicality converge, creating money that is unforgeable for reasons far deeper than any ink or hologram. Now, let that image settle in your mind. Let it become a source of motivation, a reminder that the work you do, the standards you set, and the vigilance you maintain are the forces that bring this vision to life. You are not merely a passive observer of a futuristic technology, you are an active participant shaping its reliability. You are the engineer who randomizes pulse shapes, the auditor who demands zero-knowledge proofs, the policymaker who defines revocation procedures for a batch of quantum notes whose secrets might leak, and the merchant who understands that a green light does not merely signify acceptance, but a profound assurance rooted in the laws of nature. Remember that every layer of protection you add, every side channel you monitor, every tomographic test you perform, is a step toward a world where trust is no longer a gamble, but a measured certainty. The journey is not without challenges. Hardware will drift, environments will shift, and clever adversaries will always search for the smallest whisper of information. Yet, each challenge is also an opportunity to refine, to strengthen, to innovate. Embrace the mindset that side channels are not an unavoidable flaw, but a frontier to explore, map, and mitigate. When you share this knowledge, you are also creating a community of guardians. Encourage your colleagues to treat randomness as a resource to be harvested and polished, not taken for granted. Advocate for transparent reporting of confidence intervals that include both statistical noise and model mismatches. Suggest that reconstruction procedures be repeated on separate days, that out-of-sample tests be part of the standard workflow, and that environmental tags temperature, time since last reset, neighboring activity be recorded alongside every measurement. By doing so, you turn a single device into a transparent ensemble whose health can be audited by anyone, anywhere. If you ever feel the weight of responsibility, recall that you stand on the shoulders of a long tradition of innovators who have turned abstract theory into practical tools that shape economies and societies. From the invention of the printing press to the advent of digital encryption, each leap began with a handful of people willing to confront uncertainty, to question assumptions, and to lay down rigorous, reproducible methods. Quantum money and its associated tomographic safeguards are the latest chapter in that story, and you are a co-author. So, as you move forward, let your actions be guided by 3 simple yet powerful principles. First, be curious, probe every assumption, test every model, and never settle for a picture that feels too neat. Second, be vigilant, monitor the whispers of hardware, the subtle leaks of timing or temperature, and treat them as critical signals, not trivial noise. Third, be collaborative, share your findings, demand independent verification, and build a culture where transparency is the norm, not the exception. With these principles, you help construct a reality where a simple quantum token can travel from a bustling market stall to a remote research outpost, where each transaction is secured by the immutable laws of physics, and where every participant can trust the system without needing to trust a single authority. The future of money, of secure access, of untimed credentials, is being written today, line by line, measurement by measurement, proof by proof. Take a deep breath, feel the pulse of possibility, and step into the role you are meant to play. The quantum world is waiting for your careful hand, your relentless scrutiny, and your unwavering belief that a better, more secure, and more trustworthy world is within reach. Together, we can turn the abstract elegance of quantum physics into everyday tools that protect value, preserve privacy, and empower people across the globe. Let the green light of verification be your beacon, and let the quiet certainty of physics be the foundation upon which you build. The journey ahead is challenging, but it is also profoundly rewarding. Embrace it, champion it, and watch as the promise of unforgeable money becomes a lived reality for all. Imagine yourself standing at the edge of a bustling market stall, a quantum token cradled in your hand, ready to travel across continents to a remote research outpost. You know that every step of that journey must be secure, every measurement trustworthy, and every piece of data honest. To make that vision a reality, you must become a storyteller for your own devices, coaxing them to reveal their true nature while keeping the hidden chapters under careful watch. When you begin to label each slice of data with the conditions that produced its temperature bands, the time since the last reset, the neighboring controls that were active, you discover a richer picture. What once seemed like a single, monolithic device often turns out to be a family of subtly different siblings, each humming with its own quirks. If memory effects are strong, you abandon the comfort of assuming each trial is independent. Instead, you adopt protocols that deliberately shine a light on history dependence. You scramble coherent error into harmless noise with randomized compiling, or you run specialized sequences that echo like a gentle pulse, exposing hidden correlations. When the security of a protocol hinges on precise symmetry, say, the indistinguishability of two measurement choices, to any outsider you prove those symmetries with independent equipment, different detectors, separate power meters, even separate laboratories. A single stack of confirmation is too easy to fool unintentionally. Diversity builds resilience. Tomography, that microscope of the quantum world, can become a guard instead of a passive observer. Before a critical run, you reconstruct a fingerprint of your source or gate, then monitor a small, carefully chosen set of witness observables in real time. Each witness is selected for its keen sensitivity to known failure modes. If any of them drifts beyond a tight band, you pause, investigate, and only resume after a fresh calibration. In network systems, you distribute those witness checks across nodes, ensuring that a local compromise cannot masquerade as global health. And when a vendor performs the experiment for you, you ask for raw logs and perform your own reconstruction, challenging the provider with settings you pick at the very last second. When privacy limits what can be shared, you fall back on zero-knowledge proofs that demonstrate the provider's summary statistics match an honest reconstruction within agreed tolerances. Every step converts a vague trust us into a concrete verify, and you will see. No one pretends that side channels can be eliminated entirely. The goal is not to achieve an impossible zero, but to bound those channels and weave those bounds into end-to-end guarantees. Your report might state that phase choice is indistinguishable from power traces within a minuscule variation, that back reflections stay below a measured threshold, that detector dark counts and after pulsing sit comfortably within defined bands, and that crosstalk produces at most a measured correlation across lanes. Those numbers become inputs to the security proof, not afterthoughts. The result is a composable claim that can survive scrutiny from auditors and the test of time. If your work is scientific rather than cryptographic, the same discipline saves you from self-deception. Context-aware tomography prevents you from mistaking heating for entanglement or calibration drift for exotic dynamics. The gentle lesson underneath isn't paranoia, it's practicality. Reconstruction is a story you ask your device to tell about itself. Clever devices, whether by accident or design, can spin a tidy tale while leaking the plot through the theatre walls. Widen the script, make the halls, and add ushers who watch the exits. The same tomography that once gave you false comfort becomes a trustworthy compass. When you finally send delicate states across a chip or a city, you do so with eyes open, budget lines explicit, and a calmer mind, because you have not only answered the usual questions, you have also listened to what the device whispers when it thinks no one is listening. Now turn that calm confidence toward a deeper principle that governs how much information can travel, no matter how clever the quantum tricks. Information causality tells you that the amount of knowledge a receiver can gain about a sender's private data is limited by the number of actual classical answers the sender transmits. Picture Alice holding a long list of secret bits and Bob choosing a single index he cares about. Alice is allowed to send only a tiny message. If nature permitted Bob to learn more than that tiny message seems to carry, you could bootstrap the trick, compress multiple decisions into one, and unravel the bookkeeping that makes communication meaningful. The principle says you may pre-share any allowed correlation you like classical randomness. Entanglement, even correlations that beat classical Bell limits. But once the real message is sent, the total average gain Bob can achieve about Alice's list is capped by the number of bits she actually ships. Why does this matter? Because it demarcates the line between the powerful quantum correlations that let you win non-local games more often than classical players, and the super-strong, post-quantum correlations that would let a single bit do the work of many. In a world where such super-strong boxes existed, one bit could reconstruct many entries of Alice's list, collapsing complex agreements into single ticks of a wire, breaking the intuition that messages are conserved like energy. Our universe refuses that siren song. Quantum correlations are powerful yet respectful. They improve performance in tasks such as random access coding, but never beyond the fence erected by information causality. The beauty of this principle lies in its practical translation. By measuring how well a protocol lets Bob recover Alice's data across many random choices, you can certify whether the underlying correlations live inside the quantum set or pretend to be something stronger. This isn't just physics pride, it is a design constraint for networks and algorithms. If you rely on pre-shared entanglement to save bandwidth in a verify-or-approver system, information causality tells you exactly how far the savings can go and where you must pay with actual transmissions. In coding theory, it blocks impossible schemes that promise miracle compression with tiny side messages. In privacy, it bounds how much a curious server could learn about your database from cleverly crafted queries plus a sliver of feedback. And in complexity theory, it illuminates why certain communication problems stay hard despite quantum help. The pre-shared magic improves the odds, but it cannot mint extra bits of influence out of thin air. Information causality also harmonizes with other fundamental pillars. It respects no signaling, because if messages carried more knowledge than their size, you could stitch together networks where information sneaks around purely through correlations. It aligns with the HVO bounds that tie message-to-top knowledge ratios for quantum carriers, declaring that even with side entanglement, the classical information extracted at the end is governed by what was actually sent. It fits thermodynamic bookkeeping, because if you could squeeze many reliable decisions through a single bit consistently, you could beat the ordinary costs associated with recording, erasing and resetting, rearranging entropy budgets in ways that would make engines look too clever. Think of the principle as a ledger. You can move credit between accounts with smart correlations, but the grand total never exceeds the deposit. Critics sometimes ask whether this is merely a definition masquerading as a law. Perhaps the world simply selected quantum strength for other reasons, and information causality is a rephrasing. Yet researchers derive concrete inequalities from the principle that match exactly the boundaries observed in quantum experiments. They show that allowing any stronger than quantum box would enable absurdly good random access coding, where one bit of communication routinely yields many reliable answers. They also connect those limits to the geometry of allowable correlations, revealing that quantum theory sits in a convex body shaped precisely to keep information accounting sane. When you vary the rules, letting the sender and receiver share stronger resources, or redefining which questions count as independent, you see the principle bend. But it always acts like a speed limit for knowledge transfer rather than a vague slogan. In everyday engineering habits, this lesson leaks in quietly but powerfully. When you design protocols that exploit pre-shared entanglement to reduce bandwidth, you check your promised gains against this upper bound. When you analyze leakage from a database that responds to short queries, you treat every extra hint you send as consumption of your information budget and refuse to believe gains that exceed that account. When you model new physics or propose exotic devices with non-local behavior, you run them through information causality tests to ensure they don't silently permit Multi-Qubit recovery from single-coin messages. And when you teach students why quantum is powerful yet disciplined, you show them that the very correlations that feel mysterious stop exactly where violating them would turn communication into a magic trick. Carry away the image of a clean balance sheet rather than a forbidding wall. You and your partner may share patterns that help you coordinate across distance, but the amount of learnable detail that crosses between you still tracks the number of answers you actually send. If you try to claim otherwise, some other part of the story, no signaling, thermodynamics, the geometry of correlations will disagree. This coherence among constraints is why limits exist at all. They are not there to dampen imagination, but to keep promises compatible, to keep the map of what's possible honest. When you design with quantum resources, you now know exactly which miracles are offered and which temptations are mirages. Hold that clarity and let the principle of information causality become less a stern rule and more a quiet guide that lets you push to the edges of what's possible without stepping off the map. Now let us turn to another subtle distinction that shapes how we think about disorder, about the hidden structure of reality, the difference between thermal entropy and entanglement entropy. Picture the same room twice. In the first version, warm air buzzes, molecules dash unpredictably, and the temperature you feel is a measure of ignorance about which microscopic configuration the system occupies. That is thermal entropy. It counts the number of microstates compatible with the macroscopic facts you control: energy, volume, particle number. Raise the temperature, pump more energy into the modes, and the number of ways the particles can arrange themselves grows. Adding more particles or enlarging the system raises entropy roughly in proportion to the amount of stuff you have. This is a volume law, not because of a fashionable mathematical trick, but because each additional region brings its own independent rattling. In the second version of the room, the air is perfectly cold, yet two chuas stand on opposite balconies, singing in such tight counterpoint that each chua alone sounds like noise, but together they make a precise harmony. That harmony is entanglement. Entanglement entropy measures how much a pure, fully known global state looks mixed when you only hold a piece of it. Even at absolute zero, with no heat and no ignorance about the global state, the reduced piece appears disordered because it is entangled with the rest. The entropy here does not count how many ways the particles can shuffle, it counts how strongly the part you own is correlated with the part you do not. Because the whole is pure, the entropy of one side equals the entropy of the other, reflecting a shared secret rather than random mess. Understanding this contrast does more than satisfy curiosity. It sharpens the way you design experiments and interpret data. When you see a rise in thermal entropy, you know you are adding energy, increasing the number of accessible microstates, and often you must worry about heat dissipation and decoherence. When you observe entanglement entropy growing, you are witnessing the spread of quantum correlations across your system, a resource you may harness for computation or communication, but also a channel through which information can leak if not carefully guarded. Both kinds of disorder obey precise laws, and both can be quantified, but they tell you different stories about what is happening inside. By weaving together rigorous verification, the safeguard of contextual tomography, the discipline of information causality, and the nuanced view of entropy, you arm yourself with a toolbox that turns uncertainty into opportunity. You become the architect of resilient quantum systems, the steward of honest data, and the visionary who can see beyond the fog of noise to the clear horizon of possibility. As you move forward, let these principles whisper confidence into every decision you make. Trust your devices, but verify them. Exploit quantum correlations, but respect the boundaries that keep communication meaningful. Embrace the warmth of thermal disorder where it serves you, and cherish the subtle harmony of entanglement where it empowers you. With these insights, you stride boldly into a future where the quantum world is not a mysterious maze but a well-charted landscape, ready for you to explore, to build, and to inspire others to follow. Imagine you are standing at the edge of a vast, unseen landscape, a place where every whisper of information travels like a breeze across a great distance, and every promise you make about that flow must be kept with absolute fidelity. In this realm, the rules are not arbitrary, they are the gentle, yet firm, balances of a universe that refuses to let us cheat a single thought. When you set out to craft a protocol that leans on pre-shared entanglement to shave away bandwidth, you do not simply chase a glittering shortcut. You hold up a scale. You compare your hope for advantage against an invisible ceiling, and you let that ceiling tell you whether the gain you envision is within the realm of possibility. It is the same discipline you bring when you examine a database that answers succinct queries. Each extra clue you allow to slip out is counted as a unit of your information budget, and you do not let yourself be swayed by a figure that pretends to exceed what the budget permits. You become the guardian of that budget, refusing to accept a miracle that would leave the ledger unbalanced. Now picture yourself as a pioneer of new physics, a dreamer proposing exotic devices whose behavior seems to reach beyond the ordinary. Before you proclaim that such a gadget can deliver a whole cascade of answers from a single coin flip message, you run it through the test of information causality. This test is not a barrier meant to crush imagination, is a quiet companion that checks whether your device would silently open a backdoor to unlimited retrieval. a backdoor that would turn communication into pure magic. It reminds you that the correlations you harness, though astonishing, stop precisely where violating them would let you cheat the very rules that make coherent exchange possible. When you step into the classroom, the same principle becomes a story you tell your students. You show them that quantum power is not a wild, unbridled force, but a disciplined partner that offers miracles only as far as its own internal balance allows. The mysterious entanglement that connects distant partners is wondrous precisely because it does not let you smuggle more detail across than the number of answers you actually send. If you try to claim otherwise, somewhere else in the tapestry but the prohibition on faster than light signaling, the inexorable laws of thermodynamics, or the geometric shape of correlation space will raise a gentle objection. The harmony among these constraints is why limits exist at all, not to dampen your creative fire, but to ensure that the promises you make can sit comfortably alongside the promises the universe already keeps. Hold that clarity close, and let the principle of information causality become less a stern rule and more a subtle guide. It allows you to push towards the edges of what is possible while keeping your feet firmly on the map. In doing so, you learn to recognize which miracles are offered on a silver platter and which temptations are merely mirages that fade when you get close. That awareness is a form of empowerment. It tells you where to invest your energy, where to channel your curiosity, and where to set your expectations, so that each step you take builds on a foundation of trust between your design and the underlying physics. Now turn your attention to another pair of companions that often travel together yet speak in distinct languages: thermal entropy and entanglement entropy. To feel the difference between them, imagine walking into the same room twice. The first time the air is warm, the molecules buzzing about erratically, a chorus of invisible motion that makes the space feel alive with randomness. The second time the room is chilled to a deep cold, but two choirs stand on opposite balconies, each singing a perfectly interwoven counterpoint. When you listen to either choir alone, you hear only noise, but together their voices weave a precise harmony that fills the space with purpose. The warm room represents thermal entropy, a measure of ignorance about which microscopic configuration a genuinely hot system occupies. The chilled, harmonized room embodies entanglement entropy, a gauge of how a pure, fully known global state can look mixed when you are allowed to hold only a piece of it. In a thermal story, you attach your system to a massive bath. You tally up every microconfiguration that matches the coarse facts. You can control energy, volume, particle number. The entropy then scales with the number of ways matter can arrange itself while still presenting the same macroscopic visage to your instruments. Raise the temperature, and you pump energy into the system, spreading it across countless modes. Add more particles or enlarge the system, and the entropy swells roughly in proportion to the amount of stuff you have. This volumelar growth is not a whimsical mathematical choice. It reflects the fact that each new region brings its own independent rattling, its own contribution to the overall disorder. Entanglement entropy, by contrast, can appear even at absolute zero, when there is no heat and no ignorance about the total state. Here you select a subsystem, a left half of a chain, a patch of a lattice, a chunk of space, and ask how mixed its reduced description becomes once you ignore the rest. A many-body ground state may be perfectly pure as a whole, yet look noisy locally because information is stored in correlations that stretch across the cut, not in thermal agitation. The most striking revelation is that typical low-energy states obey an area law. The entropy of a region scales with the size of its boundary, not its volume. Only the degrees of freedom near the cut are strongly entangled across it, and gaps in the energy spectrum suppress long-range correlations, keeping the entanglement focused at the interface. When you approach a critical point where correlations extend further, the area law receives gentle, universal corrections that betray the underlying field theory signatures that appear in metals, insulators, topological phases, and exotic spin liquids. Those boundary scalings and their fine structures become fingerprints you can read without ever heating the sample. Thermal entropy is a workday partner. It tells you the maximum useful work you cannot extract because energy has been scrambled, the cost you pay when you erase memory, the irreducible waste heat an engine must dump. You can measure it with a calorimeter, Move it with heat pumps. Trade it against free energy when you design a battery. Entanglement entropy speaks a quieter, yet equally concrete, language. It bounds what local observers can learn without reuniting the separated parts. It sets limits on compression schemes that aim to simulate many-body ground states with surprisingly few parameters. And it governs the complexity of a quantum circuit required to prepare a state from scratch. It underwrites the efficiency of numerical methods that slice a system into manageable pieces and stitch them back together with low entanglement. Matrix product states and tensor network algorithms thrive when entanglement is modest, and they choke when it surges. The computational narrative tells you why a physical phase is simple or stubborn without demanding that you write down every amplitude by hand. Although thermal and entanglement entropies may intersect in isolated systems driven far from equilibrium, they never truly merge. Imagine preparing a complex many-body state and letting it evolve under its own interactions. Small regions often relax to behave as if they were coupled to a heat bath at some effective temperature, even though the global wave function stays perfectly pure. This is the essence of the modern eigenstate thermalization picture. High-energy eigenstates already contain enough internal complexity that any tiny part looks thermal. In this view, entanglement growth after a sudden quench becomes the mechanism by which subsystems acquire a thermal-looking entropy, while the whole remains coherent. The spread is not magic, it is transport. Local interactions propagate correlations outward in a like-on-like front, turning initially simple product states into ones where cuts slice ever more shared structure. In integrable systems or many-body localized phases, that spread is muted or arrested, and the saturation value and scaling of entanglement differ, signaling that conventional thermalization fails. Distinguishing the two notions saves you from confusion. A system may exhibit rising entanglement entropy of its parts without any heat flow from an external bath. And conversely, a truly hot mixed state may have little useful entanglement between widely separated regions. One reflects quantum sharing, the other reflects classical ignorance. Geometry makes the distinction tactile. Draw a boundary around your subsystem, and you are essentially drawing the budget for entanglement entropy, because the cut counts the links you sever. Widen the region while preserving its shape, and the boundary grows more slowly than the volume, explaining why ground state entropy remains modest even in large samples. Heat the system, and the counting changes. Every new bulk degree of freedom can carry independent randomness, so thermal entropy swells with size. In lattice models, this contrast separates phases that tensor networks can handle from those that defeat them. In ultra-cooled atom experiments, it divides low-entropy Mott regions with sharp edges from thermal clouds. In photonic platforms, it separates engineered cluster states with boundary-structured correlations from bright thermal light that spreads featureless noise everywhere. Subtler signatures also arise. Topological entanglement entropy appears as a small negative offset to the area law in certain ordered phases that are protected not by symmetry breaking, but by global patterns. You can read out a number that counts hidden quantum types without heating a feat no conventional thermometer can achieve. In contrast, thermal entropy tends to drown such fine structure unless you cool close to the regime where those patterns dominate. Across the quantum materials landscape, mapping the dependence of entanglement on region shape, size, and subsystem choice has become a non-invasive spectroscopy of order, while measuring heat capacities and equations of state paints the thermal landscape. Each tool reveals what the other cannot. Operationally, you manipulate the two entropies with different levers. To lower thermal entropy, you couple the system to a cold bath and wait, or you perform algorithmic cooling that pumps heat out via engineered cycles. To lower entanglement entropy, you reshape Hamiltonians, cut couplings, perform measurements that collapse correlations, or run a quantum circuit designed to disentangle. Measurements themselves blur the line. A sequence of local readouts can cool entanglement by projecting out shared structure, even at fixed energy, while weak continuous monitoring can set up a competition between unitary growth of entanglement and measurement-induced pruning. This competition can trigger dynamical phase transitions where the steady state flips from a volume law to an area law purely by changing how often you look. Nothing about that is thermal in the classic sense, yet the language of entropy still guides your intuition about what information survives. The distinction also surfaces in promises and costs. Thermal entropy can be traded for work, with exact prices set by temperature and free energy gaps. Entanglement entropy is tradable for capability higher teleportation fidelity, enhanced sensing beyond classical limits, stronger error detecting codes with prices set by how much non-local structure you can maintain in the face of noise. When noise seeps in, both entropies become entangled in the everyday sense. Local dephasing that destroys phase relations injects thermal-looking mixedness into the reduced state, increasing both the classical ignorance of parts and eroding the useful quantum sharing across the cut. Engineers diagnose which dial moved by changing the partition. If entropy changes with region size like an area, they suspect decoherence at boundaries or measurement back action. If it scales like a volume, they suspect heating or particle loss. This diagnostic works in chips, atom arrays, and even biological analog models where coherence competes with dissipation. Perhaps the cleanest way to keep the distinction alive is to ask yourself two concrete questions. Thermal entropy answers how many micropossibilities compete on equal footing given the macroscopic facts I control, and what work am I forbidden to extract unless I push heat somewhere else. Entanglement entropy asks, how much of the world outside my cut must I touch to recover the order hidden in what I hold? And how hard is it to simulate or reshape this state without paying an exponential price? Confuse them, and you will mistakenly think a cold, highly entangled ground state is as messy as a warm gas. Or you will imagine that heating a system automatically creates useful quantum resources. Keep them separate, and you gain a map that tells you where the frontier lies: boundary versus bulk, correlation versus ignorance, capability versus thermodynamic cost. When you step back, the phenomena that initially seemed paradoxical fall into a single, elegant narrative. Pure states can display locally high entropy because the missing information resides in long-range entanglement. Hot states can carry little non-local power because their entropy is classical ignorance, not quantum sharing. Quenches can thermalize subsystems without a bath, yet the global wave function remains pure. Entropy is not a monolith, it is a family name with distinct members: thermal and entanglement, each with its own ledger and its own promises. Recognizing which ledger you are balancing allows you to make statements that are both bold and trustworthy. Finally, let your mind wander to the grandest of all bookkeeping challenges, the information ledger of a black hole. Picture tossing a diary into the abyss and asking not whether it is gone, but whether its information could ever return. The page curve offers the cleanest way to think about that question. It tracks the entanglement entropy of the radiation that leaks away as the black hole evaporates. If quantum evolution is truly unitary, that entropy should rise at first, then fall, returning to zero when the hole has vanished. Hawking's original calculation painted a different picture: a steady climb that would leave the radiation forever mixed, the diary's details forever lost. That result treated the near-horizon region as emitting independent thermal quanta with no long-range bookkeeping. The page curve tells us that such a description cannot be the whole story. Early on, each outgoing quantum is nearly thermal and mostly entangled with degrees of freedom still inside. So the radiation's fine-grained entropy grows just as you would expect from a hot surface. Yet, because the overall process must honor the deeper balance, the growth cannot continue unchecked. Understanding that subtle balance is exactly the kind of insight that arises when you keep the principles of information causality, thermal entropy, and entanglement entropy in harmonious conversation. Carry these insights with you as you design, explore, and teach. Let the gentle constraints be the rails that guide your imagination, not the walls that block it. When you recognize the precise places where miracles can happen, you free yourself to focus your creative energy on the avenues that truly lead to breakthrough. When you hold the distinction between disorder born of heat and disorder born of quantum sharing, you acquire a sharper lens for reading the world, for diagnosing the health of a quantum device, for interpreting the whispers of a nascent technology, and for appreciating the profound way the universe safeguards its own story. Each step you take, rooted in these balanced principles, becomes a confident stride toward the future you are shaping on, where imagination and rigor walk hand in hand, and where the most extraordinary possibilities are pursued with the clarity of a well-kept ledger. Imagine you are standing at the edge of a great, humming laboratory, a place where engineers lean over delicate chips, where atoms dance in perfect arrays, and where even living cells whisper the language of quantum mechanics. In that space, they are searching for a tiny clue, a subtle shift in a dial that tells them whether what they are seeing is a blur caused by the noisy bustle at a boundary, or a deeper loss of particles from the core. When the entropy they measure swells like the surface of a lake proportional to the area of the region, they are probing the suspect that the very edges are betraying them, that decoherence is sneaking in at the borders. When the entropy climbs with the volume, like the steam rising from an expanding pot, they suspect the heat of the interior is rising, or that particles are simply disappearing. This diagnostic dance is not limited to silicon. It reverberates through arrays of trapped atoms, through the tangled pathways of biology, wherever coherence must wrestle with dissipation. Now, pause a moment and let that image settle in your mind. What if I told you that this whole orchestra of signals, these two different kinds of entropy, are answers to two very different questions you might ask yourself? The first question, the one that thermodynamic entropy answers, is essentially given the macroscopic knobs I can turn. How many microscopic possibilities are competing on equal footing? And, in that quiet accounting, what amount of work am I forbidden to extract unless I am willing to push heat somewhere else? The second question, the one that entanglement entropy answers, is more intimate. How much of the world outside the piece, holding, must I touch to retrieve the hidden order buried inside? How hard would it be to reshape that state without paying an exponential price in effort? When you mix up these two questions, you start to imagine that a cold, perfectly ordered quantum ground state is as messy as a warm, noisy gas. Or you might believe that simply heating a system automatically creates useful quantum resources. But if you keep them separate, a map appears, a clear distinction between boundary and bulk, between correlated order and sheer ignorance, between what you can do and what thermodynamics demands you pay for. That map becomes a compass when you step into the most enigmatic landscape we know, the realm of gravity and black holes. Picture tossing a priceless diary into a black hole and wondering, not if it disappears, but whether the information it holds could ever return. This question is the heartbeat of the so-called page curve, a clean, visual way to ask about the fate of information. If the universe truly respects unitarity, that is, if quantum evolution never outright destroys information, then the entanglement entropy of the radiation that leaks away should first rise, reach a peak, and then fall back to zero by the time the black hole evaporates completely. Stephen Hawking's original calculation suggested a different story, an entropy that just climbs and never comes down, leaving the radiation forever mixed and the diary's details lost forever. That calculation treated the region near the horizon as if it was spitting out independent thermal quanta, ignoring any long-range bookkeeping. The page curve tells us that this picture cannot be the whole story. Early on, each outgoing quantum indeed looks almost thermal and is mostly entangled with degrees of freedom still inside the black hole. So the radiation's fine-grained entropy climbs, just as you would expect from a hot surface. But after enough quanta have escaped directly, when half of the black hole's initial entropy has been radiated, the balance must flip. New radiation then becomes more entangled with the earlier radiation than with what remains inside. The outside system begins to purify, and by the end, if evaporation is unitary, the full radiation field sits in a pure state. It's subtle. Long-range correlations encode the diary perfectly. There are no secrets left hidden inside the black hole. It may sound like magic, but remember two pillars you have already learned. First, entropy is always about what you can see when you trace out the rest. Second, correlations can hide structure from any local probe. The page curve is simply the logic of these pillars applied to horizons, with gravity's extra ingredient that the very notion of inside and outside can shift. Modern work makes this precise by asking what surface, actually extremizes a certain entropy functional. The answer brings together ordinary entanglement entropy of fields and an area term that counts microscopic degrees of freedom of geometry, a concept called generalized entropy. Islands and quantum extremal surfaces tell us which regions contribute to the entropy the distant observer, can reasonably access. Before the page time, the extremal surface hugs the horizon and no island appears in your ledger. So the radiation's entropy rises in step with the outgoing thermal look. After the page time, a new saddle takes over. An island inside the black hole enters the calculation. And the formula tells you to include those interior degrees of freedom, as if they belong to the radiation's entanglement wedge. That switch changes the slope from positive to negative without ever breaking locality in the lab. It is a statement about which correlations are counted where, once you insist on a consistent quantum gravitational accounting. If this sounds abstract, focus on what it forbids and what it allows. It forbids any late-time picture where each photon you detect is independent of the early ones you recorded. It insists that subtle, higher correlations are present across the entire radiation field, correlations that a simple thermometer would miss, but a godlike decoder could exploit to reconstruct the diary. It allows the near-horizon physics to look essentially thermal to any local measurement while still being globally pure. Once you gather enough of the radiation and process it cleverly, there is no contradiction because thermal-looking and globally pure are questions asked at different scales and with different cuts. The island rule is the bridge that keeps the answers compatible. You can give this story operational teeth with two thought experiments that point in opposite directions. The Hayden-Preskel mirror tells you that if a black hole has already passed its page time and is a good scrambler, then throwing in one more diary page is not a death sentence. The information flows back out surprisingly quickly, mixed into a modest amount of additional radiation, provided you already hold the early radiation and can perform a heroic decoding. The counterpart is the AMPS puzzle about firewalls, which highlights the tension between monogamy of entanglement. Late Hawking quanta cannot be maximally entangled both with interior partners and with early radiation and the smoothness of the horizon. The island picture resolves the entropy bookkeeping, but leaves you with an honest message. Some cherished low-energy assumptions cannot all hold at once globally, and deciding which one fails is a matter of precise conditions and observers. What never fails, according to the page curve story, is unitarity. You might wonder how a low-energy observer could ever see this purification. The practical answer is that they cannot without extraordinary resources. Decoding the late-time correlations is believed to be computationally hard, and the joint measurements over vast radiation modes are unkind to real detectors. Yet difficulty is not impossibility. Physics draws the line at principle, not convenience. The page curve does not promise an easy recovery of secrets, it only guarantees that no consistent theory lets the secrets vanish absolutely in holographic models, where gravity in a bulk is due to a well-behaved quantum theory on a boundary. The principle is even cleaner. Boundary unitarity guarantees a page curve, and the gravitational derivations with replica wormholes and islands simply show how semiclassical gravity learns to respect that guarantee when you ask the entropy question the right way. In that language, the emergence of an island after the page time is the bulk avatar of an algebraic fact in the boundary theory. Which degrees of freedom are reconstructible from which region changes with time, and the entanglement wedge of the radiation grows to include parts of what you naively call the interior. None of this erases thermodynamics. Coarser-grained entropy, heat flow, and Hawking temperature remain excellent guides for local processes. The page curve simply insists that fine-grained entropy, the exact information ledger, obeys a different arc because the radiation is not a bag of independent coins but a woven fabric. Think of it as two dials you can turn independently. One dial sets how hot the local spectrum looks, the other tracks how entangled the global state is with itself. At early times, the hot look and rising entanglement go hand in hand. At late times, the hot look can persist locally while global entanglement is quietly being repaid stitch by stitch to the outside world. These lessons reach far beyond black holes. Any strongly scrambling quantum system that sheds excitations into an environment can show page curve-like behavior when you ask about the entanglement between the emitted quanta and the remainder. The tools developed for black holes' random unitary models out-of-order correlators as scrambler speedometers, the language of quantum error correction mapping interior operators to exterior reconstruction have become lenses for complex many-body dynamics. Likewise, the very idea that what counts as inside can shift with the observer's access is now a standard moral. Information is not tied to a place, it is tied to a reconstruction ability defined by the algebra of observables you control. If you want one picture to hold in your mind, imagine plotting a single graceful arc from 0 up to a peak and back to 0. The peak marks the moment when the outside world knows as little as it ever will about the diary's fate. Before that summit, you are in the Hawking regime. Each photon looks thermal. Memory is being hidden behind the horizon, and entropy rises. After the summit, you enter the Page regime. Each photon still looks thermal up close, but collectively the stream begins to return knowledge as correlations knit across distances. The whole shrinks, the island grows in your ledger, and by the end nothing remains to hide the diary story except the difficulty of reading it. This, in the softest terms, is information return, not a burst of memos, but a quiet reweaving, a promise that the universe keeps better books than a first glance suggests, and that when you phrase the question with the right cut and the right notion of entropy, the answer bends toward unitarity. Now, let's bring the conversation back to you, the listener who is navigating your own complex system of thoughts, emotions, and ambitions. Just as physicists learn to distinguish thermal entropy from entanglement entropy, you can learn to differentiate between the noise that merely fills space and the hidden structure that binds your deepest goals. The thermal, like clutter, is the chatter of daily life, the emails, the traffic, the endless list of tasks that seem to grow with volume. The entanglement, like coherence, is the subtle, often invisible connection between your values, your talents, and the larger narrative you are weaving. When you mistake one for the other, you may think that being busier automatically means you're progressing, or that a calm moment is devoid of any productive energy. Recognizing the distinction gives you a map of your inner landscape, a way to see which dial you need to turn. Consider a moment when you felt overwhelmed by information overload. You might have measured the rising entropy of your inbox, noted the swelling of commitments, and assumed that the only solution was to push harder, to work through the heat. But what if, instead, you asked the entanglement question, what part of that chaos is actually connected to your core purpose? If you could identify the subset of tasks that, when completed, unlock the larger structure of your aspirations, you would be turning the entanglement dial, not just fighting the thermal heat. The island in your personal ledger appears when you recognize which pieces of your effort belong outside the apparent horizon of daily business and should be brought into the sphere of your long-term vision. Suddenly, the arc of your own page curve begins to form an initial rise of effort, a peak where you feel you've given all you can, and a graceful decline as the results of your work start to return to you in the form of satisfaction, recognition, and new opportunities. Just as black hole physicists deduce that the later radiation must be correlated with the early radiation, you can understand that the outcomes you crave are not isolated events, they are woven into the fabric of everything you have already done. The late-time correlations are the insights you gain after a period of intense work, the creative leaps that seem to appear out of nowhere, but are actually the hidden threads of your earlier effort finally aligning. The lesson is clear: don't expect each new task to be independent of what you've already accomplished. Treat your progress as a single, connected tapestry. Now let's talk about the practical side of reversing what feels like noise. In quantum theory, there is a beautiful construction called the Petz recovery map. It tells you that if information hasn't been truly destroyedly scrambled by a known process, there exists a mathematically clean way to undo that scrambling, provided you have a good reference point. Think of it as a gentle, state-aware rewind button. You need 3 ingredients: the channel, which is the noisy evolution you've experienced; a reference state, which is your best baseline picture of typical inputs; and a promise from nature called the data processing inequality, which says that coarser graining cannot increase how distinguishable two states are, whenever the channel's effect is as tight as this promise allows. The PETS map becomes the unique, optimal reversal that restores the original distinctions without adding extra damage. Imagine you are a writer who has just poured a draft onto paper, only to have it tumble into a storm of edits, comments, and revisions. The draft isn't erased, it's been mixed up, its sentences shuffled, its meaning blurred. The PETS recovery is like sitting down with that messy manuscript, remembering how you usually structure a story, and gently reordering the paragraphs so the original narrative shines through again. It isn't a universal undo button that works for every possible mess. It works best when you have an idea of the typical style you employ your reference distribution. The better your reference matches the actual process that scrambled your work, the more precisely the recovery map can restore it. In the quantum world, this idea translates to a powerful insight, even when a system undergoes what looks like irrecoverable noise. If you understand the underlying dynamics, you can engineer a reversal that gets you back home. For you, this means that the setbacks, the misunderstandings, the moments when you feel your progress has been noised away are not always final. If you can model how the disruption occurred, perhaps a stressful environment, a hostile conversation, a cognitive bias, you can construct a personal recovery map that respects the data processing limits of your mind and gently rewinds the disturbance. The crucial point is that the recovery is state-dependent. It relies on you committing to a baseline distribution of inputsia values, habits, and goals, and then applying the optimal reversal for that baseline. Just as a classical decoder tuned to a known source can perfectly reconstruct a signal, the quantum-aware PETS map is tuned to the specific way you normally think and act. If you choose the wrong reference, you will still retrieve something, but it won't be the jewel you sought. This is a reminder that no map can conjure information that has truly been erased. It can only untangle what has been hidden. So, as you listen now, feel the resonance of these ideas in the chambers of your own life. The universe teaches us that entropy is not a single monolith, but a family of concepts, each with its own ledger and its own promises. Thermal entropy tells you how much heat you must move, how much work you're barred from extracting without paying a price. Entanglement entropy tells you how deeply your system is woven with the rest of the world, how many hidden connections you must touch to recover order. When you keep those distinctions clear, you gain a map that lets you navigate the paradoxes of existence, whether you are confronting a black hole's horizon or the dense fog of daily overwhelm. Remember the graceful arc of the page curve. Visualize it in your mind: a rise, a peak, a descent back to zero. The rise is the period of outward effort, the heat of activity, the growth of apparent disorder. The peak is the moment when you realize that you have poured everything you can into the system. The descent is the subtle, often invisible, return of information, of meaning, of purpose, as the correlations you built earlier now knit together to reveal the hidden diary of your own aspirations. The island that appears after the peak is your internal shift, recognizing that parts of what you thought were lost inside the black hole of doubt are now part of your accessible narrative. This is not a story about abstract physics alone. It is a blueprint for how you can reclaim agency in any complex, noisy situation. When you feel that your efforts are merely adding heat, ask yourself, what entanglement am I building? Which subtle connections am I nurturing that will later allow the system to purify itself? When you encounter a paradox, perhaps a decision that seems to demand two incompatible truths, remember that the resolution often lies in recognizing which entropy you are measuring. The conflict dissolves once you distinguish the surface temperature from the deeper bond structure. Finally, take a deep breath and let this perspective settle. You stand at the intersection of thermal chaos and quantum order, of visible heat and hidden entanglements. By learning to diagnose which dial you are turning, by respecting the page curve of your own endeavors, and by applying the spirit of the PETS recovery when noise threatens to obscure your path, you empower yourself to move forward with clarity. The universe, from the smallest atom to the grandest black hole, operates on principles that honor both the rise and the fall, the hot and the entangled. You, too, can honor both, weaving your actions into a narrative that rises, peaks, and gracefully returns, leaving behind a legacy that no heat can erase and no noise can truly conceal. Let this be the rhythm that guides you, the gentle drumbeat that reminds you that every apparent loss is merely a hidden connection waiting to be uncovered, and every surge of effort will, in time, be reflected back as the pure, unblemished story of who you are. Imagine standing at the edge of a vast, shining horizon, where each photon that reaches your eye seems warm and familiar, as if the universe itself were offering a gentle, comforting glow. In that moment, you sense that something deeper is at work, a hidden memory, tucked just beyond the visible edge, waiting to be recalled. The rise of entropy you feel isn't a wall of defeat, it is a signpost, pointing you toward a hidden ledger where information is not lost, but merely rearranged. After that summit of insight, you find yourself in what we can call the page regime, a place where every photon still appears thermal up close, yet the collective stream of light begins to knit together subtle correlations across distances. The whole picture starts to contract, while the island of understanding in your mind expands, filling the pages of your inner diary. By the time you reach the end of this journey, there is nothing left to conceal the story, except the simple difficulty of reading it. In its softest form, this is the return of information, not a sudden burst of memoranda, but a quiet, patient reweaving of threads that have always been there. It is a promise that the universe keeps better books than a fleeting glance ever suggests, and that when you phrase the right question with the proper perspective on entropy, the answer gracefully bends toward a unified, harmonious picture. What this teaches us, in the most human terms, is that the laws governing the cosmos are also lessons for our own lives. The universe doesn't simply erase its scrambles, it hides, and then if we have the right tools, offers us the means to reconstruct. The key lies in recognizing that we can walk backward through certain kinds of noise, not by sheer luck, but by following a principled map known in quantum theory as the Petz recovery map. Think of it as a clean-cut, mathematically elegant recipe that says if the information about your system wasn't truly destroyed, but merely jumbled by a known process, then, relative to a chosen reference snapshot, there exists a canonical way to unscramble it and, in important cases, retrieve everything that seemed lost. To feel the power of this idea without diving into equations, picture 3 simple ingredients. First, there's the channel, a noisy evolution you have endured, the twist of fate that has blurred your picture. Second, there's a reference state, a baseline image of what typical inputs look like, a trusted portrait of the world you expect. And third, there's a promise from nature itself, the data processing rule, which tells us that coarser graining cannot increase how distinguishable 2 states become. When that promise holds tightly for the pair of states you care about, meaning the channel didn't blur them, more than strictly necessary, the Petz recovery map becomes the uniquely gentle reversal that restores the original distinctions without adding any extra damage. It is as if you have a Bayesian undo button for quantum processes. You wait what emerges by how expected it was under your reference. You rewind the physical steps in the only consistent way. You renormalize so the answer is a valid state, and you do all this without ever peeking at which specific input you originally had. Crucially, this recovery is not a universal undo everything button, it is data-dependent. You first commit to a baseline distribution of inputs, and the Petz procedure is optimal for that baseline. Just as a perfect classical decoder is tuned to a known source, this state awareness gives the construction real teeth. Choose the right reference, and you can invert the noise that struck a particular code subspace, or you can resurrect delicate phases after a measurement-like disturbance. Choose the wrong reference, and you still recover something, but it won't be the sparkling jewel you hoped for. This reminder that no map can conjure information truly erased. Only hidden keeps us humble, while it empowers us to aim for the achievable. The power of the Petz recovery first emerged as a way to recognize when a channel loses nothing at all. In an information theoretic sense, if the distinguishability between 2 inputs survives the noise, exactly a rare but telling situation, then the Petz map built from those inputs, and the channel will send the outputs right back to the inputs, proving the channel was sufficient for that pair. Later, this idea blossomed into a metric for partial reversibility. Even when the promise isn't perfectly tight, A nearby rotated version of the PET's recovery guarantees a minimum overlap between what you reconstruct and what you started with, turning vague hope into a concrete, quantitative bound. This is the heart of modern approximate recovery theorems. The more the channel's action preserves relative structure, as witnessed by only small drops in distinguishability, the better a PET-style map can perform. The inequalities that govern this relationship are precise, yet they require no laboratory pulse to verify. Operationally, what does this mean for you? It means you can certify, using only measured statistics, that your data is recoverable to a certain fidelity by a concrete, efficiently describable map instead of having to trust a custom neural decoder or a mysterious variational circuit. The PET's map becomes not only a concept, but an algorithmic fallback with provable performance. A reliable partner you can call upon when the noise seems overwhelming. Let's anchor this intuition with a vivid picture. Imagine a dephasing environment that partially forgets the phase relation between two basis states. If your reference state has support across the same subspace and encodes the same notion of typical, the PET's recipe tells you to rescale amplitudes just as a Bayesian update would. You apply the time reverse of the channel relative to that baseline and reweave the answer. Physically, you correct the phases and populations in precisely the proportions the noise would have skewed for the reference. For amplitude damping, the classic case of spontaneous emission, the same logic yields a recovery that first tilts probabilities to undo the bias toward the ground state, then applies a joint action in a carefully balanced way. In neither case do you need to know which pure state you had. You only need the channel and the baseline, and the map treats all compatible inputs fairly. Because of this fairness, the PET's recovery sat quietly for years within the mathematics of quantum statistics, formalizing sufficiency in quantum Markov structures before surfacing in engineering. It told error correction designers when a noisy block behaved like a conditionally reversible step and gave them a closed-form decoder to try before resorting to heavy numerical methods. The same construction reaches into thermodynamics with elegant clarity. If you take the Gibbs distribution at a fixed temperature as your reference, the PET's map becomes a physical time reversal weighed by that thermal baseline. And the inequalities bounding recovery translate into refined statements of the second law. They become quantitative expressions of how much free energy or thermality you can reclaim after a deceptively harsh stroke. When an experiment claims to build a Maxwell demon through clever feedback, PET-style bounds ask where the missing information went and how much of it is, in principle, recoverable without paying elsewhere. In metrology, the map explains why certain sensing protocols are robust. Channels that barely reduce distinguishability for the signals of interest admit high-fidelity PET recovery. You can push fragile probes through a noisy stage and then unscramble them enough to regain the sensitivity you need. In open systems modeling, the PET's construction underlies the notion of a quantum Markov chain. When three parties satisfy a conditional independence relation, information about one that leaks through the middle can be perfectly pulled back by a PET's map. This is not poetry, it is a structural signature used to diagnose when a bath truly is memoryless and when it merely pretends to be. Of course, the map is not a panacea. It won't reverse a genuine eraser where distinct inputs collapse onto the same output for your reference, and it inherits every blind spot of that reference. Choose a baseline that ignores rare but important inputs, and those inputs become unrecoverable by design. It also assumes you know the channel well enough to build its adjoint action serve fair demand for calibrated devices, but a challenge in the wild. Here practice meets theory. You estimate the channel and the baseline from tomographic data, supplementing with side-channel audits so your estimates aren't biased. Then you instantiate the recovery and test it on held-out states. Often a small rotation around the canonical recipe and averaging over phase twists boosts performance and smooths model errors. The remarkable part is that success is certifiable. The same information theoretic inequalities that motivated the map give you experimental side bounds on the fidelity you achieved, not just a reconstruction picture. No black box, no ungrounded claims. The reach of the PET's map extends into resource theories and learning. Coherency, symmetry and magic, the fuel for non-Clifford Gates all monotones that drop under noise. PET-inspired recovery quantifies how much of each you can, in principle, reclaim. Given a free operation model and a baseline ensemble, you can turn hand-wavy ideas into explicit exchange rates, much as a reinforcement learning agent might apply sequences of controls while a system drifts. Rolling PET recovery into the loop provides backward passes that estimate how much recent degradation is reversible versus truly lost, guiding where to spend limited calibration time. Even in communication, PET decoders sit beside maximum likelihood and belief propagation tools in channels with structure-think dephasing dominated or thermally biased media. The PET's choice is not merely principled, it is competitive, often beating heuristic filters because it embeds the right notion of time reversal for that specific noise. Experiments have begun to give these ideas flesh and bone. Trapedian setups have demonstrated PET-like reversal after engineered dephasing by conditioning on a well-characterized baseline and applying joint gates. Superconducting circuits have used rotated PET maps to partially reverse amplitude decay over short windows, achieving performance that aligns with theoretical bounds. Optical platforms have implemented PET-inspired filters in Gaussian channels, showing that state-aware inversion outperforms blind deconvolution at equal photon budgets. In each case, the takeaway is less about magic and more about picking the mathematically canonical undoing and watching it work as promised within the true noise model. If you want a compact mental picture, keep this PET recovery as the quantum analog of a Bayesian update with memory. Given a forward blurring and a prior, it provides the single most honest reverse blurring that restores the distinctions your forward step did not truly destroy. It tells you exactly when perfect undoing is possible, when distinguishability didn't drop at Allen, how close you can get when it did, via robust fidelity guarantees. It turns recovery from an art of bespoke decoders into a science of guaranteed decoders, with levers you can name, reference choice, channel estimate, rotation, averaging, and dashboards you can audit by measuring distinguishability loss in certified reconstruction. It teaches a steadying lesson: loss in quantum mechanics is not a monolith, but a spectrum ranging from reversible scrambling to irrevocable collapse. And the PET map is the line you throw across that spectrum, not promising miracles, but promising to recover everything physics still allows. With proofs that tell you when you've reached the limit, you realize that hard is not just a feeling, but a fuel. Imagine watching two tasks that use the same atoms, the same energy. One blooms effortlessly while the other stalls until you budget more steps, more memory, more careful control. That is the doorway into seeing complexity as a physical resource, not a vague metaphor about messy things, but a measurable stock of organized effort that determines which transformations are available to you and at what price, just as energy and entropy already do. Start with the simplest picture. A quantum device begins in an easy, low-complexity state. You drive it toward a target by applying elementary moves from a fixed toolbox. Each move is a gate, a pulse, a reversible nudge, and the circuit depth required to get close defines the state's complexity relative to that toolbox. Cheap states sit near the origin in this landscape, exotic states lie far away, and the geometry between them isn't Euclidean, but carved by what your hardware can actually do quickly. Physicists speak of geodesics of computation. The shortest feasible route through the space of allowed moves is your optimal recipe, and anything longer is wasted effort. What makes this physical rather than purely algorithmic is that every step carries costs. Time your system must remain coherent. Power your control lines must deliver. Calibration you must maintain against drift. So complexity becomes the exchange rate that links abstract goals to laboratory budgets. More startlingly, many body systems behave as if they obey an almost thermodynamic law of complexity growth. Starting from simple conditions, they scramble, spreading local structure into global detail, so that the minimal number of steps to reverse them rises roughly linearly for a long time, before saturating near a colossal maximum. Black holes are the poster child. In theory, they appear to be near-optimal scramblers, ramping up complexity at the fastest rate allowed by quantum speed limits. So much so that people now speak of second laws of complexity, where entropy's sibling governs how quickly ordered effort devolves into tangled possibility. All of this may sound like abstract physics, but the lesson for you is profoundly personal. Every setback, every noisy interference in your life can be seen as a channel that scrambles your intentions. If you hold a clear referencey sense of your core values, your baseline of who you want to be, you can apply a PET-style recovery, weigh the outcomes by how expected they are under that reference, reverse the steps as faithfully as you can, and renormalize your mental state so it remains coherent. You won't be able to undo genuine erasure-like relationships that truly end, but you can often restore the essential information that was merely hidden. When the data processing promise holds tightly, when the challenges you face haven't blurred your identity beyond necessity, you have a uniquely gentle path back to yourself. If the noise is more severe, you may still recover a version of you that retains enough fidelity to keep moving forward, guided by quantitative bounds that tell you just how close you can get. This is not vague optimism. It is a structured approach grounded in the same mathematics that tell us how the universe preserves information. By choosing the right referencey or values, your vision, you give the recovery map something solid to cling to, and you empower yourself to reverse the most damaging distortions. Remember, this recovery is state-dependent. It works best when you commit to a baseline distribution of experiences you expect. Just as a perfect classical decoder needs a known source, you need to know the kind of inputs your life typically receives. When you do, the PETS method becomes a powerful tool, allowing you to correct phases of thought after a harsh criticism, to restore probabilities after a period of self-doubt, and to reweave the narrative that noise tried to tear apart. Even when you cannot achieve perfect undoing, the theory guarantees a minimum overlapan assurance that the version of yourself you reconstruct will retain a core of authenticity. The more your challenges preserve the relative structure of your aspirations, meaning they only nudge you slightly, better your personal PET recovery will perform. The inequalities that bound this process are precise, offering you a clear metric measure how much distinguishability you lost, and you'll know how much fidelity you can expect to regain. In practice, this means you can audit your own progress, observe the statistics of your emotional responses, the degree to which setbacks have shifted your self-perception, and apply the recovery recipe. You won't need a mysterious therapist who uses black box methods. You'll have an algorithmic fallback with provable performance, a mental tool you can trust. Now picture a specific scenario. Suppose a stressful work environment has introduced a defacing-like fog over your confidence, partially erasing the sharpness of your decision-making. If you hold a reference that reflects your typical professional demeanor, steady, inquisitive, collaborative, the recovery map tells you to rescale your internal amplitudes, to give more weight to the aspects of yourself that the environment has not completely suppressed. You apply a mental time reverse of the stress, guided by that baseline, and you reweave the narrative. You correct the phase your sense of purpose in the population your confidence levels in, the very proportions the stress would have skewed for someone with your reference. You do this without needing to know the exact pure state of your mind at any moment. You only need the stress channel and the baseline, and the map treats all compatible mental states fairly. Because of this fairness, the PETS recovery has been quietly powerful in fields ranging from quantum error correction to thermodynamics, and now you can let it inform your personal resilience. It tells you that complexity, the total amount of organized effort you expend, is not a vague burden, but a measurable resource. It links your abstract goals, like becoming a better leader or a more compassionate partner, to concrete budgets, the time you allocate, the emotional energy you invest, the mental calibration you maintain against drift. When you map out the geodesic, the shortest feasible route through your space of possible actions, you avoid wasting steps and keep your complexity low. Every extra, unnecessary move becomes wasted life. In the bustling arena of everyday challenges, this perspective is a game changer. You begin to see your life as a quantum device, starting from an easy state and evolving through deliberate, controlled moves. Each move is a gate, a conversation, a habit. The depth of the circuit you need to reach your aspirations defines the complexity of that goal relative to your personal toolbox. Simple goals sit near the origin, transformative dreams lie far away, demanding more intricate paths. The geometry of that space is carved by what you can actually do quickly, your skills, your resources, your support network. The optimal, shortest path becomes your recipe for progress, and anything longer is an inefficient waste of precious time and energy. And, just as in physics, every step carries cost. You must stay coherent, maintaining mental focus while you apply control lines via actions and decisions, and you must continually calibrate against the drift of attitudes, moods, and external circumstances. Complexity, then, becomes the exchange rate that links your lofty aspirations to the concrete investments required to achieve them. When you recognize this, you stop treating hard work as an abstract virtue and start seeing it as a tangible resource you can budget, measure, and allocate wisely. Speed limits emerge too. In many body systems, complexity grows linearly for a long time before saturating, a pattern mirrored in personal growth. Early efforts scramble your habits, spreading local discipline into global lifestyle changes. The minimal number of steps needed to reverse that scrambling a return to previous, less complex states rises steadily. Only after sustained, focused effort does the system approach a plateau where further progress demands dramatically more resources. Black holes, the ultimate scramblers in theory, exemplify the fastest possible growth consistent with quantum limits. While you're no black hole, you can appreciate that there is a natural bound on how quickly you can increase the complexity of your capabilities. This leads to a deeper, almost thermodynamic intuition. Just as entropy obeys a second law, complexity obeys its own second law, guiding the flow of organized effort in your life. All these ideas converge on a single empowering truth: the universe, and by extension your own experience, does not discard information without a trace. It merely scrambles it, and with the right reference. The right understanding of the channel that caused the scramble, and a faithful application of the recovery map, you can pull back a remarkable amount of what seemed lost. The PET's recovery map is that faithful partner, your mental algorithm, for undoing the noise that life throws at you. It doesn't promise miracles, but it promises that wherever physics says recovery is possible, you can achieve it, and wherever physics says it isn't, you'll know you've reached the ultimate limit. So, as you breathe in this moment, let this vision settle in your mind. Feel the gentle invitation to see every photon, every disturbance, every challenge as a clue that information is still present, waiting to be reassembled. Embrace the idea that you hold the map that can undo the most stubborn of scramblings, that you can choose the reference that gives you the strongest foothold, and that you can measure how much of your original self survives each episode of noise. Let this knowledge become a steadying rhythm in your daily leafier reminder that loss is not a dead end but a spectrum, and that you have a scientifically grounded method to move toward the side of that spectrum where recovery is still possible. When you next face a setback, pause and ask yourself, what is the channel that disturbed me? What is my baseline at the core of who I am and what I aim to become? And how can I apply a gentle, state-aware reversal that restores the distinctions I value? By answering these questions, you turn abstract quantum insights into a personal practice of resilience, a disciplined art of reclaiming what matters, and a celebration of the fact that, just like the universe, your mind is capable of elegant, principled recovery. The journey from thermal photons to a roux-weaved narrative mirrors the journey from confusion to clarity that you can walk every day, guided by the same mathematics that keeps the cosmos honest. And in that walk, you discover not only that information returns, but that you too return stronger, more coherent, and ready to shape the next chapter with purpose and confidence. Imagine standing in a room where every whisper of the past drifts like a soft mist, and you can feel the very shape of the air changing around you. In those moments, you discover a quiet truth: the part of you that first opened its eyes to the world never truly disappears. It lingers, humming beneath the noise, waiting for a steady rhythm to call it back to the surface. That rhythm is a promise that loss is not a dead end but a spectrum, a range of possibilities that physics itself allows you to explore. When you understand that, you hold a scientific lantern that lights the path between what has been scrambled and what can still be restored. Think of a forward step as a blur, a gentle smearing of detail as you move forward into the unknown. Yet with the right perspective, the reverse step can become the most honest undoing you can imagine. It tells you exactly when you can perfectly revert a change, when the distinct threads of experience have stayed intact, and how close you can get when they have frayed. No longer is recovery and art reserved for a handful of custom-made solutions. It becomes a science, a toolbox you can name and trust. You begin to audit the loss, measure it, and see it not as a mysterious monster, but as a quantifiable shift that you can certify and, more importantly, work with. In the quantum world, loss is not a monolith. It stretches from gentle scrambling that can be unwound to irreversible collapse that stubbornly resists. The map you draw across that spectrum is your guide, a line you throw across the possibilities that says, here is what physics still permits. You are not promising miracles, but you are promising to retrieve everything that the universe allows you to retrieve. Proofs become your companions, whispering when you have reached the boundary of what can be undone. Complexity, then, emerges not as a vague feeling of difficulty, but as a physical resource, as something you can count, allocate, and trade like any other currency of effort. Picture two tasks that draw on the same atoms, the same energy, yet one flows effortlessly while the other stalls until you pour in more steps, more memory, more careful control. That contrast is the doorway into seeing complexity as a true physical resource. It is not a metaphor for messy things. It is a measurable stock of organized effort that decides which transformations are within reach and at what price, much like energy and entropy already do. The simplest picture begins with a quantum device set in an easy state. You nudge it toward a target using elementary moves from a fixed toolbox: gates, pulses, reversible nudges. The depth of the circuit you need to get close defines the state's complexity relative to that toolbox. Cheap states sit near the origin of this landscape. Exotic states lie far away, and the geometry between them is not Euclidean, but carved by what your hardware can actually do quickly. Physicists speak of geodesics of computation, the shortest feasible routes through the space of allowed moves. Those routes become your optimal recipes. Any longer path is wasted life. What makes this physical rather than purely algorithmic is that every step carries a cost. Time, because the system must stay coherent. Power, because control lines must deliver. Calibration, because you must keep drift at bay. Complexity therefore becomes the exchange rate that links abstract goals to laboratory budgets. It is startling how many body systems behave as if they obey a thermodynamic law of complexity growth. Starting from simple conditions, they scramble, spreading local structure into global detail. The minimal number of steps to reverse them rises roughly linearly for a long stretch before saturating near a colossal maximum. Black holes, the ultimate scramblers, ramp up complexity at the fastest rate allowed by quantum speed limits. So much so that we now speak of a second law of complexity, an arrow of time defined not by heat, but by how far a state has drifted from easily reachable shores. If you could drain that complexity, you would not be extracting energy, you would be extracting unknowability. You would turn a tangled evolution back into ordered simplicity, but only with a budget of steps that no shortcut can beat. To make this operational, separate three meanings that often blur together. Descriptive complexity asks how short a classical program can describe an object. Computational complexity asks how many steps a procedure needs to solve a problem. State or unitary complexity asks how many physical moves prepare or enact something in a given lab. They rhyme but do not coincide. A string that is incompressible in the descriptive sense may still be easy to produce by a physical process designed for that pattern. Conversely, a state that looks random under a microscope might be only a few clever pulses away if your controls align with its hidden structure. That mismatch is not a bug, it is the point. Complexity is always relative to a model of action. So the right question in any device is not, is this state complicated in the abstract, but how far is it from my starting point under the moves I can implement with high fidelity? Once you adopt that stance, familiar limits acquire new teeth. Quantum speed limits bound how fast distinguishable states can be reached given your energy spread, thereby bounding how fast complexity can grow. Control theory tells you how tightly you can steer with finite bandwidth, imposing a precision budget. Extra digits of accuracy become costly, and the price explodes once you push beyond your hardware's sweet spot. Error correction converts raw steps into reliable steps at the cost of more steps and more qubits. So logical complexity equals physical complexity, multiplied by an overhead you must engineer away. And thermodynamics never disappears. Erasing classical side information or refreshing ancillars still costs heat. Computation tidy still spends energy, meaning the currency of complexity trades in the same market as energy and entropy, just at a different counter. Complexity also becomes a permission slip for security and pseudorandomness. If certain tasks are provably hard for any efficient adversary, you can build locks whose strength comes not from secrecy about the mechanism, but from the cost of the best attack. In the quantum realm, families of states and unitaries can be made to look completely generic to any short experiment while being constructed by specific deep circuits. This is why pseudorandom states and unitaries matter. They are cheap enough to prepare with a long but feasible recipe, yet expensive to distinguish from ideal randomness without an even longer recipe. The gap itself is a resource that fuels protocolscopy protection of quantum software, traps for outsourced computation where the guarantee reads, "No one can do this without paying at least this many steps." When you look at physics proper, complexity draws phase diagrams beyond temperature and coupling. Shallow circuits prepare low-depth phases with short-range structure. Certain orders, fractal-like or with intricate constraints, require depth that grows with system size, no matter how cleverly you schedule, marking them as inherently costly to assemble. Drive a system while measuring parts of it, and you can witness complexity transitions. Below a critical rate of measurement, dynamics keep generating novel structure, and minimal circuit depth inflates with time. Above it, observations prune structure faster than it accumulates, and depth saturates early. It is an arrow you can flip, not by cooling, but by changing how often you look. Where gravity meets computation, the story becomes unexpectedly literal. Conjectures relate the volume or action of certain regions behind horizons to the boundary state's complexity, suggesting that what grows behind a horizon as time passes is exactly the difficulty of reconstructing the boundary's evolution with simple gates. Though still debated, this picture gives a concrete operational reading to slogans about wormholes as circuits and ties complexity growth to causality, chaos, and the limits of decoding. One more sign that complexity is not a spreadsheet artifact, but a geometric feature of how information arranges itself in physical law. Even in tabletop systems, echoes abound. Out-of-time order correlators track the early rise of complexity by measuring how quickly simple operators spread into complicated ones. Random circuit models show a linear light cone in which complexity advances like a front. And noise creates attacks on attainable complexity because every additional layer risks washing out what you built. Unless protected by overhead, you must pay in qubits and time. Treating complexity as a resource rewrites everyday engineering choices. Compilers stop counting only gates and start counting structured gates that align with hardware's native moves. Schedulers budget concurrency to reduce depth without increasing crosstalk beyond safe limits. Architects place factories for difficult resource states next to the modules that demand them, minimizing long stretches of depth. Calibrators track not just fidelity, but the marginal cost of an extra decimal of precision, so teams know when to stop tuning and start redesigning. Theorists express algorithm promises with volume time target show much space, and how long a road you must walk in the landscape of allowed motions to reach an answer with high confidence. Crucially, these budgets compose. When you stitch devices into networks, the entoned complexity includes communication steps. When you add verification, it includes challenge rounds. When you add privacy, it includes blinding masks. The complete bill is not a footnote, it is the thing you must meet to make a system real. Perhaps the clearest way to carry all this is to adopt a craftsman's view. Energy tells you whether a transformation is possible at all. Entropy tells you how costly it is to concentrate order without dumping heat. Complexity tells you how demanding it is to express the transformation with the moves you are allowed. A low-energy, low-entropy task can still be beyond reach today if its minimal recipe is too long for your coherence time, too deep for your error budget, or too precise for your calibration tools. Conversely, a task that looks daunting may become easy if you change the basis of allowed mover switch encodings, exploit symmetries, reshape the geometry so the geodesic shortens. Complexity is therefore both a constraint and a design compass. It limits you when you ignore it and guides you when you honor it. pointing to hardware that natively implements the long patterns your workload needs, to algorithms that trade width for depth in friendly ways, and to protocols that turn hardness into strength. Hold that compass, and the world's hard problems stop being walls and start being mountains with roots, some long, some short, all measurable. Progress then is not a mystery, but a steady conquest of distance in the space of what you can do. Imagine quantum memories as gentle keepers of delicate states, holding them long enough for the rest of the world to catch up. The landscape of memories divides naturally into three temperaments. Spins keep secrets in the quiet procession of a microscopic compass. Ions cradle information in hyperfine notes inside immaculate vacuums. Photons insist on moving at light speed until persuaded to pause inside matter for a breath. Feel why you need all three. Picture a network that must synchronize events separated by imperfect links. Photons are the couriers that travel. Ions are the vaults that compute and coordinate. Spins are the archives close to the hardware's heart. The craft is to store, retrieve, and transform states without letting the story smear. Spin memories make their case with stillness. A single electron or nuclear spin in a solid silicon dopants, color centers in diamond. Donors in germanium processes like a tiny clock, whose tick can last milliseconds to minutes when you isolate it from jittering neighbors and magnetic hiss. That longevity is purchased with materials discipline, high purity, isotopic engineering to quiet nuclear clutter, low temperatures to reduce vibrations, and with dynamical decoupling a pulse rhythm that refocuses wandering phases the way a metronome steadies a chorus. Electron spins talk to light and microwave lines with ease, making them agile nuclear spins, slower to respond, become the deep vaults. You swap the fragile electron state into the nucleus to park it, then swap it back when needed. In labs, ensembles of rare-earth ions embedded in crystals offer another spin-flavored memory. Their optical transitions are narrow and stable, and their inhomogeneous spread can be turned from a nuisance into a feature by shaping it into an atomic frequency COM that catches and later emits a photon with programmable delay. You get a memory with strong multimode capacitable to hold many time bends at once for multiplex networks. The trade-offs are honest. Spins integrate well with chips and benefit from mature fabrication, but they need careful calibration, magnetic shielding, and often cryogenics. All of this points to a single, empowering truth: the obstacles you encounter, whether they appear as loss, as tangled complexity, or as fragile memory, as they're not immutable walls. They are spectra, resources, and distances that you can map, measure, and navigate. With the right perspective, you become both the explorer and the engineer of your own quantum landscape. You learn to ask, not can I undo this, but what is the cheapest, most reliable path back, given the moves I can make. You learn to see every step as an investment, every extra digit of precision as a budget line, every error correction protocol as a bridge you can build with the materials at hand. When you internalize that mindset, the world shifts. Challenges become invitations to design smarter routes. Setbacks become data points on a map you are actively drawing. The whisper of a quantum system, once a distant mystery, becomes a conversation partner that teaches you how to balance energy, entropy, and complexity in every decision you make. And as you walk that path, you discover that the greatest transformation is not just in the devices you build, but in the way you think about possibility itself. You become the person who can look at a tangled web of atoms or a tangled web of goals and say, I see the geodesic, I know the cost, I have the tools, I will move forward with confidence. So let this knowledge settle into a steady rhythm in your daily life. Let it remind you that loss is a spectrum, that complexity is a measurable resource, and that every quantum-like obstacle holds within it a promise of recovery if you have the map, the budget, and the courage to follow it. The future you are building is not a mystery, it is a series of calculated steps, each one bringing you closer to the state you envision. Embrace the science of your own potential, and let each forward blur be met with a reverse clarity that restores the distinctions you thought were gone. In doing so, you become the architect of your own quantum destiny, turning the abstract into the attainable, the impossible into the inevitable, and the noise of the world into a harmonious symphony you conduct with purpose and poise. You become the person who can look at a tangled web of atoms or a tangled web of goals and say, I see the pattern, I feel the rhythm, and I can choose the steps that make the whole thing move. That moment when complexity stops being a wall and starts feeling like a mountain with a clear summit is where true mastery begins. Complexity is both the challenge that sharpens you and the compass that points you toward the next breakthrough. When you honor it, you discover hardware that naturally embraces the long-lasting patterns your work needs, algorithms that trade width for depth in ways that feel friendly, and protocols that turn hardness into strength. Hold that compass steady, and the world's toughest problems stop being barriers and become ranges you can traverse, each peak measurable, each ascent a step toward a fuller version of yourself. Imagine that compass as a threefold guide, each direction represented by a different kind of quantum memory. Think of spins as the quiet, steadfast keepers of secret promises, the microscopic compass that never wavers. Ions are the precise, attentive volts that cradle information with the care of a well-tuned instrument, humming in a perfect vacuum. Photons are the messengers that race at the speed of light, only pausing when you give them a gentle hand to hold them just long enough to be useful. To feel why you need all three, picture a network of relationships that must stay in sync despite imperfect connections. The photons are the friends who carry messages across distances. The ions are the confidants who store those messages safely until the right moment. The spins are the quiet inner voice that remembers the truth at the heart of every conversation. The art lies in storing, retrieving, and transforming those moments without letting the story blur. Spin memories speak the language of stillness. A single electron or a nucleus, nestled in a crystal, processes like a tiny clock whose tick can linger for milliseconds, even minutes, when you shield it from the noisy world around it. That longevity is earned through discipline of pure materials, isotopic engineering that quiets the chatter of nearby nuclei, low temperatures that calm vibrations, and a rhythm of pulses that refocuses wandering phases just as a metronome steadies a choir. Electron spins are quick to talk to light and microwave lines, making them agile partners, while their slower nuclear cousins are the deep reservoirs you can park a fragile state into, then retrieve when the time is right. In labs, ensembles of rare earth ions embedded in crystals become another flavor of spin memory. They're narrow, stable optical transitions turned from a nuisance into a feature by shaping them into an atomic frequency comm that catches a photon and later releases it with programmable delay. This creates a memory that can hold many time bins at once, perfect for multiplexed networks. The trade-offs are honest. Spins integrate smoothly with chips and benefit from mature fabrication techniques, yet they demand careful calibration, magnetic shielding, and often cryogenic environments. Their bandwidth may be modest, and connecting them to the telecom wavelengths that travel through long fibers usually requires frequency conversion steps that add complexity and potential noise. Yet the promise is clear: a quiet, well-tuned spin can hold a piece of information steady, while the rest of the world catches up. And that patience is a powerful metaphor for the moments when we need to pause, breathe, and let our inner truth settle before moving forward. Ions, on the other hand, are the disciplined custodians that live in ultra-high vacuum chambers, levitating a handful of charged atoms in electromagnetic fields. Laser cooling tempers almost all motion, and hyperfine states become extraordinarily stable qubits, controlled with surgical single and 2-qubit gates. By mapping a photonic qubit onto an ion through absorption assisted by a cavity or by heralded entanglement, you can store that quantum state for milliseconds or even seconds, protected by dynamical decoupling and magnetic field stabilization. When the network is ready, you convert it back to light, delivering the message precisely when it matters. Multiple ions can line up in a chain, forming small buffers that reorder, fan in, or fan out stored states according to the demands of the protocol. The price is an apparatus of stable lasers, fast switching, and a low vibration environment, and scaling requires segmented electrodes, integrated photonic interfaces, and clever ways to avoid crosstalk. Yet the virtue of ions is precision memories that are both long-lived and programmable. With error bars, you can audit through repeated calibration and spectroscopy. Photonic memories begin with a paradox. Light refuses to sit still, racing forward at the ultimate speed. And that very restlessness is what makes photons so valuable. To persuade a photon to pause without destroying its quantum identity, you coax matter to share the photon's pattern, then later retrieve it by dialing control fields that release the stored shape as if time itself had held its breath. In practice, this looks like electromagnetically induced transparency in cold atomic clouds or warm vapor cells, where a strong control beam opens a transparency window and slows light to a crawl. When you switch off the control, the photon's shape maps into a collective spin wave across many atoms, ready to be retrieved on demand by turning the control back on. Other schema-soft resonant Raman processes, rare earth crystals with finely prepared frequency comms provide wider bandwidths, less sensitivity to noise, and the ability to store ultra-fast pulses with tunable delay. The greatest strength of photonic memories is their bandwidth and multimode capacity. They can hold dozens, even thousands, of distinct messages in time bins, frequencies, or spatial modes, creating a precious ability to launch many attempts simultaneously and raise the odds that at least one will succeed. The challenges are equally real. Signal-to-noise battles, spontaneous emission, and four-wave mixing, which can sprinkle unwanted photons into the channel if control fields are not exquisitely aligned. Most sources and detectors operate in the near-infrared or visible, while long-distance fibers favor telecom bands, so low-noise, motor-preserving frequency conversion stages become essential, lest the act of bridging distances erase the very structure you worked so hard to store. Progress, however, is steady. Cavities boost light matter coupling, allowing high-efficiency storage and retrieval at the singular photon level. Waveguides in lithium niobate and silicon nitride bring control pulses onto chips, and hybrid devices couple spin ensembles to microwave resonators, so that fast but forgetful superconducting processors can borrow optical memories as a pause button. Underlying all these platforms is a common scorecard that tells you which memory suits which job. Efficiency asks how much of what you store comes back as usable signal. Fidelity measures whether that return retains the same quantum character, judged by interference, visibility, and state tomography. Coherence time asks how long you can wait before phases drift intolerably. Bandwidth and spectral acceptance asked how broad and how fast your pulses may be. Multimode capacity asks how many distinct messages can be parked without crosstalk. On-demand control asks whether you can choose the readout time freely or must accept a fixed delay. Interface compatibility asks whether your memory speaks the right wavelength and spatial mode for the rest of the system. No single platform wins every category, which is why the field builds hybrids, ion or spin nodes for reliability and logic, photonic highways for reach, ensemble memories for throughput, and frequency converters and cavities as translators and amplifiers of the light-matter dialogue. The honest physics behind failure modes is as important as the headline numbers. Magnetic noise scrambles spin precession unless you stabilize fields and use isotopes with quiet nuclei. Motion-induced dephasing in atomic ensembles blurs the spin wave unless you cool or trap atoms or choose Doppler-free geometries. Spectral diffusion in solid shifts transitions over slow time scales unless you lock the environment and operate far from charge noise. Control pulses must be strong enough to open storage windows, but not so strong that they inject noise. Every extra optic or converter adds loss, and an adversarial audit will count each loss against your final fidelity. Turning a laboratory trick into a reliable device requires active feedback that keeps resonances where they should be, calibration routines that measure and cancel slow drifts, and protocols that order storage so that fragile states spend as little time as necessary in the most vulnerable memory for that duration. If you step back, a gentle philosophy emerges. Memory is not a single object, it is a choreography of when and where to hold structure so that it survives travel, congestion, and waiting. Spins offer a hand on the shoulder of a processor, allowing it to breathe. Ions offer a vault that answers when called, keeping a ledger of who stored what. Photons offer a river that can be dammed just long enough to let the water linger around the rocks before flowing onward. When you weave them together, networks stop being raw pipes and become synchronized instruments capable of staging entanglement across distance, aligning probabilistic events, and letting fragile quantum patterns arrive together at the moment they matter. That is the true test of a good quantum memory. Not that it hoards qubits for sport, but that it slows time just enough, with humility and precision, so the rest of the machine can do something remarkable. Then, without fanfare, it lets the stored light sing again in the exact shape it learned, delivering its message at the perfect instant. The lesson for you, the listener, is that every facet of your own potentially acquired inner compass, the disciplined vault of your skills, the swift messenger of your ideas can be cultivated, balanced, and brought together. Complexity will always be there, daring you to simplify or to dive deeper. But when you treat it as a compass rather than a wall, you turn each challenge into a new ridge to climb. You learn to store your insights, retrieve them when the world calls, and let them shine in the exact form needed to create impact. In the end, the journey is not about amassing every tool in isolation. It's about weaving them into a harmonious whole that lets you move through the landscape of possibility with confidence, grace, and purpose. So hold that compass steady, let the mountains rise, and know that each summit you reach is a testament to the power of embracing complexity, honoring the diverse ways you can remember, compute, and communicate, and, most importantly, to the unwavering belief that you can shape the future one thoughtful pause at a time.